pointer?
Oh, it's here. It's here. Sorry. Yeah, it was working earlier.
Okay.
That's good. Yeah, it works. Works. Morning, everyone. Welcome to the first session this morning. We've got a good program organized for you. First up is Andy Crivellin. Andy, you need to speak into this microphone. He's going to tell us all about lots of interesting anomalies in particle physics. All the speakers this session, I'm going to be strict with the timing, and I'll give you a 5-minute warning. It's 25 plus 5, okay?
Okay, good. Good morning, everyone. Can you even hear me without microphone? No? Okay. I have to try to stay close. Okay, so I want to talk about anomalies in particle physics. This mainly means, in this case, B anomalies, but I will also talk a little bit about G-2 of the muon. The Cabibbo angle anomaly, you might not have heard too much about this, but I think it's quite interesting, especially because it's related to non-resonant dielectron searches. The electroweak fit, W mass, said to be B bar. The W mass you definitely heard in the last times. And I will also very briefly mention some direct LHC accesses, but for this we had other talks, so I will not go into any detail. Then I want to give you one overview slide on how you can explain these anomalies by adding new particles to the standard model content. And then I will give you a very personal selection of possible common explanations of some of the anomalies. Okay. The first thing is we should always keep in mind, in order to not get frustrated because we haven't observed any new particles directly, is that the standard model must be extended. We know it cannot be the complete story. In fact, we only have found 5% of the particle content of the universe. We know that 95% are missing, and somehow you have to account for it. We also know that neutrinos are not exactly massless, and that we all exist, so that there's a matter-antimatter asymmetry. Now, these are well-established facts, but the point is there are many ways how to explain it with, in models beyond the standard model. And I think we got a very nice selection of possibilities here at the conference. But if you have listened to the talks, you really see there are a lot of ways to do it. And what is even more important, there are a lot of different energy scales how you can do it. For example, for neutrinos, you can add a right-handed neutrino from the KeV scale to the GUT scale. You don't know where the new mass scale is. So we only know that the standard model must be extended, but we don't really know from these observations what the underlying fundamental theory could be. And this is where all these anomalies, including the flavor anomalies, come into the game. Because if the anomalies I want to discuss in these talks are confirmed, it tells you there must be new physics at the TeV or multi-TeV scale. So it will be discoverable at the LHC or at a future collider, and it also leads to interesting indirect effects in other observables. So this is then really testable. And if it's testable, we can get a step closer to the underlying fundamental theory of nature, which we, or at least most of us hope, might also include supersymmetry. So how do we discover this kind of new physics? There are in principle 3 frontiers, and we had separate sessions for all of these frontiers. There's the cosmic frontier, the energy frontier, and the intensity frontier. But what I would like to highlight here with this graph is that it's not only a competition, but it's also complementary. So if hints for new physics or even an observation is made in one of the areas, it's also beneficial for the other 2 areas. So let's take the example of the intensity frontier. Here I will of course focus on flavor. And you say we confirm hints for beyond the standard model physics in flavor. Then this is of course great for the energy frontier, because there is something you can discover at the LHC or at future colliders. And it's also important for the cosmic frontier, because anything relatively light could lead to a new phase transition, to new sources of CP violation. So this has important implications for all of these frontiers. And I also think we need all of these frontiers in order to really get to the next standard model of particle physics. Only finding new physics in one frontier is not enough. We need to combine everything to get a complete picture. Now, as I said, I focus on indirect searches for new physics, including mainly flavor. Now here, how do you look for new physics? In principle, it's very simple. You produce many, many heavy quarks and leptons, which are unstable and decay to light fermions. Now, what you do is you just compare your experiment to the standard model prediction. And if it doesn't agree, this should be new physics. This sounds, of course, easy, but in fact, it's not. The experimentalists have the very hard job to do their experiment correctly. And then you also need a precise standard model prediction. For some of these processes, like mu2 3e or mu2e gamma, highlighted here on the right, it's very simple, because you just know in the standard model it's 0, even with massive neutrinos. For other observables, like b to s mu mu, here you have hadronic effects. Here the standard model prediction is not easy or simple, also like in G-2. But anyway, if you are sure that the experimental result is correct, and you are sure that your standard model prediction is correct, and they don't agree, this means there must be new physics. It's the old saying from Sherlock Holmes: if you excluded everything impossible, the remaining possibility, no matter how improbable, must be the correct one. So this means no matter if you like the new physics to which these anomalies point, if there is really new physics, that's the way it is. So even if it's not supersymmetric, if they really disagree, there must be some new physics. And the good news here is, if you look at this plot, I have to admit it's made under favorable assumption for flavor observables, but even then, what you can see here is you can test higher scales with flavor observables, then you can test directly at the LHC. So if you turn this around, it is possible to find new physics in these indirect searches for new physics before observing them directly at the LHC. And some people definitely know better than me. If you look at the last 5 decades, I think this is always what was the case. There were always indirect hints for physics beyond the standard model before we made a direct discovery. We knew to a good approximation the top mass from kaon mixing. We knew that there's something like the Higgs from electroweak precision observables. And then only later it was found at the LHC. So now the hope is that the indirect hints for new physics I want to discuss here, or at least some of them, will be confirmed in the future, and then later we can find it at a high energy collider. So the first class of anomalies is this B to SLL. You already heard about this in some parallel sessions for those who didn't attend them. What you look here are these ratios, RK and RK star. And the important thing here to notice is these are, you need hadronic quantities here called form factors to calculate these ratios. But since the muon and the electron mass can be completely neglected compared to the B meson mass, the predictions for these ratios are in principle just 1. Not exactly, but in principle. So if you then look what LHCb observed here is that you see both in RK and RK star, you find something like a 20% deficit. In fact, here in RK, LHCb even announced the first evidence for lepton flavor universality violation in a single observable. So this is also always important here because you compare muons to electrons, and the standard model gauge interactions don't care if you have an electron or a muon, and it differs from one. What you need is some new physics that discriminates between the lepton generations. It's also supported by this lambda B measurement, and so this really looks a very interesting hint for new physics. However, it's not even all you have. There are many more observables in which contain a transition of a bottom quark to a strange quark and a muon pair that significantly deviate from the standard model prediction. Most importantly for the experts of you, it's B sub S to phi mu mu, and this famous observable P5 prime in B to K star mu mu. Anyway, there are many, many more observables, more than 180, and if you include them all in a global model-independent fit, you have several scenarios which are significantly preferred above the standard model hypothesis of more than 7 sigma. Now, you might ask the question, there's no anomaly above 4 sigma. How is it possible that in a global fit I get 7 sigma? And the answer to this is that if you have heavy new physics, you can parameterize their effective interactions with this effective Hamiltonian, where you have an operator coupling bottom and strange quark to a lepton pair. And this has a Wilson coefficient, which tells you the effective interaction strength. And now, the important thing is there's very limited number of these effective interactions, which you can write down. And if you turn on this Wilson coefficient here, one Wilson coefficient affects many observables. So you do a consistency check. You turn on the Wilson coefficient, and you see if it explains all your deviations from the standard model predictions, while at the same time not messing up the observables that agree. And that this works is a consistency check. So it's like combining several decay modes of the Higgs in order to get evidence for its existence. So in the same way, you can combine here several B2SLL observables. And this is how you arrive at such a great significance. RD star, next hint for lepton flavor universality violation because you compare tau leptons to a muon or an electron. Here, the cross is the standard model prediction, not that precise this time because you can't completely neglect the tau lepton mass, so you get some residual dependence on the form factors. But here, what you see is from this red ellipse, it's something like a bit more than 3 sigma if you update the standard model predictions above the standard model prediction. This time, what you need is something like 10% new physics at the amplitude level, which is constructive compared to the standard model. And B to C tau nu, this is just a tree-level W diagram, so this is huge in the standard model. So if you want to compete for this with new physics, you need quiet light, meaning TV scale new physics with order 1 couplings. So something that could definitely be observed at a collider. Another anomaly you might not have heard so much about is delta AFB in B to D star L nu. So here again, this is a difference between muons and electrons. So this is a measure of lepton flavor universality violation. And here, in this analysis from Bobet van Dijk et al., using the Bell data, under conservative assumption, they found more than a 4 sigma deviation from the standard model prediction, which is again very clean here, because you can again neglect all the form factors. Now, what is interesting here is this is an asymmetry. So you need interfering amplitudes, and amplitudes with different Dirac structures. So you need a scalar or a tensor operator. And then this gives you a very nice connection to G-2, B to S mu mu, and also to RD star, which I'm trying to show here. So delta AFB is a charge current like RD star. It involves B quarks and muons like B to S mu mu. And it is chirality flipping and involves muons like A mu. So this is what I really think makes this anomaly quite interesting. It lies at the intersection of all these other anomalies, and I think it's definitely worth investigating this in more detail, especially for our experimental friends from Babar who haven't measured this, and of course Bell 2 will look at this in detail. The anomalous magnetic moment of the muon was already mentioned in the last part. Here, I think you all know the story about the 4.2 sigma deviation. The problem comes from this diagram here, where you can have any hadronic stuff inside. This makes the prediction difficult. However, if you believe in the data-driven approach of the white paper, you have this 4.2 sigma. Also important, the difference between the standard model and experiment is of the order of the electroweak diagrams, of these diagrams here. So if you want to account for this with TV scale new physics, you already lose a factor of mw squared over the new scale squared. So something like a factor 100. Now, how you can't gain this by the couplings if you want to stay perturbative. So how can you explain G-2 with new physics? The answer to the question is chiral enhancement. In the standard model, you do the chirality flip necessary for G-2 with the small muon Yukawa coupling, while beyond the standard model, you can do it with a much larger coupling. And then, in the MSSM, for example, our famous chiral enhancement factor is tangent beta, but generically, you can just do it with a sizable coupling to the Higgs doublet. What is also important is you can consider it as a sign of lepton flavor universality violation, because if you had new physics that were completely flavor blind, like the Schwinger term here, you would, and you aim at explaining G-2 of the muon, you would overshoot G-2 of the electron by an order of magnitude. So if there's new physics in G-2 of the muon, it cannot be flavor blind. It must again violate in some way lepton flavor universality. Non-resonant dileptons, that's also probably something most of you haven't heard about yet, but I find it quite interesting because here CMS observed 44 events while they only expected 29 plus minus 3.6 events with an invariant mass of the electron pair above 1.8 TeV. And then they also performed this ratio of muons over electrons. So again, a measure of lepton flavor universality violation. And then here you can imagine a curve, I will show this later, where you have, which goes below 1. So here you need this time constructive interference with electrons. Also, Atlas and Hera observed slightly more electrons than expected. So this is another hint for lepton flavor universality violation one should keep in mind. The next one, Cabibbo angle anomaly. So, you know, the CKM matrix within the standard model is by definition unitary. So it must fulfill the unitarity relations for each row and each column. The square of the elements must add up to 1. But if you look here, both first row and first column, you find something smaller than 1. Now, you see, VUD is by far the largest element. So if you want to explain this with new physics, it should probably relate it to the extraction of VUD. VUD is determined from beta decays. So how can you affect beta decays? You can either have a direct new physics contribution to beta decays. You can modify the Fermi constant because you need the Fermi constant in order to extract VOD from beta decays. And you can do it indirectly with a modified W mu nu coupling. And importantly, only W mu nu coupling works because the effect of a W E nu coupling in beta decays and muon decay drops out. So again, the Cabibbo angle anomaly you can interpret as a sign of lepton flavor universality violation. You can. There are other possibilities. You can also interpret it in the context of the Fermi constant, which is then related to the W mass. The next anomaly I want to come to. So, the W mass, the CDF measurement was 7 sigma away from the standard model. I would probably say, as a theorist, I can do this. The errors were probably too small, and maybe the central value was too high. But what is interesting, it goes in the same direction as the previous measurement. So already before the CDF measurement, there was a 2 sigma tension in the W mass. And now, if you increase the errors in a conservative approach, you end up with something like 3.7 sigma in the W mass, which I think is a reasonable estimate. And then there's also still this old tension in Z to BB bar. You again see B quarks, so this tells you naively maybe this is related to all the B anomalies we have heard about. So here the question is, how is the W mass and Z to BB bar, or is it related to the B anomalies? But obviously there's the possibility. Okay, this brings me to the summary of the first part of the talk. I'm not yet done. So here we have all the hints of new physics I talked so far about. So the first sector are all these hints for lepton flavor universality violation. So new physics that distinguishes electrons from muons from tau leptons. Cabeba angle anomaly, G minus 2 of the muon, B to S mu mu, B to C L nu, Q Q bar to E plus E minus. Now, after the CDF measurement, I think one should also look again at electroweak precision observables, but also since the Montreal conference, more and more hints for indirect searches are popping up. As I said, we had dedicated talks for this, and Sven also presented a nice overview here. But you see, it's getting more and more, so it really seems like there is something missing in the standard model. Okay, now how do we explain for these hints for new physics? I don't have the time to go into details. Please ask me after the talk if you want to know a bit more about any specific explanation, but this just tells you here how you could do this in a simplified setup in general. So the colored boxes, these are the anomalies I talked about, and some more I did not have time to talk about. And in the middle, the black boxes, these are the possible extensions of the standard model. So one possibility are leptoquarks, vector-like fermions. So this means new fermions which have the same charges under the standard model gauge group. This means that left and right-handed one are under the same representation, such that you can write down a mass term without breaking electroweak symmetry. So they can have masses at any scale. They are not confined to the electroweak symmetry breaking scale. New scalars, Z prime boson, W prime boson, which could be related via SU2, so belong to the same multiplet. And now you see here, for example, delta AFB is quite nice. You can show the only way to explain it is a leptoquark. So if this anomaly were confirmed, it would be circumstantial evidence for a leptoquark. For G minus 2 of the muon, there are many possibilities. It includes, again, leptoquarks or heavy fermions and scalars, which is just a generic case for the MSSM, where you explain it with your fermions and gauginos. B to S mu mu, again, quite a number of possibilities. Z prime works nicely. Vector-like fermions, scalars, also leptoquark, I've got the error here, sorry. RD star, probably you need to go for leptoquarks. And the W mass, you see here, there's really a big number of possibilities. But what the slide should tell you here is that by confirming or disproving any anomaly, you get closer to how you could extend the standard model. And of course, if you find a new anomaly, it's even better. Now, this tells you how can I account by adding one new field for a single anomaly. This is interesting to keep it in the back of your head, but of course we want to be more ambitious and we want to find a more unified theory. We are by far not yet there, but in the remaining, how many minutes?
3 minutes.
Okay, in the remaining 3 minutes, I will talk about some simultaneous explanations of the anomalies. The first very nice one is a vector leptoquark SU2 singlet. So this is also often called the Paty-Salam leptoquark because it has the quantum numbers of the one arising in the famous model unifying lepton number with color. It gives the right effect in data, no effect in BS mu mu, no proton decay at any perturbative level, so it works nicely. However, it's difficult to get a UV completion here. Standard Paty-Salam doesn't work because of k long to mu e and k to pi nu e, so you need something which is more baroque. There are many attempts, but nothing is yet conclusive here. But just assume you have a simplified setup with this leptoquark. What I can tell you is the agreement with data is amazing. So it's definitely worthwhile spending some more effort on model building here. You have RD star, RD over RD standard model, RD over RD star standard model here. You have a tree-level effect in B2S LL. And this here also generates a loop effect. I don't have time to explain you in detail how this works. You can ask me later. But it's really amazing that the preferred region from B2S LL, the yellow one, perfectly overlaps with the blue band from RD star. This could be completely differently. I really zoomed in. So the agreement with data is perfect. And it doesn't violate any constraints. So this is definitely something to keep in mind. We proposed here a model which is a bit also quite ambitious, explaining B to SLL, Kabibber angle anomaly, Z to BB bar, and tau to mu nu. What you do is you take the standard model here on the left, you extend it with a L mu minus L tau gauge symmetry, this time heavy, not like the light ones Julian discussed in his talk, and then you add two pairs of vector-like quarks, a singly charged scalar and a neutral scalar. The neutral scalar breaks L mu minus L tau and gives masses to the Z prime as well as to the vector-like quarks. So the vector-like quarks have naturally the same mass as the Z prime. And then you get a quite nice interplay here. So the heavy quarks mix with the standard model quarks, generating modified Z couplings. So this gives both Z to BB bar and the modified Z coupling B to SLL. This gives effect in Fermi in muon decay, explaining the Kabibber angle anomaly. This explains tau to mu nu, and this explains B to SLL. And if you put everything together, you really need all these ingredients. All the ingredients give the right effect, and for something like 1.5 TV new physics, you can explain it without violating LHC bounds. Second to last slide, Kabibber angle anomaly and non-resonant dileptons. This is also quite intriguing coincidence, or unless it's really realized in nature. You take the single operator here, C3. This is a left-handed operator coupling first-generation quarks to first-generation leptons. The 3 here means it is a SU2 triplet, so it contains a charge current and a neutral current. The neutral current explains the CMS data. The charge current explains the Kabibber angle anomaly via an effect in beta decays. And you see here the delta chi-squared, it's exactly at the same point nearly. So where you explain the Kabibber angle anomaly, you explain the non-resonant dielectrons. And if you add this up, you are at more than 4.5 sigma, better than the standard model. Final slide, BS mu, W mass, and Z prime mixing. Z prime mixing, if the Z prime is an SU2 singlet, needs to necessarily constructive effect in the W mass. Ben also pointed this already out before the W mass measurement. And then what you see here is that the electroweak fit in red prefers a non-zero mixing angle because of the W mass. And also B to SLL prefers a non-zero mixing angle because of the global electroweak fit where you would like to have C10. Anyway, you see again, this is in very nice agreement, these two regions. So you explain the W mass and B to SLL at the same time in a simple model with Z prime being an SU2 singlet. Okay, this brings me to my conclusions. There are many intriguing anomalies that emerged over the last years. A big class of them contains hints for lepton flavor universality violation, new physics coupling differently to muons, electrons, and taus. But there are also hints in electroweak observables and direct LHC searches. So you see here, it really ranges from the muon scale to over the nuclear, B meson scale, electroweak scale, LHC scale, even to the scale of an FCC EE. And if you look at all of this together, I think we cannot expect that all anomalies will be confirmed, but it still looks to me like the standard model is crumbling. So I think we have exciting times ahead of us. Thank you very much for the attention.
Thank you. Thank you for this very nice overview. Do we have any questions?
I don't believe your statistics at all. The
It's not
problem
my
is,
statistics, but
yes, it is. The problem is that you only fix those operators that explain the data.
you're talking about
that's a
B2.
posteriori choice, right? It's not a priori that somebody tells you you should take this operator 03 in your
But
last plot, right?
You're talking about B2SLL.
Anything, also your 4.5 sigma with one operator. But you only pick the one operator.
Yeah, but
if you want to put it properly.
I can well motivate that there's only one operator here, for example.
No.
No, I can't. This is, if you have...
No, you did not know beforehand that this operator would be the one. You choose this operator because it explains the data. But
Yeah.
that means you have sort of a theoretical look elsewhere effect. What you really should do is just fit everything. And when you do that, in this MEFT you have like 2,000 operators and your statistics is completely gone.
Yeah, this is why
Even
one
if you
should
take the electroweak fit, you have, I don't know what the number is, 200 or something. So really what you're doing is you're fitting 200 parameters, out of which 198 come out to be 0, plus minus within the error. But then your statistics is completely gone. Now that you have, from the first measurement, fixed the operators, then with new measurements, I grant you, you can choose this particular operator. But then it even turns out this doesn't necessarily work, right? Like with this forward-backward asymmetry, you wanted a different chirality than the RK ratio and so on. So you put some new operator. I think this is not proper statistics what you're doing there.
I mean, it's definitely proper statistics concerning the choice of free parameters. Now, how you arrive at the choice of free parameters, that's something different. I agree with you, there are many operators that could contribute, and this is also a reason why one should not stay at the level of effective operators, but move beyond it to simplified models, or in even a better case, to UV complete models. But how would you estimate such a look elsewhere effect? I mean, it's just...
Let's do the rest of this discussion in the coffee break. I think Steve's got a question.
Yeah, thanks. Nice talk. Could you? The vector leptoquark looks pretty good.
Yes.
But can it also explain the muon G-2?
Yes, the leptoquark is in fact one of the best solutions for the G-2 of the muon, because it gives you an M-top enhanced effect. So in this case, like M-top over mu, this is 1,600. So even for 10 TeV leptoquarks, you can easily explain G-2 of the muon. Let me see if I have a backup slide on this. I think there should be. It's amazingly slow. Yes, here. So this is one of the. So you can easily explain even for 10 TeV leptoquarks G-2. So this is this is for 1.5 TeV leptoquark. This orange boomerang here is the region preferred by G-2 of the muon. So you see, you can do it here with very small couplings for 1.5 TeV. For 10 TeV, it would be order 1 couplings, and you predict some effect in Z to mu, but you would need FCCEE to discover this.
Okay, thanks. Yeah, and just to make, I wanted just to say I'm going to be talking about twin Pati-Salam in my talk. So, yeah.
Ah, great. Yeah, but the Pati-Salam leptoquark is unfortunately the one which doesn't have an M-top enhancement. But I mean, if you have an extended scalar sector there, the scalar sector could contain such an M-top enhanced effect. Yes.
Okay, unfortunately we're out of time, so let's thank Andy again. Now we have Laura. You can do it. Okay, so that's for the laser pointer.
Okay.
Left and right. Okay.
Thank you very much.
And I'll give you a 5 minute.
Okay. Okay, so good morning and thanks to the organizer and to all of you. I'm here to discuss about a superspace approach to M5 brain, which is in fact I want to discuss a problem which is related to dealing with chiral p-forms in superspace. What I discussed is based on a recent work made in collaboration with the group in Torino Politecnico, Dauria, Trigiante, and me, with some postdoc, Norris and Ravera, and from the group in Alessandria University, Cremonini and Grassi. Okay, so the final goal of this line of research that we are pursuing is to give to arrive at two derivative Lagrangian description of the low energy dynamics of a stack of M5 brains at the full supersymmetric level, including all the fermion contribution. The final goal would be, in fact, to arrive at the action principle in superspace, but it is, of course, a very ambitious aim. For the moment, we already it was non-trivial to get the first step, which is to build the Lagrangian of an non-interacting tensor multiplet in flat equal chiral for zero superspace in 6 dimensions, which is in fact the dynamical theory living on the world volume of the M5 brane at low energy. The next step is already under construction, is the interaction with supergravity, at least in the cases which there are no, which is anomaly free. And then the more ambitious aim would be to add self-interaction and to embed in 11-dimensional superspace. But the problem is already at the first step, which is the fact that in general, in this kind of theory, there is a problem with a Lagrangian description of 2 forms which are an ingredient of the model and which are called chiral key 2 forms that I'm going to show. So I will first briefly sketch the model, the field content. Then I will discuss what is the problem about chiral forms in dimensions doubled of odd. And then I will show how the ergonomic approach in superspace, which is an approach developed in the Politecnico group in Turin, allows to solve the problem. And then I will show how a more recently appeared approach by Sen to this problem, which was in fact it comes from stream field theory as a more large application, but how this approach can be somehow embedded in our approach. Okay. So first of all, the model. Okay. What are M5 brane? They are assumed to be half BPS extended object of M theory, and they appear in the low energy 11-dimensional supergravity limit of M theory as black brane sources. They were much investigated, in particular during the second string revolution, and it was clarified that the world volume theory of the M5 brane is described at low energy by the dynamics of tensor multiplets in chiral equal 6 superspace with 16 supercharges. In fact, in this kind of in dimension space-time dimension 2, 6, and 10, one can have chiral fermions which which are not related by complex conjugation to their anti-chiral counterpart. Why this theory? Okay, in principle, the multiplet contains 5 scalars, which in the relation in the M brane description are the direction transverse to the brane in 11 dimensions, and fermions, which it is a Break supersymmetry. So the fermionic degrees of freedom are on shell 8. But then this is not enough to have matching of on-shell degrees of freedom, and in fact the world volume contains a 2 form to the index antisymmetric tensor, which however would account in general for 6 degrees of freedom, but then to have a matching of degrees of freedom, it is necessary that the bosonic field, the 2 form has to be chiral. It means that its field strength has to be self-dual, has to satisfy. This is a well-known fact, and this is a differential non-local constraint on the derivative of on the field strength of the fields, which is at the basis of the problem that I want to clarify here. What is the problem technically? Technically, it comes from the fact that, contrary to the 4n case dimension of space-time, in these theories, the self-dual and anti-self, you can have, it is an even dimension, so you can have self-dual forms, but they are real. And so you can have in a Lagrangian describing only self-dual or anti-self-dual forms, but any D form built by the product of two self-dual form or two anti-self-dual form is 0, just simply because of the property of the Levi-Civita operator. So a D form written in terms of self-dual forms is always different from 0 if you have a self-dual and an anti-self-dual form. So why this is a problem? Why I'm talking about this here? Because if one wants to write the kinetic term for the self-dual forms, the kinetic term involves self-dual forms whose kinetic term is then vanishing just because of this. So what is the way? But at the level of the effective Lagrangian, one can forget about the problem, work with unconstrained 2n forms, and then impose the constraint after, or to keep in mind that it is to be imposed. But okay, one would like to have it already at the Lagrangian level in order to go to, in principle, to go outside from the very low energy limit. And this is what I want to discuss here. So, in fact, the problem is well known and old, in fact. There were various strategies that were engineered to face the problem. Maybe I would say that the first one was, to my knowledge, was by Daura-Frey together with Regge in '83 with the Ioannina superspace approach that I will discuss more. It was in the case of minimal six-dimensional chiral theory. But then many were developed during the years with each one had some, all of these approaches are effective, but all of them have some advantages, but some drawbacks. And in particular, there were some formulations which were, however, not non-Lorentz covariant, so they were described as five-dimensional theory and then uplifted, or there were constructions with an infinite number of auxiliary fields. Then another approach was with only a finite number of auxiliary fields, in fact one, but in terms of a non-polynomial action where the derivative, the field strength of the auxiliary fields appeared in the denominator of, and in fact it was shown later that these two approaches were in fact equivalent. Then the Ioannina approach in superspace that I will tell much of my talk will be about this, so I will don't spend more here. And in fact, apart from the Ioannina approach and from some paper about the others, but very few papers face the problem at the full supersymmetric level. Most of them were formulated at the bosonic level. Recently, this problem became to new life, to new interest because of Sen, who proposed an approach that is in fact inspired by string field theory, and which is manifestly Lorentz covariant. It has a finite number of degrees of auxiliary fields. In fact, it is particularly interesting because it is rooted in string field theory, and somehow it allows to evade a possible no-go theorem for string field theory. That was, it was if a manifestly Lorentz invariant superstring field theory could be formulated, then it should be possible to have a low energy description, including a Lagrangian description of this kind of theories. In absence of this low energy description, it could be that it is there is a problem in formulating string field theory. So this is why recently people started to be interested again in the problem. And so I will discuss about the rheonomic approach, and then where we were able, at least for the simplest non-interacting case, to build a Lagrangian including the self-duality constraint, and then I will show how it is possible to embed the SEN formally, the SEN prescription at low energy in our framework. So what is the rheonomic approach? It is a geometric superspace approach to supersymmetric theory, which can be applied also to theories with chiral p-forms. The idea is that one deals off shell with unconstrained p-form fields, but the self-duality constraint is not to be put by hand, but it emerges from the field equation, Euler-Lagrange equation, in superspace of the Lagrangian, and also independently asking closure of the superspace Bianchi identities. So in particular, to my knowledge, it was applied in two cases to this kind of problem, chiral p-form. It was what I already cited, 6-dimensional minimal pure supergravity by Dabria, Frey, and Regge, and then more recently, 10 years later, to the 2B chiral theory in 10 dimensions. The advantages are that in principle it is a Lorentz covariant, no exotic auxiliary fields, and the drawback, however, is that the self-duality constraint does not survive the space-time projection. So the superspace Lagrangian includes it, but when it is restricted to space-time, it does not anymore. So some more details about the approach. It is a superspace generalization of Einstein-Cartan formalism. So the idea is that simply that supersymmetry transformations are understood as a supra-diffeomorphism, so diffeomorphism in odd direction of superspace. The full local symmetry and supersymmetry is encoded in the formal definition of the superfield strengths of the model and on their rheonomic, I will tell what this means, parametrization. I mean the parametrization of the field strength on an anolonomic basis of superspace spanned by Filbert forms and Gravitino forms. So the construction of a theory in this approach is based on two pillars that are in fact equivalent. From the one hand, one asks consistency of the rheonomic parametrization with Bianchi identity in superspace. As you know, since supersymmetry is an on-shell symmetry in absence of auxiliary fields, Bianchi the theory closes only, supersymmetry closes only on-shell on the fields. So Bianchi identities are not identities anymore in this case, but they are insightful relations which impose constraints on the fields. So in particular, these constraints include the dynamical field equation of space-time, but also the self-duality constraint on the chiral p-forms, but also the supersymmetry transformation laws, which can, on space-time, or the fields, which can be deduced from comparing the formal definition of field strength with the parametrization, and all the other constraints required for supersymmetry. However, This is not the only funding, the only thing that come out from that one can find from this approach. One can also construct, and this is what interests me here, one can construct a geometric Lagrangian, which is a D-form Lagrangian in superspace. And it is geometric. It means that it is written only in terms of differential forms and their exterior derivatives. Without use of Hodge operator, I will show in the last slide why this is important. So the field equations are field equations in superspace, which are K-form field equation, and their component along all the bosonic field bands are the dynamical field equation on space-time, while the component in direction, including odd, at least one gravitino, are in fact the requirement that the field equation hold, give constraints, all the constraints required by supersymmetry, including the self-duality constraint on the chiral P-forms. Finally, the restriction to space-time of the Rhonomic Lagrangian is supersymmetric invariant up to total derivative and with respect to the supersymmetry transformation law derived through Bianchi identities construction. So very sketchily, in this case, what we did, we deal with rigid supersymmetric background, which is characterized by the supertorsion constraint. The superfield band can be chosen like this, but in fact, having a geometric Lagrangian, it is not so important to choose. We can any choice of metric, any choice of basis of superfield band is fine. Then the matter content is based on a free differential algebra because we have a two-form and the rest of the field. So we have the free differential algebra for the two-form B, and the rest are the derivative for the spinor and for the scalars. Formally, one D2 closure gives the Bianchi identities, which of course take this form due to Firth identities, which always control the theory in superspace. And these relations are not anymore identities, as I was emphasizing before, but they are relations. So asking that a parametrization on a basis of superspace of the fields strengths satisfy the Bianchi identities turns out into precise constraint which determine the above this expression for the Rhonomic parametrization of the field strengths, and also provides a field equation, in particular for the spinor field, for the other follow by supersymmetry, and also the self-duality constraint. In this expression, just to say that the quantities appearing in the components along all bosonic field, and what in other approaches are called the supercovariant field strengths O. So the supersymmetry transformation laws can be read also from this approach, since they are diffeomorphisms in odd direction superspace. And so it is easy to recover them and also their restriction to space-time. The approach also gives, allows to derive a Lagrangian, which is a 6-0 form Lagrangian in superspace. So in principle it can be, in this approach, it can be integrated over any 6 submanifold of superspace, but in order to be independent on the embedding, it is of the bosonic submanifold in superspace, it is necessary that the theory be completely geometric, so that it does not include Hodge operator for the fields, because they rely on the choice of the metric and so on the choice of submanifold. So it is written as a first-order Lagrangian in superspace. This is I emphasize the term for the two-form. But so using some auxiliary fields, which through their equation of motion are identified with the super-covariant field strengths. And it also includes the self-dual constraint, but it is in the 2 psi sector of the variation of the Lagrangian with respect to the 2 forms, and also in other sectors. However, the restriction to space-time of the Lagrangian becomes very simple, trivial in fact, and it includes non-constrained B mu nu fields. It is, however, invariant of shell on the supersymmetry up to a total derivative, but of course it is formally invariant, but supersymmetry does not close on the fields. So, and in particular, one can see that the wrong duality part appear in the total derivative term, which misses the invariance. There is also, however, an associated neutral current, which on shell is conserved. We could in principle stop here, because this Lagrangian is well defined. At the classical level, it is fine, but and in fact, we are continuing in this direction, constructing the coupling to supergravity, which includes self-dual forms with the opposite chirality. However, I want to spend the last minutes to show how this approach can be modified slightly to implement the same prescription not only on space-time but also in superspace. Very short, I will not enter into the details. The formulation of SEN includes an extra chiral form which has a wrong kinetic sign, but it is fully fully decoupled from the sector. And this decoupling holds not only at the classical level, but at all orders in perturbation theory. It was in particular studied for the 2B theory in 10 dimensions, but in the decoupling to the gravitational field included a strange, let's say, non-standard formulation of general coordinate transformation. Then it was applied already into our model, let's say, in the equal 6 chiral theory by Lambert. And but what we are going, I want to show in the last minutes is how this formalism can be applied to our superspace Lagrangian. So there is in fact a complication of our model. In fact, that it is a first order description. So we have 2 ways to face the problem. One is to pass to second order, and this in fact is something that we are doing through the group of Alessandria, Cremonini, and Grassi, but this relies on the construction including integral forms, which is, I will not talk here, or we can reformulate same prescription such that it holds at first order, and then to modify our Lagrangian such that once restricted to space-time is equivalent to same prescription, but its Euler-Lagrange equation in superspace are the same of the bosonic one. Okay, I will skip all the details and pass only to the conclusion. So the point that we have constructed a supersymmetric invariant Lagrangian in 6-dimensional superspace for tensor multiplets in rigid chiral theory with 16 supercharges, whose field equations in superspace include the duality constraint for the 2 forms. But we have also then modified SEN prescription to a first order one and to a description in superspace, such that to incorporate his findings. Next steps are then, to add the interaction with supergravity, at least for the anomaly-free case, and try to apply our extension of SEM prescription in this case, which is more challenging because already SEN had a non so clean description, in my opinion, of what happens. At least I did. It was not so clear for me. Is a description of general coordinate transformations. Or then the other way is to extend our Lagrangian to Lagrangian in the full superspace, so to work at second order and by adding appropriate integral forms. Or then the very far is to try to go off shell in some way. Okay. Thank you very much for your attention.
Thank you. Do we have any questions for Laura? Yeah.
Thank you. It's very interesting. Yes. So I don't have it very clear yet. So imagine SEN will not have done what he had done.
Okay.
So the problem with the renomic approach would be that it is very well implemented in superspace, but not in the component action.
Yeah.
Okay.
It is. I mean, it is fully well defined and everything is well in superspace. And the Lagrangian is a superspace Lagrangian, includes the constraint. However, if you restrict it to space-time, you lose. The superspace Lagrangian contains much more than its space-time restriction.
Okay, but and the other way around, you start. So what would you add to SEN? For instance, SEN already said, well, I have an approach to deal with
the fact is that the SEN approach does not. Okay, it describes very well the frame in string field theory, but about the low energy limit, there is not a so well defined description at the supersymmetric level.
Okay.
It gives just some general description, and in particular, it needs for its description in the gravity case, so at the level of flat, the rigid superspace. It is very clean, also the description of SEN, and okay, but it is not so clean how at least in my opinion, how it describes the coupling to fermions. In coupling to supergravity, the problem is that it uses a weak gravity limit, which I think it should be at least covariantized somehow, and this is one of the aim of our approach.
Okay, thank you. Thank you.
Hello. In the different theory, we can have the Poisson structure and know how to deformation as in the Moya product. But in a different theory, we can have the Poisson structure and also know how to deformation as in the Moya product. And for this approach, we have the C-field background. Could you find the number Poisson structure and know how to deform this number Poisson structure?
Which structure?
Number Poisson structure. Because C-field background, you should have 3 slots for the product. For this Poisson structure, but the one problem in the M5 brain is that we do not know how to deform this number Poisson structure because we have a main no-go theorem.
I don't know how to answer your question, but I know that in the SEN paper in 19, he discussed in detail the Hamiltonian structure of the model. And so, including all the Poisson brackets.
So you say Poisson structure or number Poisson structure?
Poisson or number Poisson?
I don't know.
Okay, thank you.
Sorry.
Yeah. Let's thank Clara again. We move to the next talk. Fernando Quevedo.
Okay, well, thank you very much for the invitation to come to this conference. I always love to come to Ioannina. And this is a work that I have been doing with my collaborator, Cliff Burgess, for the last few months. And it has appeared in several papers, and one together also with Doreen Daniel, who's a student of Cliff. And so I have SUSY in the title, so I think it's appropriate for this conference. And so I'm mixing several things: nonlinear supersymmetry, vacuum energy, and inflation. Just as a spoiler, I can tell you that this is an idea we try to step away for a while about at least my natural environment, which is just a stream phenomenology, but just to think about a bottom-up approach to think about things like the dark energy. And the spoiler is that, of course, as most of the attempts to understand dark energy is not straightforward, so we cannot claim any success so far. But I think the ideas that we have been coming up with, I think they're interesting and maybe have some applications of, and in particular, we are exploring that for understanding better inflation in some contexts, in particular within string theory. So the outline is I will give you a general motivation and introduction, the idea of nonlinear supersymmetry and dark energy, and then towards a UV completion and inflation. So the introduction. So in general, I would say, as we all know, low energy supersymmetry has a lot of positive properties, but I call low energy means of the order of TeV, because I will go to lower energies later on. And of course, the original motivation is the hierarchy problem, then the success of unification after LEP, then the dark matter candidates with the neutralinos, the nice explanation of the Higgs potential. And so all of these have been always positive things about the supersymmetry that we have been working for many years, and that's what essentially the field has been developed from the low energies. But also it has some negative things that, of course, it hasn't been seen yet, that we didn't know in the past, but now we are at the moment, which is a difficult moment to see if it will be actually seeing in the near future. It has many free parameters. Once you put soft breaking terms, you have so many free parameters, and so it's not nice. But what I think is the most important problem that at least I used to emphasize in my lectures, for instance, is the issue about dark energy for supersymmetry. So supersymmetry is approaching one hierarchy problem and is totally forgetting about a bigger hierarchy problem, which is dark energy. So the question is, if anything solves dark energy, that may also apply to the hierarchy problem. So maybe supersymmetry is not the full approach. So that's the motivation to do what we have been doing. So recall the hierarchy problem. We have the standard model written in terms of operators for the dimensionalities of the coefficients and the operators up to 4. And the leading order, of course, is the cosmological constant. And dimension 2, we have the Higgs mass. And dimension 3, we have, of course, if there are right-handed neutrinos, there will be a right-handed neutrino mass, which is not that relevant for my talk. And then all the other ones are dimension 4, and then we have the whole standard model effective field theory for higher order operators. And of course, the problem is these leading order operators, how the coefficients are too small. And in particular, if the Higgs mass is 10 to the minus 15, which is the hierarchy problem, we have a much bigger hierarchy problem, which is the cosmological constant problem. So as I emphasize that the problem may be that we have been concentrated too much on this part and forgetting about this when we talk about supersymmetry. So, sorry. Yeah, so the question is, can we address both problems at the same time, in particular with supersymmetry? And there is one approach, which is the string landscape, after the ideas of anthropic ideas, but for Weinberg, Busso, Polchinski, and others. It is everybody's favorite idea to hate, essentially. But I like to be provocative and call it is the worst solution to the cosmological constant problem, with the exception of all the other ones. So essentially, we have to take it seriously, because if anybody has a better solution, most probably it will be killed in a few minutes after you discuss it. But as this one, we hate it because it relies on anthropic arguments, but there is no alternative to it. And it addresses the whole point about the cosmological constant problem. So, and it addresses the two things, of course. So you can have the anthropic arguments towards the cosmological constant problem, but also you can have even at low energies, you can address similar arguments for the hierarchy problem. And that has led, for instance, for many people to like the version of this split supersymmetry as a particular realization of low energy supersymmetry that still doesn't solve the hierarchy problem, but keeps many of the good properties of low energy supersymmetry. And that fits with this. So in that sense, this is, as I say, is the best thing we have in time. And it's very important because it may be the right solution. So that's, I have to say that it cannot be even claimed, this is just a proposal. There's a lot of effort towards really implementing this, because you have to get solutions, real solutions from string theory or anything else that give you the sitter, and that's a big debate in the community at the moment. And even though we have had several talks about string models from here, I think it's fair to say that at the moment there's no model of string theory, even though this landscape looks very huge. There's no model of string theory that is realistic. And then the structure of this landscape has to be actually explored. So, and that's a lot of challenges there. But at least as a setup, it's very formulated and addresses the two problems, the hierarchy problem and the cosmological constant problem. The question is if there are alternatives to this, and that's what we're trying to discuss. So, as you can see, I'm critical, but still I think that this is something to be taken seriously. But I would like to also explore if there are other possibilities, and that's what motivated our work. So let me just remind you what the relationship that the string theory, supersymmetry, the supersymmetry has had with dark energy. And historically, it's interesting. You start with global supersymmetry, the potential, the F-term potential. It takes this form, is positive definite, and then the order parameter of supersymmetry breaking is precisely the vacuum energy. So in that sense, it is very, very, very closely related to the vacuum energy. And of course, it cannot be the solution because we know that the world is not supersymmetric. So this cannot be zero, and then we have the problem. That was global supersymmetry. In supergravity, the nice thing is that you have the famous negative term in the F-term potential. Then it makes two things. One is that it allows to have supersymmetry broken, cancel in this term, and then you still get a zero or a small cosmological constant. So that's a progress somehow, because these are the F-terms. And the other possibility, the other thing that supergravity gave us is the no-scale supergravity, in which says people found, Kremer et al., that particular form of a Kerr potential such that this cancels automatically, and that's the famous no-scale supergravity. And extensions of that, we call extended no-scale, we even modify this, the log of tau to log of tau plus a function of other fields, still keeps this property. And so in that sense, that's something very interesting. However, we all know that this is only true at the leading order in expansion, and after once you include loops, this property disappears. And that may not be that bad at the end, because we think that the cosmological constant is not zero. So it can be small, but not zero. So in that sense, corrections to these things can be there, but they don't have to be little. And something that I criticized a lot in the past is that people use supergravity to models of quintessence. It's all supersymmetry is perfect to address flat potentials. And for instance, they had this dynamical supersymmetry breaking potentials, groups, Binet-3, Copland, and many others in the past, and then use these supersymmetric potentials or superpotentials to generate flat potential that can give you quintessence, and that would be, they saw that would be interesting. I was very critical to this because this is a very low energy physics, but whatever is quintessence, and we already know that supersymmetry had to be broken at the TeV scale or so. So how can you keep working on supersymmetric Lagrangians at lower energies relevant to quintessence? So I was always critical to them, and now I have something to argue that in this direction. So there's something to keep in mind. So please remember these different approaches. Okay. The other ingredient is nonlinear supersymmetry, that it has been discussed here by I think Dudas and other people. And but let me start with the multiple splitting in general. The mass of the bosons and the mass of the fermions are different, and that is proportional to the F terms times the coupling. So that motivates something that you can say that the weakest coupling will be gravity, so that means that you expect that naturally the smallest splitting will be in the gravitational sector, not necessarily in the standard model sector. Okay? So that's something to keep in mind. And experimental bounds, we know that in the standard model, the split of the masses is of the order of a TeV or so, but in gravity it's much smaller, because the constraints using the gravitino with the cosine component, you can put bounds and it's smaller. So that motivates the fact that you can see maybe the gravity sector is more supersymmetric than the standard model sector. Okay. And that motivates to study nonlinear supersymmetry in the sense that we treat the standard model in terms of nonlinear supersymmetry and then gravity in a supersymmetric way. So that's what we have, and then we propose, or we study this possibility, have a natural relaxation of the cosmological constant from the standard model, question mark. And this is work in progress and not yet a UV completion, so it's not, we're not claiming success, and I can show you what the challenges are. So the ingredients we have is a Gaussian superfield, X, such that besides being a chiral superfield, satisfies X squared equal to 0 as a superfield, so it has only the Gaussian component as a dynamical, and of course the F term. And as Dudas and Faragos talks have already mentioned this. We need what is called a relaxation mechanism to reduce the leading order contribution to lambda. That essentially takes care of the global supersymmetry part of the potential that I told you was positive, definite, and big. So we need a field that does that. And it is nonlinearly realized, and so that field satisfies d bar x phi bar, so it's equal to 0, or if it is real, we can have x phi bar equals to x phi. We call the relaxant superfield. And then in the gravity multiplet, beside the graviton and the gravitino, we have a scalar dilaton superfield, superfield, which is linearly realized, and that keeps track of scaling properties of the Lagrangian. So these are the three ingredients that we will discuss. And they are, of course, all of them are present naturally within string theory, but this is just a bottom-up. And just to give you an idea of the scales and threshold, we have the Planck scale threshold, we have the standard model, the superpartners will be heavier, so that's why we treat nonlinear supersymmetry, and gravity is more supersymmetric, so then the gravity multiplet and the dilaton multiplet will have smaller splittings compared to the standard model. So, and we will be interested, not in this part will be the UV completion, but for us the UV essentially will be from this energy and below. So we want to talk about the standard model scale, but not below the superpartners. So the theory we will consider is this one. So the standard model will be non-supersymmetric, so non-linearly realized, whereas gravity can be linearly realized. Yes, exactly. So if you do then it's something, it's an exercise which I enjoy very much thinking about it. I will try to encourage you to think also, is to treat the standard model in terms of nonlinear supersymmetry. There is something that Emiliana and Ignacio called in the past the nonlinear MSSM, but in that case, only X was included nonlinearly and the rest of the standard model was linearly realized. Here, everybody is nonlinear. So you can include the quarks and leptons of fields Y with a constraint X times Y equals 0, where X is the X squared equal to 0, the Gaussian superfield. So that makes the case that Y has only a fermion but not scalar component. The gauge superfield, W, you have XW equal to 0, the same thing. You have only the gauge boson but not the gauge genome. And the Higgs has satisfied this constraint also, d bar X, H bar equal to 0. That's in general d bar X, F, H bar equal to 0. I will call this the nonlinear MSSM somehow. You can write the bosonic Lagrangian in terms of a carrier potential and superpotential. But look at, there are already different things. There is no second Higgs because first of all, there is no need of a second Higgs for anomalies, and also it has been everything has been integrated out, and then there is no mu term, so no mu problem. For instance, in this formalism, the Yukawas, we can have the standard Yukawas for the down quarks and the leptons, but for the up quarks you get it from the carrier potential, and again anything coupled to X. So in that sense, from this you can write a supersymmetric theory in which the standard model is non-linearly realized and the gravitational part is linearly realized. And so you have interesting properties. I think it deserves to be explored phenomenologically. I don't think it has been done. Well, the Lagrangian will have an expansion in different terms, and when we keep track by this expansion in terms of the tau field, which is keeping a scaling variance. So each term is scaling in a different way, and that is a way of counting a perturbative expansion. So then the log energy action we write like -3 log of P, and P start with tau. That will be the first. That will be the no scale part. It has a next term which is independent of tau, and then an expansion 1 over taus. So for large tau, this is the dominant term, and that will be no scale. And even in the next order, you have a tau minus k that is still what people call extended no scale. Still, they give you 0 potential, and only starting with this next expansion, that you will get a smaller contribution to the cosmologic, to the vacuum energy or to the potential. And the superpotential is superpotential depending on the fields plus x times w on phi, and and you can have a 5-bar dependence in the superpotential because of the constraint. So in that sense, it's not holomorphic on the fields as long as you have the superfield X. And that's another property that is different from the standard MSSM. And then the scalar potential, you write it in terms of going to 1 over tau to square, 1 over tau cube, because this is a square and 1, and 1 over tau to the 4, and so on. And so you have to consider so we have, as I told you, the scalar potential, we have the expansion, and this expansion state is dominated by or given to you by the scaling arguments. However, these coefficients, the coefficient of the expansion, in principle can depend on the log of tau. The scaling, the powers of tau are okay, but there can be log dependence on tau, which is a standard in field theory, because tau measuring the scales, at the end you have logs of ratios of masses, and the mass depends on tau, so that means the ratios of masses generally will depend on tau, and that will give you a log tau. And once you have logs, you think about the normalization group, so you can have a resummation of all that. Including logs has been discussed in several papers. In string theory is not yet fully established, it's something to be discussed, and I think Ignatius mentioned them in his talk. The interesting thing, sorry? Good. Oh, wow, thank you. So the interesting thing is that once you have that and you have a normalization group resummation, you have naturally alpha log of tau of order 1. This is once you do the resummation of the logs, you're resuming that, and that gives you that log of tau is of order 1 over alpha, so tau is exponentially large, and that's precisely what we want in this expansion of 1 over taus. So we have a concrete example with this expansion, and we have minima, which are de Sitter and anti-de Sitter, and with very large tau. And then we have scales, and this is the sad part of the story, the bad part of the story. The standard model particles depends on at the end they end up to be 1 over tau to the 1/2, and the neutrino is 1 over tau, so that essentially gives you the hierarchy to work well. And for tau 4 to the 10 to the 28 or so, you have the right scalings, and you almost get the vacuum energy in the right way, but you have to satisfy some constraints. In particular, the F terms have to be bigger than the TV, and then the best we can do is lambda 10 to the minus 90 something. So in that sense, we cannot get all the way to 10 to the minus 120, but at least it is interesting to consider. You have to worry about feed forces if these fields are too light, and for that we need a screening mechanism. We have proposed one, but we're still working on that, so that's something we have to be critical in that way. The screening mechanisms that exist in the literature do not apply in general here, and we came out with one in terms of using the axion as a way to screen, but it is not yet finalized. There's a cosmology you can study here to see when this is the potential, you have the minimum in the log, and then you can follow the evolution of different components, the matter, radiation, and the potential of the dilaton. In this case, the field runs away, but once you include the whole action, then at the end, the evolution is such that the field stays in its minimum and dark energy dominates by the minimum. And this is how the field evolved itself when expansion of the universe. So that's the cosmology part. Okay, so let me just finish with a UV completion. And so this relaxon field that I introduced, it looks very arbitrary. Thinking about string theory, I didn't find any connection with what a string theory could be. But then we realized that the potential has, I remember I told you we started with 1 over tau squared, 1 over tau cube, and 1 over tau to the 4. At the minimum, these terms are essentially 0, and then you get over 1 over tau to the 4 with the logs. But outside the minimum, these terms dominate. And then you get a potential where at the field, which is in this case, the potential is a function of phi, because these are functions of, then you get functions of phi. You have an inflation potential, and at some point it relaxes to the minimum. So then at large values, so while it inflates, tau is not that large, so these terms dominate. And after it finishes inflation, it goes to the minimum. These terms essentially vanish, because this is, that will give you the zero of the potential, the minimum of the potential. And then you have right now at late times, you have tau very large. And a small cosmological constant, but in the early universe, tau was not that large, and Wx was different from 0, which is the phi dependence, and then this field, which is the relaxon field, happens to be the inflaton. The nice thing is that, 2 minutes, perfect. The nice thing is that we have a string theory version of this, so I tried to avoid the string theory until now, but the string theory version of that is, so, and people have done that all the last 10 years or so. This is, but then the relaxon, you can think, well, what will be the relaxon in this picture? Because the standard model may be here. If you live in an anti-brane, the standard model will be non-supersymmetric, whereas the rest will be supersymmetric. So that fits precisely with the scenario we have. And the relaxon field happens to be, perfect candidate is to be a brane going towards the anti-brane, and while it approaches each other, the field inflates, and that's precisely the effective field theory you get is of the type I was describing, and the relaxon field will be the separation of the branes. And so that is nice and addresses one problem that people had. You know, brane anti-brane inflation has been around for almost 24 years, and it had something called the eta problem. The eta problem is that once people tried to formulate this inflation, you had sorry. The eta was of order 1, whereas here the way that we stabilize the fields is perturbative, so eta is the eta problem is disappear. So I will just finish with my talk. Oh, well, let me just say, say just the last, then you can end inflation, and that's a nice way of inflation by attacking from the brain and anti-brain, and the Higgs field can play precisely that role. So that's an interesting observation. Okay, so conclusions. We have a discussion that motivated by just trying to understand alternatives to the entropic proposal of the dark energy. We got a little bit far, but not far enough to actually claim success. There are open questions. Some issues have been improved, like, for instance, the treatment of supersymmetry. When you talk about late-time cosmology, we can do it by using this. So in that sense, the criticism we used to have to the people doing that in the past still applies to them, but doesn't apply if you do non-linearly realized supersymmetry. But still, we don't get the scale to work. You need UV completion to get such a large values of tau are not clear, because if tau, the natural thing to be is the volume of the extra dimensions in string theory, and then you cannot have the string scale to be too small. So that puts a bound on how large tau can be, so it cannot be larger than 10 to the 20, and we needed 10 to the 30 or more. And of course, there are many open questions to be understood, so I think it's an interesting subject to study further. Thank you very much.
Thanks, Fernando.
Okay, thank you. Very nice talk, Fernando. My question is, since in your effective theory you have the standard model, so you should have quadratic divergences. And so this means that the hierarchy problem, well, is around, no? The hierarchy problem?
No, that's precisely, yes. So my concentration here was using the TeV scale and above, but some UV complete theory that takes care of that. So the problem we're addressing of the dark energy is what happened at the standard model and below. And this non-linear supersymmetry is precisely giving you that. So in that sense, we're addressing, say, the difficult part, although not too high energies, of the dark energy, if this will have worked. So essentially, you can take care, the supersymmetry is good for that, because essentially the fact that you have a because you have non-linearly realized supersymmetry fully, it is the same as not having supersymmetry. But you have non-linearly realized supersymmetry in the standard model, but there is this protection of supersymmetry from supergravity, from the gravity part. In that sense, supersymmetry is still helping you there. So, well, I don't know if that addresses your point, but,
okay,
but
we can
exactly.
speak privately.
Okay, very good.
Perhaps, yeah.
Yeah, thanks. Nice talk. Does modular symmetry play any role in this framework?
Modular symmetry?
Yeah.
Not really. That's a good point. Yes, usually people use the modular invariance of the taus, and so because this the -3 log of tau scalar potential is invariant on the SL2R. And usually, in string theory, this SL2R is broken to SL2Z, which will give you a modular invariance. And the way to do it is that there will be a non-perturbative contribution to the superpotential that depends on tau, on the whole superfield tau, and that will compensate. So you can have something like a modular form divided by the dedicated eta function to the power 6, or something that will make you something invariant. These are non-perturbative effects. And there will be, in our approach, since we are concentrating on tau to be very large, these non-perturbative effects go like powers of exponentials in minus tau. So in that sense, they are subdominant somehow. So in that sense, if we concentrate at the larger values of taus, they are much more suppressed. If we go to very, very taus of order 1, then they will be relevant. But at that level, we don't know if we can trust effective field theory, because the effective field theory, you have to assume that you have a volume large enough to be valid.
Okay, thanks.
Okay, there are several more questions, but I think we're out of time. We should ask them at the coffee break. Thank you.
Okay. when we have to have the solution outside and inside, we have to match the person. And the unison, but some general classes for all the unisons, we will think of what we want. And for that, we should be matching with the software.
But in paper, I think you got like proportional to like the standard matter, right?
Yes. But we just do those things. But now we have to try and bring new solutions. And it's not working.
wanted your reaction.
That's why
They still accept the landscape. They don't accept that there are possibilities.
Yeah, they accept the landscape.
So the landscape they accept can also.
Yeah, that's in the work.
Yes, it cannot help us.
Exactly, so it's not another addressing this.
Yeah, I mean, they say that there is no specification.
Yes, yes.
That's how. But I mean, you know, often saying that this is a solution. Then you imply.
Okay. For the audience. 2 minutes. May I kindly ask you to be seated?
No, it's this.
Do you know how to use that?
No, but it's the push.
That's the laser.
And this works.
Yeah, and I have to talk here.
Yeah.
Okay, let's start our next session. Our first speaker of the session will be Keith Olive. He will talk us about gravitational portals and particle production during reheating. Okay, thank you. 25 minutes.
Okay. Okay, so I'm going to be talking about really the end period of inflation where reheating starts, and I'll be talking mostly about non-instantaneous reheating, and so we should distinguish that from, say, non-instantaneous thermalization, which is what Emmanuel talked about. But I'll go through what actually happens at the end of inflation, and in particular how that leads to particle production, and then I'll get to gravitational portals that they're always there. These are gravitational production mechanisms which just use minimal gravity as the mediator. And as examples of that, so I have to have some background example to work with, and for that I'll start with Starobinsky models and give you a little bit of an idea why, and then T models that were proposed by Kalash and Linde. So just to start, probably most people know, but at the end of inflation, inflation itself is governed by the scalar equation of motion. This, for example, is the Starobinsky potential. Mu, the parameter mu that sets the scale here, is set from CMB, and the normalization of the CMB anisotropies. And in principle, you start out at large field value. The inflaton here evolves towards lower values. There's at some point where you reach, in this case, where x is about 5. This is all in Planck units, where x is about 5. That's where about the last 50 e-folds of inflation begin. And then at some point, inflation ends when x is about 1. And that corresponds to when one of the slow roll parameters is about 1. It's really when the acceleration of the universe starts to vanish. And then after that, the inflaton goes through a period of oscillations, okay, in this kind of a model. What happens next is that you start entering this period of reheating, and we'll define the moment of reheating, if you want, as when the radiation density is equaling to the inflaton density, that is the density left over in the inflaton oscillations. And given that as your definition, you can compute the reheat temperature in terms of the inflaton decay rate. And I'm going to parameterize the inflaton decay rate as just y squared over 8 pi times m. M in principle, as you'll see later, can be a function of phi. And y could also be a function of m if you want. If you're talking about gravitational decays, y might go as being proportional to the mass of the inflaton over m Planck. And that leads to this reheating temperature. So for y of about 10 to the minus 5, for example, you would get 10 to the 10 GeV. Okay, so that's all pretty standard, I think. And then during the period of oscillations, and this is what I'll be talking about mostly, is that's what leads to particle production. So let me just back up and say a quick word about Starobinsky model, in case some of you aren't familiar with it. So this was really one of the very first models of inflation proposed before what we call old inflation due to a first-order transition of a gut symmetry. And this was really designed not to solve the standard cosmological problems, but more to solve the singularity problem, is what Starobinsky had in mind. And he wrote down a modified theory of gravity, r plus r squared. But if you do a conformal transformation to the Einstein frame, then you can write the action this way, and out appears a scalar field with a potential, and that potential is that potential I showed a little bit earlier, is the Starobinsky potential for inflation. It's quite nice in terms of Planck, in this case Planck being the experiment, not Planck the mass scale. But you can write you can write the Starobinsky potential in different ways. You can compute very easily the slow roll parameters. As I said, you normalize to the microwave background anisotropies, and you get the mass scale that's sitting in front of that potential. And the slow roll, then the tilt of the anisotropy spectrum comes out in very good agreement with experiment, and there's a prediction for the tensor to scalar ratio. Now, in the back of my mind, so this is supersymmetry, I have, how does this come from a supersymmetric model, and can we find a model for Starobinsky consistent with Planck? And a number of years ago, John and Dimitri and I were looking at this, and starting with a no-scale model, actually it's like the extended type that Fernando just talked about, so minus 3 log t plus d star, and then the matter fields here. And if one of these fields has a superpotential that's given by a very simple form, and I think Dimitri talked about this as well, just the phi squared minus phi cubed superpotential for specific choice of lambda, this will lead exactly to the Starobinsky potential. And the way that works is that once the T field picks up a VEV, so we're going to assume it picks up a VEV C, I'll then set C equal to 1. The potential has the global form, so it's as if you had a global supersymmetry with a conformal factor here. And that if you canonically rescale the scalar field, then you get exactly the Starobinsky potential. So choosing lambda and C, the scalar potential looks like this. And then when you go to the canonical field values, you get exactly the Starobinsky potential. And so that is the black line here. This is an old plot. I'll show something newer in just a moment. But this is how sensitive it is to that choice of lambda and the values of this tensor to scalar ratio that you get in that case. So the inflationary context is that assume no scale supergravity. Most of what I'm going to talk about actually doesn't rely strictly on this, but I still, in the back of my mind, this is the context that I'm using. So the Starobinsky potential is derived with this superpotential and that Kähler potential. I'll also talk, and actually probably more, concentrate on these T models, which I can write like this, and you say that's a funny form for the potential, but it's derived from the same no-scale supergravity model with a superpotential of this form. And it looks maybe a little bit funny, but it's not that strange. So for example, for k equals to 2, which is sort of the baseline model that I'll always be referring to, k equals 2, this is phi squared minus phi to the 4th. Okay, so it's nothing that unusual. And the potentials look a little bit like this for k equals 2, 4, and 6. And the nice thing about this is that when inflation is done, when we're talking about particle production, phi is much less than 1. And the series expansion for this is just a polynomial, so it looks like phi to the k around the minimum here. Now, another thing that we've looked at recently is how this now compares with the newer results from Planck and Bicep and Keck. And so here's the current plot. And I'd want to just make one point here, is that this band here, which the band always guides your eyes to that's what you should be looking at. But this is not 50 to 60. Most people plot the little band to be between 50 and 60. 50 is here, and 60 is here. And though that's not really realistic, because the number of e-foldings, this n star that you have till the end, is not something you can just choose. It's something that depends on the reheating temperature, among other things. It depends on the equation of state. It depends on the inflaton potential as well. But you see, this is the inflaton decay coupling or the reheating temperature, 1-to-1 between those. But you're not going to get up to n equals to 60. You can get, for y equals to 1, you can get maybe up to n equals to 55. So here's y equals to 1. And really, we even put a cutoff that you shouldn't have reheating temperatures bigger than that, which would lead to a Gravitino problem. So if you want to avoid the Gravitino problem, and you want to have reheating above, say, the electroweak scale, that's what this red band is. And this is for the Starobinsky model, and this is for these T models. Alpha here, by the way, you see that it's a band because we're just changing -3 log to -3 alpha. But I'm going to be sticking with alpha equal to 1 for the remainder of the talk, and really now concentrating on these T models. So what happens post-inflation? Well, we have the equations of motion. We're allowing for the inflaton to decay. So we have the decay rate. And then you can now solve the equation of motion for the energy density of the inflaton, the energy density of radiation. You have the Hubble parameter, which we assume is dominated by the inflaton energy density. The equation of state parameter, normally you would just take that to be 0 if k equals to 2. So k equals to 2 is the one where you have a quadratic minimum. K equals to 2, W is 0, and you get something that maybe looks a little bit more familiar. So now what happens? The inflaton starts its oscillations, and we can separate this out into the behavior of the amplitude of the oscillations and the periodicity of the oscillations. And the amplitude it's very simple to work out from the equation of motion what happens to the amplitude. Again, for k equals to 2, this is just 1 over a to the 3/2, which is what you would expect. The periodicity function is the one that's a little bit more complicated to get. You have to do a Fourier expansion of the potential, and then you get the frequency. This little bit of a mess, again, for k equals to 2, all of this mess reduces to 1, and the frequency is just m phi, which is what you would expect because it's oscillating as a cosine or a sine. So if the decay rate is small compared to the Hubble parameter for k equals to 2, this looks like matter. This is just going as 1 over a cubed again. And as I said, if inflation ends when this quantity is equal to 1, or when a double dot is 0, and that means that the normal slow roll parameter defined in terms of the potential is about 1. So then what happens? You can solve for the radiation density. So this is the same inflaton density during the oscillations. That amplitude is just decreasing. The radiation density starts increasing. This is only complicated because of the normalization here to rho reheating. The scale factor dependence is here and here, and even this one is not so important. But what happens, now just follow the lower curve. This is the density of in the inflaton oscillations, and this one is the density that's generated from the decays. So it grows up to a maximum very, very early and then decays away. But it decays away with a power that's not 1 over a that you would normally expect for radiation, but it's going as 1 over a to the 3/8. And that's because you're continuously dumping more radiation in, so it doesn't fall so fast. And that's what leads to reheating, because it's going as 1 over a to the 3/8. This is going as 1 over a, this is going as 1 over a to the 3/2. This one's going as 1 over a cubed, and so eventually they cross, and that's what, as I said, we define the moment of reheating. I'll come back to the upper curve a little bit later. Now you can do this. You don't have to do y if phi goes to FF bar. You can think about going to bosons or even scattering to bosons. You can do it for k equals 4, 6, and 8. One case does not reheat just because of the way the temperature falls off, but no, you can generalize this to in any way you want, but I'm not going to go there. All right, particle production. Let's assume now, and I'll come back when I come to the gravitational production. I'll drop this assumption, but you can imagine assuming that that there's some particle that you want to look at that's being produced from the radiation bath, and the cross section for that production has some temperature dependence and some mass scale that's governing that. You can work out then from that what the rate of production is. And then you can look at the Boltzmann equation. You can rewrite that in a very simple form. So these equations are equivalent. And you can do all this analytically. It's not that hard. You can get solutions to the number density of particles produced. This is for scalar particles, for example, if I'm looking at the production of scalars. And it depends on this value of n. And remember, n is just the exponent in the production cross-section. And so for different values of n, this is sort of the more typical one. You see there's some, if n is equal to 0, for example, this is T reheat to the 4th. If I then divide by n gamma, which would be T reheat cubed, this would just be T reheat over, eventually just over m Planck, if lambda is m Planck, say. But you see, it could depend, if n is larger, it could depend on the value of the maximum temperature. That is, most of your production is actually happening right when inflation ends, not at the point of reheating. Okay? So, as I said, an example, n equals to 0, would be the production of gravitino. So this is sort of, we didn't call it that, we didn't call it freeze-in back in 82 or 83 when we were first looking at the production of gravitinos. But n is 0, lambda is m Planck, and then ns over n gamma is just T reheat over m Planck. Is very simple. And then you know for if m3 halves is about 100 GeV with a reheat temperature of 10 to the 10, you get the right relic density. Alternatively, and the example here would be gravitino production in high-scale supersymmetry. The distinction is now that you cannot singly produce gravitinos. You have to doubly produce gravitinos if everything else is very heavy. In this case, n is equal to 6. Lambda is something like m3 halves m Planck. And then for k equals to 2, to get the right relic density, you need a gravitino mass in the order of about a 1 eeV, so 10 to the 9 GeV. Okay. All right, let me come to gravitational portals. So what do I mean by that? I mean, looking at just the Einstein Lagrangian, so just expanding R and looking at the kinetic term for that, and then normalizing it to a canonical kinetic term, and then just looking at the interactions between the perturbation and everything else that you have in the theory. So this is all set. There's nothing. This is all minimal. This is all standard. And I can talk about the energy momentum tensor for the standard model, the inflaton, anything else that I want to consider. It, of course, only depends on the spin of the particle. So for scalars, fermions, vectors, whatever you want. And then you can look at just diagrams of either phi producing dark matter or standard model production through gravity producing dark matter or the standard model itself. So you can do any of these combinations. But this part is completely model independent, right? There's nothing I'm adding here. There's nothing. This part is inevitable. This part has to be there if you're talking about minimal gravity. Okay. So as I said, there are three processes that we considered. There's the gravitational production of dark matter from the thermal bath. So that would be a standard model to XX, for example. Gravitational production of dark matter from inflaton scattering, so phi to dark matter. Or gravitational production of the thermal bath from inflaton scattering, which is sort of interesting. Okay. So go through each of these cases. The first one is probably the least interesting, using the standard model particle. So the thermal bath producing some particle X, which may or may not be your dark matter particle, could be. In this case, the rate, you can compute the rate. It goes as t to the 8th. The coefficients are a little bit funny and a little bit tedious to calculate, but nothing extraordinary. And you can compute the number density. I don't go into this a little detail. You see here the result for omega. That is the omega in X coming from thermal production. The number here is about 10 to the 6th or so, but you see here it's mx over GeV and then T reheat cubed over m Planck cubed. So to get a reasonable density for this, you have to have sort of both a very high reheating temperature so that this suppression isn't very large and a relatively high dark matter mass. Now, I say this isn't too interesting because it's completely overshadowed by the production of dark matter from the inflaton scattering. So here again you can work out essentially everything analytically. The sigma here is a little bit hard because again it involves these Fourier coefficients of the periodicity function, but you can still do it. This is much, much larger than the thermal production, mainly because it depends on the energy density of the inflaton at the end of inflation, not at the point of reheating, which could be orders of magnitude below rho end. So this production usually completely swamps the other one. And this is showing the mass of this whatever particle it is that you're producing and then the reheat temperature. So for k equals to 2, the more standard case, if you have a 10 to the 10 GeV reheating temperature, you would need a dark matter mass of about 10 to the 7 GeV. Okay? If you go to higher dark matter, higher reheating temperatures, you can lower that to some extent. Okay. This line, by the way, it actually presents an upper limit. So everything to the right of the line would be excluded because the relic density would be too large, if whatever you're producing is stable, of course. So if you're talking about, let's say, a 10 to the 12 GeV reheating temperature, your upper limit, and this is for scalar dark matter, would be about 10 to the 5 GeV. For k equals to 4, it's actually independent of the reheating temperature, and you get an absolute upper limit. If your inflaton potential is k to the 4th, you get an absolute upper limit on a stable scalar mass of about 100 GeV. You can't go above that because this kind of production you can't get rid of. There's not anything you can tune to make this production smaller. This is just minimal gravity. Okay? And for k equals to 6, it's even more severe. For fermions, it's relaxed a bit because basically the production mechanism needs a spin flip, so you get some powers of the dark matter mass here, or fermion mass over the inflaton mass. But you get the same basic type of picture. You have, for k equals to 2, now you have to go to much higher dark matter masses to get the right relic density, and they're less dependent on the reheat temperature. But again, this swamps the thermal production. Now, as sort of a sidebar coming from this is that you could ask what happens if the particle that you're producing, say a fermion in this case, is the right-handed neutrino. Okay? And in that case, you can again just use essentially the same expressions I had before, compute the right-handed neutrino mass, and you can then, that right-handed neutrino mass, that right-handed neutrino is going to be severely out of equilibrium. It will decay, it will produce a lepton asymmetry, and then produce, through Sphaleron effects, a baryon asymmetry. And again, this production you can't get rid of. You can add other mechanisms to produce right-handed neutrinos and get more, but you can't get less than this. Now, it doesn't work for k equals to 2. It doesn't actually even work for k equals to 4. On this figure, which has got probably too much information on it, but I'll use the rest of it later. Just look at the curves with the dots on it, not the triangles. So this is 10 to the 13. This is the mass of the right-handed neutrino of 10 to the 13, and it tells you what reheat temperature you would need for various values of k, which, remember, parameterize the inflaton potential around the minimum. So 3 times 10 to the 12, 10 to the 12, 3 times 10 to the 11. Okay. Good. So this is sort of, as I say, a minimal source for the baryon asymmetry, dependent on this inflaton potential. Okay, the final thing, and this will become more interesting in just a minute or two, is the production of the standard model particles through the gravitational scattering of the inflaton. Again, this happens right as inflation ends. You can you have an effective quartic coupling, say, to the Higgs, phi squared h squared, and so you can now compute the equation of motion for producing Higgses if you want, or in this case, any scalar. You can do it for fermions as well. And now I come back to, there's the solution. Again, analytical solutions aren't very difficult to achieve. Now you get the upper curve. And now what's interesting about this upper curve, so this is k equals to 2, and the upper curve is the production of Higgses. Now, and the radiation only coming from gravity, and now it falls off very fast. So this doesn't lead to reheating because this curve will never cross the blue one. So you still have to have some sort of normal inflaton decay to get your reheating. But in this case, you see what happens is that the maximum temperature coming out of reheating can be greater than that from decay. So any process any sort of other process that you might add that's sensitive to the temperature, like the T equals 10 to the 6, or sensitive to the maximum temperature, will be dominated by the radiation produced by gravity and not by decays. And this then gives you an absolute lower bound on the maximum temperature, which may, depending on the value of the of that coupling for decay, if the decay coupling is small enough, in this case about 7 times 10 to the minus 6, then you're going to be dominated early times by this gravitational production of radiation rather than the radiation produced by decay. So in the last minute or two that I have, I just want to tell you what happens if you go to a non-minimal coupling to curvature, and by that I just mean that you have like in Higgs inflation, for example, a coupling to curvature h squared times r, but now we're also going to couple phi squared times r, and also if this dark matter is scalar, x squared times r, all of them, and we're not going to actually even distinguish between these. We're going to take these to be generic. You can go to the Einstein frame, you get your conformal factors again, and now you can expand this. If the psi's aren't too large, you can expand this, and you'll get effective quartic couplings for all the same type of processes that I had before, but now they're dependent on these non-minimal couplings to curvature. And this gets to dominate very quickly. So this is now again showing you the dark matter mass needed to get omega h squared equal to 1 as a function of the reheating temperature here. And this is the minimal case here is psi equals to 0. If you turn these psi's on, then what basically is allowing you to get much lower dark matter masses for the same reheating temperature. So these type of processes become much more important if the psi's are bigger than 1. Okay. And then I come back to this picture and now talk about the triangles, and this is the last thing I'm going to talk about. I come back to the triangles. The triangles down here, so this is psi equals to 0. And this is what you want to do if you want to get the entire reheating from these gravitational interactions. So psi equals to 0 is ordinary gravity. And you see, you don't do very well, right? So you have to go out to like k equals to 20, which you might argue is absurd. I wouldn't be able to argue against that. And then you would get a reheating temperature of up to about 100 GeV if k equals about 20. But when you turn on the non-minimal interactions, that's what these other curves are, psi equals 1, psi equals 10, psi equals 100, you can get sizable reheating temperatures for at least lower values of k. Still can't do k equals to 2 or k equals to 4, but you can actually produce all of the radiation. You don't need any decays, you don't need anything else, and the entire reheating comes directly from these gravitational processes. So, he's happy. So in summary, what I've tried to get across is that these gravitational interactions, this gravitational portal, we view it as the absolute minimal thing that you can have. Irrespective of whatever else you're doing, these processes, these production mechanisms are always going to be there. Anything else you do is going to add on to that. Of course, reheating is an essential component. That's not controversial. And as I said, I've only talked about looking at non-instantaneous reheating. In principle, you should also be thinking about non-instantaneous thermalization, which is, as I said, what Manuel talked about yesterday. The particle production is very sensitive to this. So depending on what your cross-section is for the producing of particles, now again, non-gravitational production, depending on that temperature dependence, it may be very sensitive to the very early stages of reheating when you're near the maximum temperature. Once you go to the gravitational portals, you're completely sensitive to that, and which is not a surprise because the energy density is largest there, right? The gravitational production is going to be dependent on the energy density that you have available, and the maximum is going to be right when you come out of inflation. And so that's going to be important for the, it's going to depend heavily on that maximum temperature and even provides you with a minimum maximum temperature. And it could be important for other processes like leptogenesis. So I'll stop there.
Thank you for this nice talk. Any questions? Yeah. It will,
Hi, thank you for the nice talk. So I have a couple of curiosities. So one is so when you have non-minimal couplings to gravity, do your predictions change if it's a metric formulation of gravity or Palatini formulation of gravity?
I'm not sure. Oh, sorry. I'm not sure I can answer because we've only done it for minimal gravity, and then putting in these very specific non-minimal couplings. So we haven't looked at it in the Palatini formalization. So
I see.
I assume it would change.
Yes, it change, right.
I don't know why it would be exactly the same.
Right. And then, I mean, probably the relic density can put some constraints on this kind of change that will have in the Palatini frame or in the metric frame, right?
Again, I assume it would change the result. I mean, here we get limits on the particle masses just from the amount of production you're getting through gravity, gravity alone, and so. And again, those are unavoidable unless, of course, the particle decays.
Thank you.
Any other question?
Very nice talk, Keith. I have 2 points. One, in the first part of your talk, the T field of the no scale didn't play any role at the end. Eh?
No, because we're assuming it's fixed. Right, I didn't go into how I'm fixing it, but the way we normally do it is we add a correction to the Kähler potential, which will fix T, right? So,
right.
But once it's fixed, in this case, no, it doesn't.
Okay, because the fixing may change your inflationary potential.
Well, well, here we are assuming it to be fixed, but let me point out one other thing. So we're always talking about two fields, T and phi. Right, and you know there's this SU2, 1 symmetry that's sort of governing this. So you can rewrite it in very many ways. So this one we happen to like. It's very simple, a superpotential that will give us inflation. But there are many others. In fact, I'm sure you know that Ciccati had a formulation which the superpotential depended on T. Right, and there's actually a whole huge class of these things. I mean, they're all funny rotations in the field space where you're starting with the same basic Kähler potential up to these field redefinitions, and the field redefinitions have to respect the SU2, 1 symmetry. But you can write many superpotentials, which will all give you Starobinsky. I think the model that Dimitri showed that from Ignatios and Rizos, they used a different superpotential that still gave you Starobinsky. But this is, again, one of the classes of superpotentials that are related by the symmetry.
But you always have the issue that once you have two fields, you have to fix one and use the
always have that. You have to fix one.
Very good. And then the other point about your gravitational portal, that looks very general for any model of inflation. Why is it wasn't done before?
Well, that's a good question. Why wasn't it done before? We were surprised too why it wasn't done before. That I can't answer, right? It does depend. It is true for any model of inflation, but it is sensitive to what you're assuming for the minimum. So the generic thing is this k = 2. So some of the things like leptogenesis for k = 2 is not interesting. But the rest of it is. For k = 2, the production of these particles coming right out of inflation, it could have been done 30 years ago. Right? I don't know why.
Okay. Thank you.
Okay. Is there any question? That's the last question.
That's
okay. So you mentioned freezing at some point, and you set the initial condition to 0.
Sorry, I mentioned freezing, but I set the initial condition to 0?
I mean, for freezing, you set the initial condition to 0, right?
Yeah, okay, sure.
When do you set the initial condition to 0? That's a question, because before...
Well, coming out of inflation. I come out of inflation, I only have an inflaton.
Yeah, but before that...
What do you mean before that?
Before that, gravity can produce dark matter in general.
No,
That's
sorry,
general.
I start with inflation, so I have nothing in the universe but the inflaton rolling on its potential. The inflaton starts to slide down towards its minimum and starts the oscillations. Still at this moment, I have nothing in the universe besides an inflaton oscillating. Very quickly, the first initial decays of the inflaton begin to happen. Okay? And now you have to be a little bit more specific, because you have to say, how does the inflaton couple to other things? And that could be, it has to couple at some level. So then you start producing particles. Then you have to worry about things that Manuel was talking about. How do these things thermalize? Okay? And so there was some recent work by Amin and Garcia that looked really at that part of the process. But then once thermalization happens, then you start producing standard model particles, right? Then what I talked about, you can start producing other particles through gravity, or if you have, of course, direct couplings, like the t to the n over lambda to some power, then you produce them in other ways. But the initial condition is that it's 0. That's why it's being produced, and as I said, we didn't used to call it Friesen, but it's what people call Friesen now.
Yeah,
well,
the background itself is time dependent.
Ah, yeah,
so
okay.
It's
That's
like a given
no,
harmonic
that's fine. That's fine.
oscillator.
You mean like Parker and Ford? That's typically. I don't know the number, but we looked at it. It's typically less than this direct production from inflaton and photon
okay,
scattering.
if it's insignificant. Okay.
Well, I don't want to make that strong of a statement that it's insignificant. It's a good question. It's a good point.
Okay, thank you.
Okay, I think we should stop here and let's thank let me call now our next speaker, who is Mariano Quiros. Is going to talk about Kaluza-Klein modes handling from gravitational waves.
Okay, so good morning to everybody. First of all, I would like to thank the organizers for this nice invitation and the opportunity to come back to Ioannina after 7 years. I was here in Planck previously, so it's like a sabbatical visit. So I'm going to talk today about Kaluza-Klein modes and gravitational waves. What I'm going to talk is based on works done in collaboration with those people, Constantin, Mejias, Nardini, and Wulser for the last 15 years. So Nardini in particular is a member of the LISA collaboration, so it helped a lot at some stages of the work. Okay, so as this is not a supersymmetric talk, I wanted to just to make some brief comments. Let me just say that I believe that seems to me that the simplest and perhaps more elegant solution to the naturalness problem is provided by supersymmetry. Okay, so there were plenty of talks here in this conference during the conference at the pre-SUSY. Okay, as everybody knows, it provides a technical solution to the hierarchy problem, that in particular the TV scale is not sensitive to the UV physics. As any other theory, this theory has some advantages and disadvantages. I think that Fernando had a slide precisely with those pros and cons. For the pros, I don't need to say anything apart from what Fernando has already said. And there are some, let's say, points which are more problematic. One is that, apart what Fernando said, also others, supersymmetry is not an explanation of why, in general, TV is much smaller than M-Planck, but it is just a technical stabilization. The mechanism of supersymmetry breaking is one of the biggest problems of the theory. It's not clear. And there is a mu problem that Fernando solved in a different way. Okay. So, okay. Then let me just tell you the contents of my talk. So I'm going to talk about, of course, warp extra dimension, which is a well-known alternative to supersymmetry. I think it was also covered during the pre-SUSY here. Okay, as any other theory, you have to confront the theory with experimental data. This is what I call collider challenges. And then I wanted to just to explain to you that there is, in this theory, there is a first-order phase transition, which is what people call confinement-deconfinement phase transition, which is somewhat related to electroweak phase transition. And then I will go to gravitational wave signatures and then to the conclusions and outlook. I'm not going to be technical, so it will be very, okay, I just wanted to point out the main points or the main parameters of everything. So the first is just warp extra dimension is as a solution to the hierarchy problem. This you have in this slide, this solution in a nutshell. So as you know, this was proposed more than 20 years ago by Lisa Randall and Raman Sundrum in this seminal paper. So the idea was based in a 5-dimensional theory with an anti-de Sitter geometry with this line element, with this metric is just linear for Randall Sundrum. And but the fifth dimension is not is compact. It's not infinite. It's compact. So you can think that you just compactify the fifth dimension on a C2 orbifold with 2 fixed points, and then you put in the 2 fixed points you put 2 branes. One is called the UV brane or the Planck brane. The other is called the TV brane or the IR brane. And they are related by this warp factor, which is provided by the distance between the 2 branes. So in those, in the UV brane, let's say the cutoff of the theory is the Planck scale, while in the TV brane is the TV scale. Both, as I said, are related by this warp factor. That at the end, okay, it has to be, okay, you can generate a very large distance with a, let's say, not so big exponent, so it's of the order of 30 something, 35, let's say. One of the points of this theory is that there is a correspondence between this theory, ADS, and a 4-dimensional, where the gravity is propagating, and a 4-dimensional theory, which is conformal field theory, which is non-perturbative, and that this provides a dictionary between both theories. Usually you do the calculation on this theory, which is perturbative, but sometimes it's very useful to go to the CFT language to understand the result or to interpret the results. In this sense, all particles are propagating in the bulk. The Higgs is localized, so every particle has a profile along the fixed dimension. So the particles with a profile localized towards the IR brane, by this correspondence, they are composite states in the CFT theory, and the particles with profiles localized towards the UV brane, they are just elementary particles. So in this sense, the Higgs has to be localized towards the IR brane, so this is why they say that the Higgs has to be composite, and this is to solve the hierarchy problem. Fermions, depending on their masses, heavy fermions are localized towards the IR brane, so that's, for instance, the top, so they are composite, and light fermions, for instance, the up quark or the electron, they are localized towards the UV brane, so they are elementary fermions. And of course, the theory predicts the existence of Kaluza-Klein resonances, and they are at the TV. They are at the TV scale. Those resonances, they have profiles localized towards the IR brane. So in principle, they are interpreted as composite states in the holographic theory. Okay, this is more or less what I wanted to say about this theory. Now you have Kaluza-Klein resonances, so you have to confront this theory with experimental data, and this is what people have been doing. So this is what I call collider challenges. So the LHC data are put in severe bounds on the mass of the lightest Kaluza-Klein resonances. For instance, the KK gluons, which are the strongly coupled particles. Here there are 2 results based on 36 inverse femtobarns by CMS and by Atlas. So in this plot, they just present a 95% confidence level upper limit on the production cross-section time branching ratio into tops, TT bar. And the red lines in both cases are just the model predictions. So there, where you cut those upper bounds, this gives let's say the lower bound for the mass of this particle. Okay, so then already from this analysis, which are from some time ago, but you can get bounds around a few TeV, so 4 TeV, let's say, no? So, of course, maybe that's a possibility. These limits point toward the possibility that nature might have chosen values of rho which are much larger than TeV, few TeV, or maybe even more. Still, there is the work factor explaining in quotes, I would say, no, because the relation between this rho and this M Planck. So if this rho is larger than 1 TeV, still it's related to M Planck by some work factors. Of course, there is a little hierarchy problem that you cannot avoid if you have something, that's in general, no, in the effective theory, you will always have a little hierarchy problem for values of rho which are larger or much larger than 1 TeV. But the point is that from the experimental point of view, those heavy KK resonances would probably escape LHC detection. So the solution is that, we have to go to more energetic colliders to see if they are found there. And this is what I'm going to talk, is that perhaps, there is another possibility, which is by gravitational wave detections, which is, will take some years, but they are going to be done, this detection. Okay, let's go. So here I wanted to go over the phases in the Randall-Sundren theory. Let me just flash a few ideas in general of those theories. So this is a theory with a warp extra dimension and 2 branes, as I said. Then this theory requires a stabilization of the brane distance. So otherwise, there is a flat radion, which is phenomenologically excluded. Okay, how can you do that? This can be achieved, for instance, by a bulk scalar field. This is the proposal by Goldberger and Weiss. The paper is 2 months later after the paper by Randall and Sundrum. By a bulk scalar field with brane potential. So you fix, you break the conformal invariance with those potentials, and this creates an effective potential in terms of the radion field. This is what you are doing. So, and then you look at the minimum of this effective potential and so on. So now, this is at low temperature. This is what you have, and then you interpret that the Higgs is confined. So you say that the Higgs is in the confinement phase. But there is another solution. There is another solution to the Einstein equations of motion, and that is interpreted at high temperature as the confinement phase. So there are finally there are 2 phases, one which is working at low temperature, the other which is working at high temperature, and there is a phase transition between both, between the confined and confined phase. And this first order phase transition can and will give rise to a stochastic gravitational wave background. Okay, so those ideas were started to appear 20 years ago. Okay, let's go. Okay, let me just explain the confined phase. I'm just going to flash results and what are the parameters of the theory. At the end, the theory, as you will see, have 2 parameters, 2 free parameters, once you have fixed the hierarchy problem and all that. No. So the effective potential at 0 temperature, as I said, you have to build it. So it's a function of the brane distance. This brane distance is related to the radion background expectation value, or in holographic language, to the dilaton background expectation value, once you normalize canonically the field. And then this depends on a parameter. This I have defined lambda1 as a dimensionless parameter, which is defined in this way. Lambda1, this capital lambda1, is a tension that you put on the IR brane. This is just a constant with dimension of mass to the fourth. And in the potential, there is this plus the superpotential at the value of V1. Okay, V1 is the value fixed by the Goldberger-Weiss potential at the IR brane. It fixes some value of this field there. And this is the so-called superpotential. It's not really a supersymmetric theory, but it is just an artifact, a mathematical artifact, to go from in the Einstein equations of motion, which are second degree, to go to a first degree equations of motion, which are much easier to solve. They can be solved in many cases analytically, which means that you can take into account easily the back reaction of the field on the metric. So in our theory, in our study, we will take into account the back reaction. So when you add those two terms, and then you define this lambda 1, which is just a definition. This is a parameter with this k is of order n Planck, as I said. So this is dimension of mass to the fourth power. So this lambda 1 is dimensionless. And you can just play with this. This is a free parameter of the theory. If you fix this parameter to 0, this is what people call tune solution. But if you detune this from 0 to some different value, you have this possibility here. So if you tune this to 0, what you get is two degenerate minima, one at R1, let's say, the brane distance at infinity, which amounts to dilaton BEV equal to 0, and the other one is just the physical one. No? Here we are using proper methods, and just to compare, we wanted to compare with the Goldberger-Weiss. This line is the Goldberger-Weiss potential, and this other line here is our potential where we are neglecting the back reaction. So it's a good agreement, but the red line is our solution, which takes into account all the back reaction. But of course, in this case, there is no possibility of phase transition because those two minima are degenerate. Then you have to detune that, and then, okay, you introduce that lambda 1 at some negative values, you create some minimum here in such a way that you can really have a true minimum here, which is below the symmetric phase. Okay. So this potential is controlled just by one parameter. It's called lambda 1. Okay, it's just a parameter of the theory. Now there is another solution at finite temperature, which is written is a black hole singularity in the fifth dimension. So it can be written in this way. So where this function h enters the equations of motion, the Einstein's equation of motion, and it is just the typical blackening factor of black holes. Has to be equal to 0 at the horizon. The horizon is along the fifth dimension. And in this correspondence, ADS-CFT, this black hole metric describes the high temperature phase of the system, where the radion is sent to its symmetric phase. No? Then what you have to do to study the phase transition is that you can compute the free energy in both phases, in the confined and in the deconfined phases. You have to compute this. This F min is, you have to compute the free energy corresponding to this solution and the free energy in the confined phase. And then you have to compare both phases. And this is a cartoon of this phase transition. So this is let's say, the Randall-Sundrum minimum. And on this side, it's really a perpendicular direction. But okay, I have drawn it on the left, but in reality, there are two directions. But there is a minimum, which is very deep at high temperature, because this F min, that I was calling F min, which was one of the contributions to the free energy, is negative, and it is proportional to the fourth power of the temperature. And it contains n squared. This n is the number of degrees of freedom of the conformal theory. Imagine that it is SUN, okay, it is this n. And it can be related to the parameters of the theory. Okay? So the phase transition takes place, of course, when the bubble nucleation rate equals the universe expansion rate at some temperature, at the nucleation temperature. For that, you have to compute the Euclidean action and to compute the bubble nucleation rate. The bubble nucleation rate is essentially the exponential of minus the Euclidean action. And the Euclidean action is dominated essentially by two possible symmetries of the action. One is O3, which is typical of a high temperature situation, and the other is O4, which is typical of low temperature situation. And they have to compete. They have to compete. And essentially, when this Euclidean action is of the order of 100, roughly speaking, you have to compare it with the Hubble expansion of the universe, and the phase transition takes place. This is in the thick wall approximation. We are not working in the thick wall approximation, but it provides analytical understanding of everything. So E0 plus F min is negative, so E0 is positive here. So at some point, F min has to be, let's say, smaller in absolute value than E0. So at this point, you can start. This is the signal of the critical temperature. And there is an n square here in such a way that when you send n to infinity, this Euclidean action goes to infinity and there is no phase transition at all. Okay? So at the end, just to point out that this, you can compute the nucleation temperature and everything will depend on two parameters which are those lambda 1 and n. As I said, n is the number of degrees of freedom in the holographic theory. But using the ADS-CFT duality, n can be connected to the k. This k was the parameter which is associated with the ADS curvature, ADS5 curvature, and it is related by this expression. So the gravitational coupling constant, G5 squared, is just essentially k divided by m5 to the power cube. M5 is the Planck scale in 5 dimensions. So then the theory is weakly coupled in the gravitational sector only when n is large. So you have to make sure that your theory is weakly coupled, but however not so much because in this limit you don't have phase transition. So at the beginning people thought that there was no phase transition at all because they were thinking on n, very large values of n. So it was, the system just remained in the confined phase. Okay. Now, so the idea is just to keep n large, but perhaps not too large. And we have done everything for, those are the Euclidean actions. For instance, here you can see for different values of the parameter, when n is large, let's say the phase transition is supercooled. As you can see, for instance, for n equals to 25, so this phase transition starts here, no? It starts here. So the beginning of phase transition is when the Euclidean action crosses those lines, and we have done everything for two typical values of rho equals to 1 TeV and rho equals to 100 TeV. But of course, we have scaled all quantities by rho also. So while if you go to smaller values of n, in that case, it's a high temperature. It is a high temperature. But in both cases, T over rho is small. Here is 0.3, and here is 0.1. No? So this means that the rho is essentially the background expectation value of the dilaton. And when the phase transition, at the nucleation temperature, it always happens that rho divided by Tn is much larger than 1. So this is why we claim that the phase transition is very strong first order. So we have a first order phase transition. There can be, if there is a supercooling, there can be some period of, a small period of inflation, the universe will reheat at the end, and well, okay, and all this you can compute. Those are some plots for instance, for the nucleation temperature. You can see that when you go, and this is lambda 1, and n is a parameter fixed equal to 10, 15, and 25. So you can see that the nucleation temperature goes down when n goes up. At some point, it will stop. Yes, at some point it will stop. And the same, well, the inverse things will happen with the heating temperature. So, okay, gravitation. So this is a first-order phase transition. So you have gravitational waves. This is very well known. We had yesterday a very good talk about gravitational waves. I think the point of the first-order phase transition was not covered by the speaker, but it doesn't matter. But it is well known that it generates a stochastic gravitational wave background. And there are those gravitational waves are controlled by two parameters, by what people call alpha and beta. Alpha measures the strength of the phase transition. So the larger alpha, the stronger the phase transition. Is just the difference in free energies divided by the energy density. And this parameter measures the inverse duration of the phase transition. So it's okay, a very strong phase transition is just very long. So this parameter beta over h is very, yeah, is very long. So okay, in the next decades, several gravitational wave observatories will have the potential to observe or constrain these gravitational waves produced precisely in this phase transition. Thank you. I'm about to finish. So let me just almost conclude. So this is just a plot for those parameters, alpha and beta, in the space of parameters. So I don't have time, I'm running out of time, of course. And this is the prediction for the amplitude of gravitational waves and for the peak frequency. So you can have a look at them in detail if you are interested. And this is, okay, this is just a superposition of the model prediction for the different values of the parameter that we have explored with the sensitivity of the different interferometers. So here you have LISA, ET, and then LIGO present and LIGO at design. So here, okay, so then you can see that depending, okay, this SNR is the signal to noise ratio. So if you assume something like larger than 2, so you can really even, LIGO will detect at this level something or could exclude something at the end. Of course, if you require 1,000, and then it's only ET and LISA that will do the job. This is just my last transparency. So conclusions, so okay, warp extra dimension is an interesting alternative to SUSY. It triggers, this is completely general, a confinement, deconfinement, first order phase transition, and of course the gravitational waves are a useful tool to detect the existence of this phase transition, which is going to be very interesting. And as an outlook, we have just put the limits that future interferometers will probe, and then we have found those values, no? So we have found that for LISA will probe Kaluza claim masses up to 10 to the 5 TeV, LIGO up to 10 to the 8 TeV, and ET also up to 10 to the 9 TeV. So in those, well, for those interferometers, they will be able to probe many values of the Kaluza claim masses and to exclude the, well, to exclude the, whatever they have to exclude. Okay, thank you very much for your attention. Sorry.
So any questions?
Nice talk, Mariano. Thank you. How much of this depends on your on the particular five-dimensional setup? I mean, because for instance, Randall syndrome has been implemented in string theory with the throat and the Calabi-Yau as the second brain and so on.
Okay, thank you. That's an interesting question. Actually, here we have worked out the simplest setup. So, in particular, we have put quadratic potential, something very simple, and this reproduces very well Randall syndrome. But there are other scenarios with warp extra dimensions. So, there are scenarios with produce soft walls, for instance, and they are going to modify a little bit those results. I don't think that too much. But for sure, there is some model dependence, yeah, in those results. Yeah, this is true.
Okay. Any questions there?
Well, I think that when they will start excluding this scenario, we will move to other possibilities.
Down there. It was not.
Hi. Is there something particular about this stochastic background, like the morphology of the stochastic background, that can distinguish it from other types of backgrounds of cosmological origin? So is it just a bump? I couldn't tell from the plot. Is it just a bump at a particular frequency with a certain power law decay, or is there something special about the morphology?
No, this is just. In this scenario where it was proposed, is just a scenario where it's not looking at the possible origin of this scenario. It can be produced by string theory in some throat or things like that. People have studied this question, but let's say that at this level it's just more phenomenological than, let's say, trying to find roots, deep roots into other theories as string theory or cosmology. Yeah.
Okay, yes, but the morphology, is it just a simple peak, or is there something more?
For cosmology?
Yes, the stochastic background, the shape of the...
Cosmology should be similar to the standard model cosmology.
No. The spectrum, the shape of the stochastic background.
Ah, okay. Well, okay, and yes. The point is that if you can, let's say, falsify this theory in this way or not, no? I'm sure that you can produce, I mean, once you have a first-order phase transition, the spectrum depends on the parameter alpha and beta, and nothing else. So the origin of alpha and beta doesn't matter. So you can have a variety of theories producing alpha equals to 20, let's say, and that doesn't matter for that.
Okay, is there any quick question? I think there.
Yeah. Actually, it's a bit related to Fernando's question. So, as you said, so in all your description, you said that it only depended on two parameters, lambda 1 and n. But this is once you fixed the brain scalar potential, right?
Yeah, this is similar.
Yeah, but so my question is that if you introduce this kind of freedom, then with this kind of plot, you can actually never go back to any, like, you don't have any standard prediction or...
No, okay, that's the same question as Fernando. It is true that
I mean,
there is a variety of models, world models that you can produce. Yeah. As I said, we have, okay, but the models, they have to solve the hierarchy problem. So in some sense, you cannot put anything there. No? So you know that the metric has to be ADS near the UV. But, okay, but you can put variety that behave like ADS at the UV, and that's the daily departure from it and on the IR. For instance, as I said, there are some metrics which produce net singularities, so the soft worlds. No? Okay, in those cases, the prediction should be a bit different. How much we can work out some of them, and the vectors are not very different, but it's still some model dependent there. Yes.
Okay. I think you addressed this question. So let's understand Mariana. So our next speaker will be Benjamin Ioannina.
Well done.
And he will talk about I don't know if the title is the same. Third family hypercharge. So you know.
Thanks. Good afternoon, SUSY-2022. All right. So Andy gave us this nice overview this morning, and I must say I find his enthusiasm contagious. So I'm going to motivate a bottom-up model from Z primes which have non-family universal couplings. But this talk's going to be in 3 acts, because when you do that, you get this from a spontaneously broken U1 gauge theory, and you have to worry about the anomalies. So I'm going to start, Act 1 is a theory part. I'm going to solve the quantum field theory anomaly equations. Then we've got Act 2 is the model building. So it's bottom-up model of a Z prime, which can explain the B anomalies. And Act 3 is experiment, because you want to see this Z prime in experiments at the LHC and beyond. Okay, I don't need to review this. Andy did it. All right. That's good. What I want to do is take a rough stab at the different models that can explain this data. So you can do it at tree level. You've got 2 options, right? You do it in the T channel, or you do it in the S channel. T channel, it couples to a quark and a lepton, so by definition that's a leptoquark. S channel, turns out, needs to be a vector boson. It's electrically neutral, so we call it a Z prime. It just means it's like a heavy spin 1 vector boson. And of course the idea is, in the B meson decays here, you get an interference with the ordinary standard model process, and it changes the predictions. And the data say you really want to be changing the coupling to the muons in preference to those to the electrons. Now, I'm going to get my Z prime from a spontaneously broken U1 gauge group. So I'm just going to do standard model across U1. I'm going to break it around a TV. The Z prime will get a mass of about a TV. It's actually, well, we'll see later. So the important thing for the phenomenology is how the Z prime couples to standard model fermions. That's dictated by the U1 charges of the standard model fermions. Okay? And so we have to impose quantum field theoretic anomaly cancellation. So we have 2 different kinds of anomaly in this talk. We have the B anomalies and the quantum field theory anomalies. And so there's some kind of a duality of anomaly, like Schrodinger's dancer here on the right. There are plenty of other uses for the Z primes. People have used them for dark matter models, axions, models with fermion masses, and particularly in this last case, you want family non-universal couplings. Okay? So we want to solve the anomaly equations in the family non-universal case, and I'm going to add 3 right-handed neutrinos so we can get neutrino masses. I'm going to denote the U1 charge, this U1x charge, by the field label. And our anomaly cancellation conditions are now this. Okay, so we've got mixed anomalies, gravitational ones here. These are all linear in the charges, easy to solve. Okay, but then we have this quadratic equation from the hypercharge times the x squared, and we've got x cubed, so there's a cubic equation too. Now, I'm looking for compact extensions of the standard model. There's an expectation that this U1 might fit in some non-abelian model at a higher energy scale. And so we're looking for solutions over integers to the 18. I have 18 different charges to fixed. So there's integers out to the 18. I've got to bear in mind, of course, it's a U1 gauge theory, so I can rescale the charges of each field. I can rescale the charges of all the fields and absorb that into some gauge coupling. All right. Now, but we're looking for integer solutions. Therefore, when you do that with a system of polynomial equations, you call them Diophantine equations, the number theorists will tell you that's difficult to do. And it is. Roughly speaking, the state of the art for a generic Diophantine equation solution is about 1 cubic in 3 unknowns. Forget this quadratic and cubic together kind of thing. All right. Now, so to begin with, we thought, oh, we'll just do a computer scan. You've got to play a few tricks, because if you do this naively and you want all charges between 10 and minus 10, you're going to have to scan 10 to the 24 different charges and check these 6 anomaly equations. That's going to take too long. But nevertheless, you can do it. We produced a list, which you can see. So this is easy for model builders. You can scan through this list and look for charges that you might want to use in your model. Later on, last year, we extended this standard model cross U1 case to the semi-simple case. So this is in particular where you add no extra fermions to the standard model plus 3 right-handed neutrinos. You demand that they form complete representations of any semi-simple gauge group, and further that that's anomaly-free. There's only 340 different possibilities, and they're in this paper. Okay, and we also, this is the only bit where supersymmetry, sadly, plays a role in this talk. We've extended it to the SUSY case here. But let's go back to the standard model cross U1 case now. All right. So the solutions are rare. Out at charges between minus 10 and plus 10, only 1 in 10 to the 12 solutions satisfies the anomaly cancellation conditions. All right. But there's still 21 million of them. Non-equivalent solutions. Okay, so you've got plenty to play with. Finding the odd solution is easy. Here we've got 3 pertinent examples. A is the third family hypercharge model. I'm going to talk about that later. B, you can see the charges here in B. They're vector-like charges. Vector-like, it's a vector-like symmetry, so you know it's going to be anomaly-free just by looking at it. And of course, it's B minus L. C is a different kind of beast, and there's inter-family cancellation here. C will be important later too. All right. But, okay, that's just, if you want a charge of 11 for some reason, you can't use our list. So we wanted a general analytic solution. And we used some simple techniques from algebraic geometry. So the first thing to do is noting that solutions over the rationals are equivalent to those over the integers, because you can clear all denominators with this rescaling symmetry. Since the rationals are a field, you can define geometry and lines and things on it. We can use those to solve our problem. So we start with rationals to the 18 solution space, or well, not a space of potential solutions. And the solutions where the charges differ by a common multiple, as I said, are physically equivalent. So we define the equivalence class to define this projective space of rationals to the 17. So it reduces the dimensionality of parameters by 1, and there's an equivalence class across each of these rays in the charge space. All right. So within this, we have the 4 linear equations. So we impose those, and we project down to a projective subspace isomorphic to PQ to the 13. And we want to look for the intersection of this quadratic surface with this cubic surface. So we use 2 techniques to solve this. The first one is the method of chords. This goes back to Newton and Fermat, certainly, but it may go back to the Diophantine school too. So a chord is like a straight line. A chord intersecting a rational cubic surface. A rational cubic surface is like a cubic with rational coefficients. Okay. At 2 known rational points, intersects it at 1 other rational point. A rational point is, well, obviously a point with rational coordinates. So our cubic looks like some function of our charges is equal to 0. So the idea is we've got two known solutions to this cubic, and I'm going to parameterize a line through them. So one of the solutions is A, so when t is equal to 0, we have A. When t is equal to 1, we have B. And extending through t gives us this full line. And the idea is this method of chords gives us one further solution along this line. And the reason is because we know this is a cubic, a rational cubic, so each of the terms on the right-hand side has to be rational. And we've got a root at 0 here, a root at 1, and there has to be, there's some other root because it's a cubic, and because it's a rational thing on the left, it has to be a rational thing on the right. Now there's a caveat, and the caveat is important. We're going to use it. The caveat says it's quite possible that this line lies entirely within the cubic surface. The cubic surface, for example, I don't know, x cubed is equal to 0. That's a cubic surface. That can look straight on this, and then the whole line is within it, and you get an infinity of solutions. All right, that's going to be useful for us. Now, I don't have to do this with cubics. I can do it with quadratics, with just one solution rather than two. Use the same method, and it will work. The other thing I need is this double point thing. So double points are solutions of the equations of multiplicity 2. All the partial derivatives of the surface vanish there. So for example, let's take 2 dimensions, and we have this polynomial. The solutions to this are an infinity symbol, and you have a point in the middle which has multiplicity 2. That's a double point. And the important thing for us is this point b minus L. This is a double point both of the quadratic surface and the cubic surface. And so this is going to let us solve, this is a special thing which lets us solve our system of equations. Right, so we've imposed our linear conditions. We're in PQ13. And we start with some point which is going to parameterize our solutions, all right? So I can imagine scanning it, but it's really just equivalent to choosing different rational numbers or integers and parameterizing the solution in terms of those. I extend that point with a straight line to a known solution. That's going to be solution C. Solution C is one solution to the quadratic. I use the method of chords to find one other solution to the quadratic along here. I'm going to call that R. Now, every solution to the quadratic lies on a line between C and some other point, S. So if I scan S, I find all of the solutions to the quadratic. So I can effectively scan through R. Then I extend this line to the double point. Now, consider the quadratic equation. So we've got 2 solutions to the quadratic equation here at B. But I've also got a third solution to the quadratic equation here at R. Therefore, we must be in this special case where the whole line is in the quadratic surface. Okay, that's fine. So this whole line is a solution to the quadratic. And then I use the method of chords with the cubic. And I've got 2 solutions here, so I can find one other solution along this line. That's this x. So this is now, x is now a solution to the cubic and the quadratic. Every such solution, x, lies on a line between b and some solution to the quadratic. And because we can solve all the quadratic, we can find all the solutions to the quadratic, then we found all such x. There's the solution. It's horrible. These gammas and sigmas are, polynomials up to 5th order in the original coordinates. The coordinates of these s's here. But the idea is if you put in any s, integer s, you work all this through and you'll get a valid solution. And if you scan over all s, you'll get all solutions. All right. The solution space is 11-dimensional, but it's not so important. We checked all this against the computer solutions that we found, and of course it's fine. All right, so I'm going to take a subset of these. This is third family hypercharge, and for now, I'm going to set t to 0, but there's an additional extension with B3 minus L3. Third family hypercharge has 0 charges for the first 2 families, but the third family charges are proportional to their hypercharge. But I want to write down, in order to be able to write down the top Yukawa coupling, because it's of order 1, I need to give the Higgs an x charge as well, proportional to its hypercharge. And then I find I can write down the third family Yukawa couplings, but not any of the others. So then I've explained why the third family is parametrically heavier. This has been known for ages that you can do this kind of thing. Of course, we're going to spontaneously break this symmetry, so the expectation is there'll be small corrections to this picture, and in the quark sector that works very well. So it's simple. We break it with a complex scalar. This is the bottom-up model buildies part. It's got a non-zero x charge, a VEV of like a TeV or a few TeV, breaks the U1x, and then we've got the standard model. So we get a Z prime with non-trivial couplings to different non-family universal couplings. Now, we've got an expectation that this will be subsumed into some semi-simple model at a higher scale, and there might be other things going on too, but it's still pertinent to worry about anomaly cancellation, despite the fact that it's an effective theory. And that's because, if you might say, well, I can change the anomaly cancellation conditions by adding additional fermions, but if you do that with chiral fermions, you have to explain where the mass comes from. You can do it, you could maybe do it at the breaking scale of this U1x. So it would have to be tied to this TeV scale that we're describing. So it's pertinent to apply anomaly cancellation still. Of course, you can add vector-like representations and it's fine. All right, so the Z prime couples like this. All of these fields in bold are 3 vectors in family space. So it couples proportional to the gauge coupling with a factor of the hypercharge out the front. And then you get a matrix in family space, which looks like this. VI is a 3x3 unitary matrix. It just describes the rotation between the gauge eigenstate and the mass eigenstate of the particular fermion. But then it's sandwiched with this matrix, which has a 1 in the 3-3 entry, and that's because it's third family hypercharge. All right, now, to make any further progress phenomenologically, I have to make some assumptions about these VIs, and it's going to necessarily be strong. But we're going to just pick a case that we think won't cause us too many problems and might explain the data. So I'm going to pick a load of the matrices I don't need to be anything else to be the identity. I need BS mixing because I want the Z primes coupled to bottom left and strange left. So I mix those up. And I need it, at the moment it only couples to tau's, so I have to do a basis change and say that this L3 field was really a left-handed muon, and a left-handed muon neutrino, not a left-handed tau. In terms of these matrices, this looks like a basis change matrix. So then when you do that, you find the important couplings are that the Z prime couples to B and S, but much more strongly we'll see to BB bar. But it does couple to BNS, and it couples to left-handed muons. Now, we've given the Higgs an X charge. That means you get a ZZ prime mixing. The mixing angle is proportional to MZ over MZ prime squared, so it's at most like 1%. So it's small, but we need to take it into account. And indeed, the Z inherits some family non-universal couplings from this initial X non-family universal gauge boson, but albeit only a small part. The Z prime decays mainly into tops and Bs, but the important experimental decay is into dimuon pairs because dimuons are very clean. You can produce it at the LHC, but its couplings to other quarks, apart from the tops, are negligible. So the production mechanism is basically by a BB bar and nothing else. That suppresses the production cross-section a lot. I mean, you've got associated production as well. Okay, so with my student, Hannah Banks, well, she did all the work, really. You know how these things work. What she did was she did a scan over parameter space and applied all these LHC bounds, these searches for dimuons. So you look for a bump in a dimuon mass spectrum, and you don't particularly see any significant ones. So you produce bounds, and the colored region is ruled out. So the colored region is in coupling over mass space against the mass, and our fit to the B anomalies, which I haven't gone into, but this is the fit, tells you that in this yellow region, so you've only ruled out this tiny bit of parameter space. It's hardly constraining at all, and that's because you produce it in this BB bar way, which suppresses the cross-section. Now, when you go to the high Lumi LHC, you can increase the sensitivity. So you've got some chance, if your model's in this region, of seeing it in some of these channels. How much time do I have, Apostolos? I'm okay. You might ask, okay, why are we first seeing flavor-changing transitions in this effective vertex B bar S, mu plus, mu minus? At first sight, it looks a bit random. But from the lens of the kind of models that I'm talking about, and you know, I've just presented one of them, and there are many others, and several people in this room have been responsible for them, not least Andy and Steve, but many others too. So from this point of view, this model, we're getting the strongest flavor effects from the heavier families, okay, from the third family actually. But the thing is, LHCb produces shed loads of bottoms. That's the official term for like a hell of a lot. And less tops, okay? So that's why we're seeing in B, in the B channel. Now you need a flavor changing transition, so it's going to go to strange, for example. And then we might expect that into tau, BS tau tau would be much more prevalent. But taus are so difficult experimentally that their sensitivity is reduced. So that's why we have this kind of vague understanding of why it might be BS to mu mu, and maybe it doesn't look so surprising. Now, I'm going to summarize first, and then I'm going to give a shameless plug for my book, all right? So these anomalies look very interesting from a BSM point of view. From my point of view, a consistent picture is emerging, and you know, this looks very good. Of course, we need an independent check, ideally from an experiment with very different systematics, and we're awaiting one from Bell 2 in Japan, because Bell 2 is operating on the Upsilon 4S resonance, so they produce oodles of B mesons. That's another official SI unit, an oodle, and okay, so this doesn't have the systematics associated with LHCb, where you're doing 13 TeV collisions, and your electrons brem photons like crazy. This is, in that sense, this is a much cleaner environment. So when they get the beam up to peak luminosity, we expect good confirmation or refutation from Japan. But of course, what you want to do, let's suppose that the B anomalies continue to be interesting. You want to find the new physics state responsible for them. And I've already said, you know, there's two categories, there's Z primes and leptoquarks. And actually there are many different examples within each that can explain the data. So, and what you really want to do is produce the new physics state and kind of give it a tickle and see what it couples to. And that will give you a direct experimental handle on physics that's pertinent to the fermion mass puzzle. Okay, so let me just give my plug now. This was based on a master's course, so like pre-PhD, for Lie algebras and Lie symmetries as applied to particle physics. And it's on Amazon. And I recorded some lectures as well to go with it. Okay, thank you very much.
You had these rotation matrices. Now for the right-handed fermions, I guess they're completely unconstrained. But for the left-handed ones, don't you have to reproduce the Km matrix somehow?
Yeah, absolutely. So I didn't go into that in any detail, but yeah. So let me see. So we're fixing the down left, and you see here that I'm constraining the other one to make sure you get the CKM matrix. And it's the same for the PMNS. So I've shunted all. I mean, these are quite strong assumptions. I've shunted all the mixing into the lepton mixing into the neutrinos from this point of view. You'll notice, right? And in fact, I think there are strong bounds on, because you'll start charged lepton flavor violation is will be strongly bounded. So what that means is that this structure here, which is essentially saying there is no charge lepton flavor violation, certainly at tree level, that's a very strong assumption. So you'd really want to, you'd really want to do, if this were confirmed experimentally, you'd want to do a lot more model building and motivate that by symmetries and so on.
Any other question? How here?
Yeah. So let me ask for a clarification, then I have a question. So the new Z prime is the coupling to E plus E minus is highly suppressed?
The question was, is the coupling to E plus E minus highly suppressed? It's 0.
It's 0. Okay.
So it's only coupling to muons in the lepton sector.
Okay.
Sorry, left-handed muons and right-handed taus and some neutrinos.
Okay, so then my question would be the following. So you showed...
Howie, can you, if you turn it like this and do it on the end? No, on the end.
Here.
There, yeah, that's it.
Okay. Yeah, so you showed a parameter space scan about future HLLHC. So although there's a region where you'd actually see the Z prime, there's a fairly substantial region that you wouldn't. So my question is for the folks who are contemplating muon colliders, is there an interesting region? You may not be able to produce it, but even if you don't produce it, you can often see evidence for higher Z prime states virtually, just by looking for virtual Z prime couplings to incoming muons. So have you thought about what the reach of a muon collider would be, taking that into account?
That's a very good question. No, but let me ask you, what's the nominal energy for the muon collider? Because it depends on that.
Yeah, sure. I mean, eventually, I think they're talking about a couple of TV.
Couple of TV. So yeah, it's a good question, and no, we haven't looked into that. But let me say that the muon coupling can be fairly sizable. So the thing is this: what you constrain from solving the B anomalies, is you constrain the coupling over the mass. So if you increase the mass, you have to crank the coupling up. So up to the right-hand side of this, you're starting to get non-perturbative. So you can't go on forever. You want to stop around here. But yeah, it's a good question. I mean, what we have done is we've done studies for the FCCHH, and that can definitely find this.
So there is one more question at the very end.
Okay, hi. Does this work? Does this work? Okay, good enough. How worried are you about the Higgs couplings? If I understood it right, you have a doublet that breaks just the electric part and not the U1X, and that only gives mass to the top and the muon. How do you get the Higgs to tau coupling?
There's a standard model singlet that gives mass to the X. The Higgs, yeah, you're right, the Higgs doublet contributes to the mass to the X and does the normal job. So, there will be bounds on flavon coupling to the Higgs because it goes like theta, dagger, theta, Higgs, dagger, Higgs, dagger, Higgs. You can tune that to 0, but I mean, we're interested, generically you'd have it, and we're looking into that now, the flavon phenomenology. It doesn't kill everything, but there are bounds on this, upper bounds on this coupling of order 0.1 or something.
Yeah, okay, that's actually not what I meant. I meant you have a 125 GeV scalar in there. Does it couple to tau the way it should? And,
yeah.
and not much larger to the muon.
Yeah.
That works? Okay.
That's fine. Yeah.
I think one last question by Athanasius.
So, very nice talk, Ben. Just to understand, this yellow band there, you explain the RK, right?
Yeah, explain RK and all the other B anomalies, yeah.
Even with Z prime mass equal to 0?
Well, that's yeah, but in the limit towards 0 with a very small coupling, yeah. I mean, okay, it doesn't. The left-hand side of this plot isn't 0. It's like 200 GeV. Our fit breaks down when the Z prime mass gets of order the electroweak scale. What I didn't say is that. Let me show you this. So here's the fit. 1 second. Here's the fit. So we have to, as I said, we changed the electroweak precision data predictions. So we have to fit that at the same time as all the B anomaly stuff. You can see the standard model fit here, and our model fit is in red. And what you see, this is pre-CDF2, but you see that we've fitted MW better, by a couple of sigma, no great shakes. But yeah, so this has changed. I've forgotten where I was going with that, but never mind.
Okay, let's thank Ben again. Call to the podium, last but not least speaker, Steve Abel, who's going to talk about genetic algorithm actually, as a search tool in a completely different field, in the string landscape. Okay, thank you.
Okay, so can you hear me? So thank you very much for the invitation to the organizers. It's always nice to be back in Ioannina. It's one of my favorite holiday spots. I was asked to talk about these two pieces of work, and mainly the second one, which appeared last year, with Andres, Konstantin, and Lucas, and Thomas Harvey. And we were interested in the performance of genetic algorithms versus other forms of machine learning. And the particular thing we were looking at was the string landscape, and I'll explain a little bit about what I mean by that. So by way of motivation, let me talk about string theory. I'm not going to pound the string theory too much in this conference, because I'm really more interested in genetic algorithms and selling that to you. But anyway, so the string landscape, for me, it's not really anything to do with the potential. It's to do just with, if I construct some sort of string theory, and I have some set of parameters I can choose, and a parameter space, typically that will give me a parameter space which is enormous. It's 10 to the 500 was Douglas's original estimate, but sort of ridiculously large numbers have been estimated by various people. And so those sorts of spaces, you can't really find the standard model in them with any kind of deterministic search. So that's the problem. You can't just do an exhaustive search of those parameter spaces, and so typically what you're left with is a set of Diophantine equations to solve, pretty much like the anomaly condition equations, and those tasks are computationally hard, you say. So there's an entire subject of complexity theory, computational complexity. These things you would call probably NP hard in that subject, you would call them. So those sorts of problems, if I increase the parameter space by a little bit, the difficulty increases exponentially. So that's the problem. So there's no chance of exploring that parameter space normally. If you're interested in that particular aspect, I'm going to recommend these papers by Jim Halverson and Fabien Ruel. So they've become the kind of doyens of that particular aspect. So because of that, in recent years, there's been a lot more emphasis, well, certainly in string theory, but also in supersymmetric phenomenology, for example, in exploring parameter spaces with machine learning rather than just doing an exhaustive scan. And so that's our kind of starting point for this study. And the thing we're aware of is that at the same time, there's this technique called genetic algorithms, which has been around for a long time, so since Turing's time. And so this technique, it obeys the rule of thumb that all crazy ideas are either Feynman's or Turing's, so this is Turing's idea. And there was some sort of development about how it should work, but Holland is the person that really kind of brought it to the fore and developed a technique for it. So that's the scheme we're going to look at, genetic algorithms. It's an evolutionary search mechanism. So you'd say it's a heuristic search, and it's based on evolution. So things I'm going to tell you in this talk will sound mad, but in the end, it will give you results. So before I start explaining it to you, so let me just give you a little bit of the backstory of genetic algorithms in particle physics. It's not a very big story. So probably from 2000, people were talking about this sort of thing. There was a paper, an early paper by your previous speaker when he was just a toddler, and Fernando. Well, he's not a toddler now, clearly, but anyway. And then some various other works. We first applied this to string theory in 2014, so I'll talk about that. And then there's not been much, but then more recently there's been more interest. So I think it's growing again, the interest in genetic algorithms, and I'll show you why, hopefully convince you that it's worth thinking about. So that's the overview of what I'm going to say. I'm going to introduce them to you sort of in a very pedagogical way, because I know most people won't know about them. So you either do or don't, and typically you won't do in this audience. And then I'll talk about the first thing we did, which was our 2014 work, and then the more recent thing, where we compare it to reinforcement learning techniques, the exact same models and so on. And genetic algorithms turn out to be, just as good, in some senses, in some ways superior to reinforcement learning. Right, so let me sort of begin with a bit of pedagogy, and I'm going to use a genetic algorithm to solve a task that you can all do, which is if I give you a function to find the maximum of it, or the global maximum in some domain, and you're supposed to do it without using calculus. So you're not allowed to use calculus. So this is how you would do it with a genetic algorithm. So the first thing you do is a genetic algorithm. It doesn't work with anything like calculus. It's basically I put all of the data that I can possibly have in a long string of data, and that defines a population for me. So the data I'm going to use for this problem is I'm going to take my x coordinate is A point B, C, D, E. So I've just got a long string of numbers, and then my y-coordinate is another long string of numbers, and if I say I want 250 decimal place precision, then I've got a 10 to the 500 size problem. Okay, so as far as the genetic algorithm is concerned, everything looks like a string landscape. Okay, so genetic algorithms they don't have any tricks apart from just playing around with these digits. Right, so this is where you start. You're going to define a population. So an individual in the population is defined by this list of numbers, that list of digits. So there's 500 of those digits. And we call that a genotype. And that list of digits produces some physical property. So in this case, it's a phenotype. You call it a phenotype. In this case, it's the function. So it's just the function of x and y is called your phenotype. So think of that as the physical properties of the creature. And then what you do is, so that means a creature will be living somewhere in the landscape, and its fitness, its physical property will be the height on the curve. Right, so then you define a population of these things to start with. So there's 100 of these things, and you sprinkle them at random over the domain. And what you do is you define a fitness function, and in this case it can be you can just rank them by how high they are, because you want to that's the thing you want to maximize. So maybe you just rank them, or you can define some other fitness function. It could be the function itself. It doesn't really matter, but you just have to get some kind of ranking to decide which are the good ones and which are the not so good ones. So that's step 0. And then you select them for breeding. Right, so this is where it starts to get a little bit crazy, but anyway, you select pairs of these creatures for breeding, and the selection process is probabilistic. So if a creature is fitter, you select it more often for breeding. And the way that you typically talk about this is that in the population, the worst individual, so the ugliest individual, sorry, that's the one on this side, the ugliest individual gets to breed less than the fittest, most beautiful one. Right? So P1 is alpha times P n pop. And alpha is a parameter, so it could be something like 3. A few more times, the fittest individual breeds a few more times than the least fit. If you're used to machine learning, you can think of this alpha as the learning rate. It's kind of a similar sort of parameter. So then you define a probability based on that. and you select pairs for breeding. So you make breeding pairs, and so each member of the pair will have a different set of digits. And what you do is you just take that long string of 500 digits, cut it at some random point, and swap the ends. So it's some kind of splicing process. Produces 2 more individuals which go into the new population, and you throw away the old ones. They wither and die, as happens. And but their children go on. And so that's the breeding. And then the last step, before you have a new population, is mutation. And so this is more important than you might think. What you do is you take all of the entire population, and the digits, or the alleles as we call them, what you do is every so often, so maybe 1% of them, you just mutate, so you'll randomly change it. And so you get slightly mutated individuals. And that's an important, as you'll see, it's an important aspect of what's going on. Right. Okay, so then you sort of rinse and repeat. So that produces an entire new generation. You go back to the beginning, you work out the fitness of the new generation, you select them for breeding, you breed them, you mutate them, and so on. You just repeat that. And what happens is you get to solve the problem that way. So let me show you what happens with this function, so this sort of toy problem that I'm showing you. So you begin with a population sprinkled randomly. After 5 generations, they start to cluster around the solutions that you know are there. And so after 10, you get that, and after 20, you get that. So at that point, you would, if I was actually trying to solve it this way, I would, if I was close enough, I would sort of concentrate on the good ones. You might look at the population and see which are solving it and which aren't. So that's on a sort of continuous problem. You can, so now let me show you some good points about this way of solving a problem. So if I have something that looks like that, so that's a much more complicated function, and it's got a large number of little lumps in it. It can still work to find the global minimum. And so it may take a few more generations to do it, but eventually the population will crowd around the maximum. It'll crowd around the maximum and find a solution for you. It doesn't really care too much about the sort of small features in the landscape that it's going through. It's kind of sampling with this process the whole landscape all at once. Right, so that's the way they've looked since sort of the 1950s, basically, and it's kind of controversial why they work, these things. There's a theorem of Holland, which is probably why his name is associated with this technique more than anyone else. So Holland's idea was that there is something called a schema at work in the population, and you can almost see it in this diagram. So in this diagram, if you think about what the x and y coordinates are, the first 2 digits, so the first 2 digits in y and the first 2 digits in x, are much more influential on the fitness than the sort of later ones, than the other ones. So if I'm Holland, I might define a schema that looks like that. So the first 2 digits of x are 6,1 and of y are 6,2. And you see the population does start to line up along those lines there, along 6,1 and 6,2. And Holland's idea is that if that thing happens to randomly appear in the population, where there's a 6,1 there and a 6,2 there, it will exponentially propagate through the population very quickly. And so before long, a lot of the population will have that schema. So that's the way they're supposed to work. It's kind of controversial, though it was sort of rehabilitated somewhat in the 1990s and early 2000s. And there's other work also which is more focused on the correlation between the fitness and the distance in what's going on. That also seems to be important. There isn't really a very good theory of this, though, it has to be said. But it seems to work. Right, so let me talk about string theory. How long do I have left? 10 minutes? Okay. Right, so let me talk about the first string example we did using that technique. So this is with John Rizzo from here. And Alan introduced those sorts of models to you, so I'm not going to go into a great amount of detail. So Alan Faraghi yesterday talked about these models. They're basically very similar models that we're looking at. It's the same technique. And we were looking here for Patti-Salam models. If you remember from the talk, there was a set of boundary condition vectors which you have to fix. And so that was found by these people, and then and also Nanopoulos, Antonios, Hagelin, Ellis, sort of based on that. And then in addition to that, you have a set of projection phases. So these phases can be plus or minus 1, essentially. And then in the end, it all boils down to having to choose in this matrix of all these phases, choose which ones are going to be 0, which ones are going to be 1, and there are 51 independent ones, so it gives you a search space of 10 to the 15, roughly, 2 to the 51. So that was our genotype, is basically that sort of just all of those phases, 0s or 1s. That's our genotype, and that's our population. So then we run things. And what we're going to do is we have to define a fitness, remember, and the fitness here is going to be its phenomenological properties. So we're going to ask for example, 3 generations, Patti-Salam breaking Higgs, a standard model Higgs, and also then what's more difficult, absence of fractionally charged states, so you don't really want those around, and an existence of a top-Yukawa coupling. So this search space, we can do it deterministically, just about. It takes a week or 2 to do it. So if I ask for A, B, and C, I know, because I've done that scan, I know that there's 1 in 10,000 satisfy A, B, and C of these models. 1 in 2.5 million will also have an absence of fractionally charged states, and then the top Yukawa really pumps it up a bit, so then it's 10 to the 10 billion. So let's see how in theory, what you would expect is that if I was just searching for these models, you have to construct about 10 billion models in order to find one that works. So we can kind of use that as a measuring stick in order to see how we're doing. So this is what you find using the genetic algorithm. And so getting back to the mutation, you see that mutation is an important aspect of this. So here what I'm doing is I'm mutating at about 1%. So about 1% of the alleles I randomly flip from 0 to 1 as I go along. And you see that there's a kind of optimum percentage of allele flips. And then here on this axis, I'm telling you how many times I've actually had to construct a model. So every time I have a new generation, I have to construct another 100 or so models. And so in total, even for this one, where it's 10 to the 10, in principle, I actually only have to construct 10 to the 5 in order to find a model that works, that satisfies all of that. So it's super efficient. And you can see that this one, so if I don't ask too much, it's actually not a great benefit to have a genetic algorithm. So this one doesn't really care about the mutation rate, and the reason why is the genetic algorithm isn't actually giving you very much. And so they work best when there are a lot of criteria and the search is difficult, basically. That's when they really sort of come into their own and you'll get a real advantage over just a scan. And the fact that you have an optimum mutation rate is really telling you that the genetic algorithm is the thing that's working here, because that's really just a sort of purely a genetic algorithm thing. Right, okay, so now let me talk about the more recent paper. Do I have 5 minutes or so? Yeah. Okay. Right, so the more recent paper from last year, and there was also related work by these guys, by Gary Hsu and friends and Sven Krippendorf and friends. And what we were doing is we wanted to then look at it didn't really matter what the sort of model was, but we wanted to compare genetic algorithms with a typical machine learning technique you might use, which is reinforcement learning, and see how they do. So I'll show you how they do. The sorts of models we studied in this paper, I mean, it doesn't really matter what we were looking at. It could have been anything, but we were choosing, so these ones, complete intersection Calabi-Yaos you start with, and then you break them. So these are the Calabi-Yaos that we start with. If you know them, then these are the configuration matrices for them. If you don't, it doesn't really matter. The important thing is this number 2 and the number 3, which is this H11 Hodge number. So that tells you essentially how many integers you're going to have to define your theory. And then what you do is you break it by adding vector bundles onto the Calabi-Yau in order to break it down to an SO10 group structure, so in order to get some phenomenology out of it. It's quite complicated in order to do it because you have to maintain supersymmetry all the time. So there's various quite complicated mathematical criteria you have to satisfy, so polystability, if you know these things. But anyway, in the end, it boils down to having to choose a set of integers again. And so this is the set of integers. K here is given by the Hodge number. Right, so what we did is we ran those things. We looked for perfect models. So a perfect model for us is, well, it's quite far from perfect, but essentially it has the ingredients you need in order to get down to a standard model. And the size of the search space, just before we start, so these numbers, they're actually not bounded, so we can have an infinite search space if we want, but we have to bound it. So we choose 10 possible integers for the B's and 10 for the C's, and if we allow 10, yes, because we're allowing 10, so you get 10 to the H11, so that's 2 or 3, times by these numbers, so that's the number of B's for every K. Right, so this can get huge, very large, very quickly, get very large. The genetic algorithm we ran on these things, it worked best when the population was larger for some reason. Okay, thanks. When the population was larger, which kind of suggests to me we didn't really do it as efficiently as we could have done. But anyway, we ended up with something like 250 individuals in a population. And then comparing reinforcement learning and genetic algorithms, we used the same function to stand for the fitness for the genetic algorithm, or in machine learning, that would be the reward. So I'll say a little bit. I've got one slide on the reinforcement learning. Right, okay, so here we go. The reinforcement learning, they'd already done this, by the way, so we know that it's amenable to reinforcement learning. This is my slide on reinforcement learning. This is roughly the way it works. So the topology is kind of similar to what you do with a genetic algorithm. So you will have a model. You work out its fitness, if you like, so whether you like the model or not, does it satisfy those conditions? And from that, you work out a reward. The reward goes back to your agent, as you have in a reinforcement learning situation. And so this is what you call policy-driven. So what you have is a neural network, and the neural network figures out the probabilities of the next move it's going to make. And so ideally, if you kind of iterate this process, it ends up with the neural network kind of learning the best move to make in order to get you to the solution. Right. So that's the way it works. No one actually knows, really, because all you do is you just download it or use it in Mathematica. So all of these sort of gubbins here is in this package Reinforce, which you can use. Right. Okay, so this is what it does. So this is reinforcement learning. With these numbers for B's and C's, so we're choosing those integers, the search space is 10 to the 12, so it's kind of moderate, really. And what happens is you have a long training period, so you have to do about 80,000 or so, up to 100,000, and at some point, it'll get the idea, and then after then, it will immediately sort of just go to, when you start at some point, it will just go to a close solution. It'll learn how to do that. So that's the way it works with reinforcement learning. So the thing which stalls you, takes a long time there, is the training period. So it's the training period which is kind of the block, really, with reinforcement learning. So this is a genetic algorithm on the same thing. So the first thing to know is we start to get solutions very quickly. So you find solutions much more quickly. There's no sort of long training period with a genetic algorithm. So if all you want is one solution, choose a genetic algorithm. Don't go for reinforcement learning. And so you can see why. What happens is, so I'm plotting here is the generation number, and this is the fitness here. And so fitness 0 is the best you can get. The population sort of crowds around fitness 0, and you can see that here. So after 100 generations, the fraction of the population, about 2/3, are sort of as the fittest individuals, but everyone's sort of crowding around, mutating around those individuals. So that's why the solutions start to pop out fairly quickly. They behave in a slightly different way. So if you look at the genetic algorithm, there's quite a lot of redundancy to start off with. So it will start to give you equivalent models. And so you can plot the inequivalent models as a function of the number of states it's produced. And there, the reinforcement learning, it starts off kind of doing quite a bit better than the genetic algorithm. It produces more inequivalent states, but it takes an awfully long time to saturate. So it takes 35 core days to find them all. There's about 600 in this parameter space. This is the genetic algorithm. After only 1 day, it's already got 2/3 of them. So you see, in a way, it's very efficient. If I just want some, then I can do it very fast. So, and then the time to saturation, the reinforcement learning takes 35 days. The genetic algorithm, it took 10 days. So it's still 3.5 times faster than the reinforcement learning, even just to find to saturate. And if you compare the saturated models, you see that it's the same. It's roughly the same 700, 650-ish that they find. So there's an additional benefit now, which I want to advertise very strongly, which is that when we started doing this at the beginning, they will start to cover different regions of the parameters. So we thought that they were actually looking at different areas of the parameter space, but eventually they fill in the same hole. And so at that point, when we find that they've got the same 700 models, we're fairly sure that in that large parameter space, which we're probably not able to deterministically survey, we've got all of the standard models that are in there. So it's a way to really learn something more about the standard model than you can get with just one of these techniques. Okay, I've nearly finished. So this is just to show you what happens when I do the other Calabi-Yau, which is more complicated. So Hodge number 3, you get the search spaces 10 to the 19. So this is quite a bit bigger, and we would definitely not be able to do this deterministically. The genetic algorithm, so it's the same two graphs, it starts to give you solutions after 300 generations. So it's twice as many generations, but you see the search space is much bigger. It's much bigger. It only takes twice as many generations to start reaching saturated fitness. Right, okay, so let me conclude. Right, so we were comparing GAs to RL in popular string constructions. They remain a strikingly effective tool for finding string vacua, and in some senses they're more efficient. We didn't really work that hard to optimize it, to be honest. We looked really at population size and mutation rate, but the rest we were really not working too hard to optimize. So you know, I think it could be even more efficient still. One thing I'd say about, just if you're interested in the string landscape, these numbers, 10 to the 200,000 or something, I think they're just silly. That's my viewpoint. I think what's important are things like the fitness distance correlation in that sort of landscape. So if I know there's a model there, how much am I drawn to that model in the landscape? You know, how much do I improve as I approach it? Is it a needle in a haystack or not, essentially? So that's the important thing, not these numbers, which, as you saw at the beginning, I can make ridiculous numbers with no problem. And then this is one of the most important things we find, that if you take combinations of these heuristic search techniques, you can actually learn something about this sort of thing, about the landscape, for example, which you can't learn with only one of them. Right. Okay, I'll leave it there. Thanks.
I think we are following the wrong field. Yeah. Right, so let me see. Let's start with Ben here.
So when we played around with this, we were doing it, genetic algorithms with the continuous parameter. But my sort of gut feeling, which I didn't really know whether it was true, was that they particularly come in the rain for discrete problems, where you have a lot of different... Would you agree? Is that, that's your experience?
Yeah, exactly. Okay. Yeah, so like with your thing, for example, is probably also something you can treat with a genetic algorithm, solving like anomaly conditions and stuff. So the reason it works better is a continuous problem. You know, if I'm trying to find the top of a hill, at some point my derivative goes to 0, and I have to kind of try and focus in So I need a lot of digits in order to do it. But discrete things, yeah, it's much easier to solve. So that's why it works pretty well, because it doesn't care about whether it's a discrete problem.
How here? Excuse me.
Right. Suppose you were trying to do a minimization problem, and suppose there are two deep minima, but one is deeper than the other, maybe slightly.
Yeah.
How often do you get trapped in the wrong minimum?
Right, so this is the way that they work, because that is the problem with, if I'm just doing like a gradient descent or something, I'm just going to fall into a local minimum. The thing which stops you doing that is the mutation. So what mutation does is, if you're stuck there, at some point someone in the population will get mutated and sort of leave this thing. It's not, you shouldn't think of it as a dynamical thing. So the new population has there's no kinetic term in this thing. It's just got a new location. And it'll start from somewhere else and then maybe find the new minimum. So yeah, that's why it's supposed to work. What the mutation does in that sort of situation, you can think of as kind of pushing you out of the minimum. It's like the population is sort of pushed out of the minimum by mutation, yeah.
Sort of a follow-up to this. If you want to find more solutions, are you better off just waiting for these mutations to find new solutions, or are you better off to just start from scratch again with a new population?
Right, so yeah, there are techniques you can, that's a good question. So you can, if I start again, my chances of finding a new solution quickly are less than if I start with sort of some mutation of the old population. So you can take the old population, do a mutation of like 20% or something, and then run it again, and it will find more solutions more quickly if your parameter space has a lot of solutions in the same place, you know. So that does quite often, something you do quite often.
Thank you very much for this nice talk and very interesting work. I want to ask something which probably is not doable, but as you know very well, in string theory, if you start pinching the cycles, the Calabi-Yau, for instance, then many vacua are equivalent. And that's how Strominger tried to argue about black holes and whatever. Can you use these genetic algorithms to have a parameter that somehow can take into account this pinching so as is not static, but somehow you vary this, so you have defects, if you like, in your system?
So you want to use it, you want to find a value of a parameter that will give you
that will give you the equivalence of vacua, for instance, or whatever.
Oh, okay.
If you can.
That sounds like a very convoluted demand. Possibly, I'll say possibly. Yeah, I can't think of anything right now in real time.
I mean, the thickness of the Calabi-Yau compactification, for instance.
Right. I mean, so if you can have a parameter which will tell you, so if I'm thinking of just creating some defect, if you have a parameter which is, say, something like the energy of the defect or something that can go into the fitness.
That's right. Yeah. To blow up somewhere.
Right. Yeah. Then that could be something you can. If you can put it into a fitness, then you can do it essentially. Yeah.
Thank you.
Last question.
Yeah. A bit related to the mutation. How much does the genetic algorithm depend on the mutation size with respect to the mutation frequency? Is it totally equivalent, or?
So with this, so the mutation, when we were encoding this, it's a binary. So the mutation is turning a 1 into a 0. So there's no
just one digit over.
Yeah. So when it's binary, you can just change a 0 into 1, and then you optimize it for the number of changes you would make. So you would do, say, 1 in 100 or something. So that we optimized. I can't tell you what it was, but it's something like 1%, something like that.
Okay.
Okay. There are no other questions. You want to ask the last question? You are very present.
Hi, Stephen. Thank you
Hi.
very much for this very exciting talk. I actually had multiple questions. So I'm going to keep for one. So you're saying that you have this issue with trying to converge to full coverage of the parameter space. So I'm assuming that you didn't do anything to the fitness function to try to enforce more exploration?
So which problem are you talking about? Converging?
Trying to find all the solutions.
Oh, okay.
Which is basically trying to maximize the coverage of the parameter space that you're scanning, right?
Yeah, that's right. So we didn't really change the fitness function very much. We didn't play with that too much. The reason why is there's so what it is, it's a set of a lot of conditions which are Diophantine conditions, and so the fitness function is essentially how far are you away from satisfying that.
Yes.
And so you can kind of try and reweight them a bit, but it doesn't make that much difference. There's too many of them to play with, essentially, to be able to do anything meaningful. You could probably use a genetic algorithm to optimize that. I don't know.
Well, yeah, no, there are prescriptions to avoid repetitive solutions and try to maximize coverage.
Yeah.
So there are prescriptions.
Yeah, so I think we probably could optimize the fitness function better than we did, actually.
In following Ben's example of self-promoting, I'll be talking this afternoon about things like this, including genetic algorithms to scan continuous parameter spaces of the CMSSM and the PMSSM.
Okay, right, yeah. So yes, you can also use it for SUSY, so you should go to his talk.
Okay, I think, we come to an end of the session. Let's thank Steve and all the speakers. See you in the panels. No, there's one more. After the line.
φοιτητό με το αυτοκίνητο. Κάτσε εδώ δηλαδή. Μετά το βράδυ. Δυστυχώς. Μπορώ να φύγω για να φύγει. είσαι χθες, 6 € έχει, βέβαια. Ωραίο. Εγώ πώς θα πω στην εκλογή συστημικής ως τι ωραία το ξέρουν ή ως το παλιό μου το κρατάω. Έχω και δύο απέναντι σε πάλι. Μία είναι παγωμένη, αλλά μπορώ να πω. Αυτό είχαν να πω, δεν μου είπαν τίποτα, τους το είχαν ζητήσει με το Πολυτεχνείο. Ως Ελλάδα, ως μεταπίσεις, στο Αραβία. Τι που φορέει. Ναι, ακριβώς. Πάμε στο λίγο. Τι είναι στο λίγο, αυτή είναι η κυβέρνηση. Μπορεί να έχει επιλογή. Να μου αξιοποιηθεί. Τι είναι, είναι άσχημα. Είναι του αλφα. Δεν ξέρω. Τι είναι, τι είναι, τι είναι. Όχι ένα πληρώνει. Δεν έχω, δεν έχει κλείσει. Άμα δεν έχει κλείσει, δεν μπορεί να κλείσει. Άρα δεν είναι που όχι μας είναι άσχη, είναι που αυτή του μανουσάκι του. Δεν το κάνει.
Θα κάνω λίγο, θα βάλω λίγο μουσική.
Δεν μας πειράζει, ευχάριστο.
Όχι εξαγωγή,
όχι, αλλά λέμε, μια καλά.
Αλλά μπορείτε και να διαλέξετε και κάποιο.
Πάμε να πάμε το πιτσάκι. Εσύ δεν θα έρθεις, ναι, ένα μόνο, μία ομιλία. Περίεργο. Μα δεν καταλαβαίνω, γιατί μας είπαν να ξεκινήσουν 2,5, δεν σκέφτονται αυτό. Ας τους 3,5. Δεν σκέφτονται. Αλλά δεν έχει χρόνο να φάει. Πάμε εμείς να πάμε ένας άλλος τότε.
Έγραψε, λοιπόν, κάτω, έχει 3 εξεδάρια εδώ πέρα, δεν το σχόλιο. Θα το πάρω από πίσω, λοιπόν. Όλο, όχι, έχει εξεδάρια, θα πει, θα πει όλο.
Μα δεν έχει.
Τι σημαίνει το είναι?
Δεν ξέρω. Σφυλότητα. Δεν νομίζω ότι είναι σφυλότητα. Δεν νομίζω ότι είναι λογική. Δεν έχει τέξει.
Δεν θα έχει να μην πω. Τα υπόλοιπα.
Άρα δεν μπορείς να βρεις τίποτα. Άρα δεν μπορείς να βρεις τίποτα. Άρα δεν μπορείς να βρεις τίποτα. Αυτό θα είναι. Πάμε να πάμε λίγο. Θα πάμε εδώ. Εντάξει. Έχουμε μια ώρα. Θα λέμε και εδώ θα είσαι εσύ. Ωραία.
Duri.
Your talk is not uploaded, Steve.
Yeah, it is.
It is. Okay. Τι είπε? Να έρθει εδώ να το κάνει, άμα είπε, okay. Ο Γιώργος. Ό,τι θέλει μπορεί να κάνει ο Γιώργος. Άμα το φτιάχνει αυτός όμως, όχι όταν το φτιάχνει.
No. But yeah. Thank you. Very good. Very good. And this works?
Yes.
To move the... Okay. Yes. Excellent. And this is the point. Okay, very good.
You have the unification? No one else.
Eh?
No one else said anything.
Exactly.
And also about the hierarchy.
Yeah, nobody
mentioned.
Nobody mentioned
Only
anything.
today, I think,
No one mentioned anything about Higgs.
About SUSY.
Yeah, about SUSY, yeah? Yeah.
alargar acá en 25 minutos tengo, ¿no? Sí, lo voy a alargar cuando empiezo.
Va a dar la charla a Steve, después que la tuya, porque
Perfecto.
como mañana no va a haber nadie prácticamente.
Perfecto. Sí. Me parece bien.
No, yo él quería mucho, porque mañana
Obvio.
la audiencia ya no
Cada vez queda menos gente.
Ahora queda menos gente.
Sí, así es. Hello.
Okay, so I think that we can start this afternoon session. There has been a little change in the program. So the second speaker was cancelled because of COVID. And then Professor King is going to give his talk after this one, before the coffee break. Okay, so the first speaker is Professor Wagner. He's going to talk about supersymmetry and experiments.
Okay. First of all, I want to thank the organizers for the kind invitation to your talk in this fantastic place. And today I will talk about certain aspects of supersymmetric phenomenology that I think have not been emphasized yet, and in my opinion should be mentioned, at least before the end of the conference. Well, we are all aware of the virtues of supersymmetry. In particular, I believe it's important this property that it can induce electrodynamic vacuum in a radiative way. That means starting with parameters that are all positive or even common parameters. So the Higgs mass parameter evolves to acquire negative values. Well, this is the soft breaking parameters, inducing electrodynamic vacuum. And the way it does it is via a property that the mass parameters of the model evolves in a way that is proportional to the corresponding Gaugino masses, so under which the gauge groups under which this particular particle is charged, and also Yukawa coupling. So in particular, the stop mass parameter, for instance, are bring down due to Yukawa coupling effects, and also the Higgs mass parameter that couples to the stops. So the particular, what we call the Higgs up, is also bring to negative values due to this effect. So this effect has two things. First, induce electrodynamic braking, and second, make the stops to be lighter than the other quarks in the spectrum. So the first issue will be interesting to look for stops because tend to be the lightest quarks in the spectrum. Now, about stop searches, we have also guidance from the Higgs sector, as I said. In particular, for instance, in the MSSM, the Higgs mass can be determined in terms of the tree-level value that is proportional to the set mass, and radiative corrections that are logarithmically dependent on the scale of supersymmetry, that is the common scale of soft supersymmetric mass parameters of the stops, and also has a polynomial dependence, quadratic and quartic dependence, on the mixing parameter appeared in the stop sector. And to give you an idea, what are the predictions for the Higgs mass, I give you these two pictures. One, in both cases, tangent beta is large in order to maximize the tree-level value. But, so in this case, the mu parameter, that is the supersymmetric Higgs mass parameter, has been chosen to be very small, and in this case has been identified with the scale of the stop masses. And these are the corresponding values of MH that you obtain as a function of the stop mixing parameter. And as you see, this the black line is for a common mass of order 1 TeV, blue 2 TeV, this is 5 TeV and 10 TeV. And as you see here, so if you put masses of order 1 TeV, it's hard to get the value of 125 GeV. And instead, if you identify mu with MS, it's even harder. So that means that naturally, to get the realistic Higgs masses in the MSSM, you need to go to stop masses of order of few TeV. And this has to be contrasted with the present experimental limits on the stop that, okay, so then depending on the decay modes, so and the spectrum, so range from values of order 1.3 TeV to of order 600 GeV. So the message here is that we are just starting to explore the mass relation associated with the Higgs mass determination, and we should make an effort to continue exploring the stop mass parameters, because actually, so the stop may lie ahead. So regarding the Higgs, I think that it's very important to emphasize the good agreement that has been established between the experimental measurements and the predictions of the Higgs mass and the Higgs couplings within the standard model. You see, this is the ratio, the kappa values that are the ratios of the couplings that you obtain from the data compared to the standard model. Kappa equal 1 would be just perfect standard model fit. And you see that only deviations of orders a few tenths of % are today allowed for the coupling to the gauge bosons or for the third generation fermions. And even for the second generation fermion, the mu, so the central value is already very close to 1. So we are facing a situation in which the Higgs that we are observing resembles very much the Higgs of the standard model. However, in supersymmetry, you have two Higgs doublets. So the question is, how can you obtain a good agreement between experiment and theory? Well, let me just emphasize that in two Higgs doublet models, based on the angle alpha that is defined from the particular combination of the neutral components of down Higgs are coupled to down quarks and up Higgs, and the tangent beta, that is the ratio of vacuum expectation values, the deviations of the couplings in the down sector, up sector, and to the gauge bosons are parameterized by sine beta minus alpha, that tends to be 1 in the case of a standard model Higgs boson, and corrections that are proportional to tangent beta times cosine beta minus alpha in the case of the bottom sector, the down sector. Now, if you got a large values of tangent beta that we are considering to get the right Higgs mass, you see the most relevant corrections are associated with the bottom coupling. And the bottom coupling is very important because it's just the dominant decay branching ratio that was set in standard Higgs. So it's very important to keep this close to 1 to recover the experimental values that we observed. Now, this brings us to the condition of alignment that is demanding that tangent beta times cosine beta minus alpha is significantly lower than 1, or cosine beta minus alpha close to 0. In the MSSM, you can compute the value of tangent beta times cosine beta minus alpha, and has a dominant dependence that is independent of tangent beta, that depends only on the ratio of the Higgs and Z masses compared to the mass of the new heavy Higgs boson. And that's why when you compute, numerically, the ratio of the down quark couplings with respect to the standard model values, you obtain values that are roughly independent of tangent beta and depend only on the mass scale of the new heavy Higgs bosons. That means that for tangent beta sizable, essentially what the present fit to the data, what tells you is a lower bound on the mass of the Higgs. Now, there is a contribution that comes at the loop level that is loop suppressed but tangent beta enhanced, that can also have an effect in the condition of alignment, in the condition of determining the deviations of the bottom coupling. Now, it turns out that these corrections can only be relevant when the values of the soft breaking parameters, AT and mu, are large compared to MS. And just to give you an example, this is what happened for small mu, so where you get the ratios, the branching ratios of Higgs to WL, for instance, are just governed by MH, and this dependence comes just from the bottom coupling. And what happens with sizable parameters, where you can get large regions of parameters where there is essentially good agreement with the standard model. Now, this indirect bound on the Higgs masses, on the new non-standard Higgs masses, can also be compared with the bounds that come from direct production. Direct production can come from diagrams like this, in which you have associated production of the Higgs with boson quarks, or gluon fusion that can be governed by either boson or top quarks running in loops. Now, the present bounds on direct searches for heavy Higgses are depicted here, as was presented in some previous talks. And you see that there is essentially a 2 sigma excess, roughly, that maybe is not very compelling, but is prominent. And this should be compared with the bounds that you obtain from indirect searches that come from the fit to the couplings, that provide a bound that is about 600 GeV. So then that means that these two bounds become complementary. Right now, for sizable values of tangent beta, the direct bounds are the most important ones. But when you go to lower values of tangent beta, like it happens in the MSSM, for instance, these bounds start to become also relevant, the indirect bounds. So now, something happened in what is called the NMSSM, that is the extension of the MSSM with a singlet. In that case, you have still the stop corrections that allow you to bring the Higgs mass up, but there is also a 3-level correction that is proportional to this new coupling that you introduce in the model that couples the singlets to the Higgs doublets of the theory. And that provides a correction to the Higgs mass that is proportional to this coupling squared times sine square of 2 beta. That means that goes to 0 for large values of tangent beta, and this goes to 0 for small values of tangent beta. Now, what is interesting is what happens with alignment. Alignment can be determined for sizable values of tangent beta like a condition between lambda squared b squared and the sum of mh squared and mc squared. So if that relation is close to 0, you get alignment. What is interesting is that independently of the value of tangent beta, the value of lambda squared that you obtain from the condition of alignment that comes from the cancellation of the off-diagonal element in the Higgs basis, so becomes roughly independent of tangent beta. And for values of lambda of order 0.65, you get essentially good alignment conditions independently of any other parameters in the whole region of tangent beta MA plane. So that means that these values of lambda are useful to bring the Higgs mass up, so with lighter stop masses, but also provide alignment, so independently of the other Higgs mass parameters. Now, what are the consequences of alignment, apart from a good agreement of the standard model Higgs boson with phenomenology? One important consequence is the following. If you have small mixing between the non-standard Higgs and the heavy Higgs, so that means that the decays of the heavy Higgs into two standard model Higgs tend to be suppressed. And the reason is that if you look at that diagram, so non-standard Higgs with two standard Higgses, you can put a Higgs vacuum expectation value in one of the Higgses, and you will obtain mixing between H and H. So the consequence of alignment is that the heavy Higgs decay into HH, and this is what happens today, allowing some misalignment, tend to be suppressed. Those branching ratios tend to be small. However, branching ratios of the heavy Higgs into a standard Higgs and non-standard Higgs can be very large in these models. So therefore, the consequence is that the non-standard Higgs tends to decay into exotic Higgses rather than into a standard model Higgs. And that motivates the searches for the case of the non-standard Higgses into a standard model Higgs and an exotic Higgs. That should be performed as has been performed in the case of decays into exotic Higgses and set-gauge bosons. So that is a very important message that I think that should be explored and has not been done yet at the LHC. Now, this concerns the Higgs and strong sector. What about the electroweak sector? Well, the situation here is far less well defined, so the constraints, of course, are weaker because of the weaker couplings. So, for instance, if you look at Stau searches, the bounds, maximal bounds are about 400 GeV, but only for a lighter supersymmetric particle that is below 150 GeV. If not, the bounds are very light. So then you can look also for electroweakinos in general. And here I want to emphasize that we can have different phases between the mass parameter of the BINO, the superparameter of the hypercharged Higgs boson, and the WINO, and also in the CP conserving case, different signs, and those can play an important role in phenological analysis. So the current bounds of electroweakinos, this is, depend a lot on the decay modes. So, but for the case of WINOs, the main decay mode is actually W Higgs, where the bounds are pretty strong, and I show you an updated bounds. You see that for the case, the associated production of a neutralino and a chargino decaying to a W, the chargino, and a Higgs, and two neutralinos, so can reach values of order 1 TeV. And this is very, very important. But I want to emphasize here that in the production cross-section of that is being used to compare the experimental limits with theoretical predictions, only the W diagram has been used, and the square diagrams have been ignored. But it's very well known that there is a destructive interference between the squark-induced diagrams and the W-induced amplitudes, and this destructive interference for values of 1 TeV and square masses of order of 2 or 1.5 TeV can be very important, can be factors of 2 or 3. So therefore, in obtaining these limits, it's very important to remember that one has used an approximation, and that approximation is very heavy squares, and it would be nice to rederive the limits in the case that you have finite square mass values of order of a few TeV, because these effects are very important. Now, the other thing that can happen in supersymmetry is that you can get a good dark matter relic density, so starting from thermal production, and this has been emphasized before. But and one useful way you can do it is via co-annihilation that brings particles that have higher annihilation rates than the pure neutralino with, for instance, the gauge bosons, to be close in mass to the lightest supersymmetric particle. And that will play a role in the rest of my talk. Now, another important thing is that if a dark matter exists, there are direct detection bounds on this dark matter that are becoming very strong. Now, some time ago with Pei-Si Huang, we analyzed the possibility of having interferences in the diagrams that lead to the direct dark matter cross-section, and it turns out that there are particular regions of parameters in where there are blind spots, where the amplitude cancels. And these regions of parameters are not crazy. I mean, for instance, I take the example here of mu for 600 GeV and 1 for 100 GeV, and you see that there is a whole region of parameters where the cross-section becomes much smaller for the case of mu negative values of the relative signs between mu and n1 than positive values. So it's very important to fix this relative sign in order to determine the real bound on the direct dark matter cross-section. And as you see, negative values lead to cross-sections that are much smaller. Okay, and that brings me to the subject of G-2 that was already discussed by Takeo Moroi and by John Ellis. So then you know there is an experimental discrepancy with the standard model prediction. The standard prediction is still being questioned, but you can go to the talk by John for more details. I will take this discrepancy seriously, and as Takeo emphasized, there are two main diagrams that contribute to G-2. One comes from the interchange of neutrinos and muons, and the other comes from the interchange of charginos and neutrinos. Now, the important thing of these two diagrams is this diagram is suppressed by mu, and this instead is enhanced by large values of mu. So when you go to sizable values of mu, then this diagram becomes dominant. When you go to low values of mu, this becomes dominant. So the other thing that is important to realize is that this contribution is proportional to mu times m2, the value of the Wino mass. This contribution is proportional to mu times m1, and everything is proportional to tangent beta. So that means that if you take standard values of delta mu, then there is a reduction of the cross-section for negative values of mu times n1 with respect to positive values of mu times n1, because, sorry, of the delta mu, because this will interfere with this diagram. So at the same time of the reduction of mu times mu, there is a reduction of the direct dark matter cross-section, also for those values of mu times n1. So then, as I said, the Wino contribution becomes negative here, so the dominant contribution, so you need mu times m2 to be positive. So, and since G minus 2 needs to be positive, compatible with between G minus 2 result detection, may achieve either for large values of mu, so for the case of mu times n1 positive, or smaller values of mu when the relative sign of the Gaussian masses is opposite. Let me emphasize, by the way, that I didn't say it, that the direct dark matter cross-section has different spots, but it's also suppressed by large values of mu. So this more or less represents what happens if you take n1 times mu negative, you get compatibility with the bounds that come from direct dark matter detection, spin independent and spin dependent, and a mu for low values of mu. That is this dark region that I'm emphasizing here, and this represents the LHC bound. Instead, if you take positive values, you get compatibility for larger values of mu, and actually that region of mu extends to larger values. And you can find benchmark scenarios for negative values of mu times n1, for instance, where you get the right dark matter with the proper spin-independent cross-section and spin-dependent cross-section, and passing all the LHC bounds. Now, regarding the LHC, it's interesting to compare the case, for instance, in the case of co-annihilation with a Wino that I represent here. It's interesting to compare the LHC bounds in one case and the case of, in the case of positive and negative values of mu times n1. In the case of positive values of mu times n1, there is a large exclusion that is represented here by the LHC. This band here represents the regions where you get the correct dark matter cross-section. This gray region represents the regions excluded by direct dark matter cross-section searches. And you see that there's only a narrow band of values that is still allowed by LHC searches and will soon be probed. So this should be contrasted with what happens with negative values of mu times n1, where again the LHC searches are here. These are regions of direct dark matter, we'll get the correct rate density, and this smaller region is a region where direct dark matter cross-section constants apply. All this region is allowed, and what is interesting is that in this region you get an enhancement of radiated decays of the second lightest neutrino to lightest neutrino. So there are regions of parameter space, and here I give you an example, where the branching ratio of chi2 going to chi1 and photon exceeds 30%, so it can be 20 to 30%, and therefore provides an opportunity for searches for this particle in novel ways, different from the standard ones. And we are performing a simulation to see in which sense these new decays can extend the reach of, for supersymmetric particles in this compressed region. Now, my final subject, new measurement in W, I want to emphasize two things with respect to supersymmetry. One is the MSSM stop contributions. You know, if you analyze what happened with the stops, I told you what happened with the Higgs mass prediction. The corrections coming from the stop to MW can parameterize in this way, where XT over MS plays also an important role. And you see that you can only get corrections to MW of order of several tens of MeV if XT is large, considering the fact that MS should be larger than about 1 TeV. But the problem that XT very large or MS so large, so if you take MS large, you need increasingly large of XT, and this is represented here. This is what you need to get the measured value by CDF. And you see that you need to go to very large values of XT. For those values of XT, the Higgs mass that is represented in the blue band goes below 110 GeV, so it's inconsistent with MSSM. So, in general, if you make an analysis, you can see that it's impossible to keep the MW correction large with values of the stop mass parameters that is consistent with the present stop mass and Higgs mass values. Now, there is another correction that you can have in two Higgs model that is associated with the Higgs couplings. So those corrections, and here I'm talking in the Higgs basis, and these are the quartic couplings of the Higgs basis. The Higgs basis is defined as the one in which only one of the Higgs requires a background expectation value. And then, that's me. So then, and that means I have 1 minute. So then, well, let me just say, stop here. Let me tell you that just to mention that MSSM, you can get such large corrections. However, those corrections get in conflict with alignment. And then it's impossible, really, again, to set the values without having large values of A lambda of MHS. So this can be done, but you can ask me afterwards. So then my conclusions are the following. So strong interacting particles are restricted to heavier than about 1 TeV, and we are now starting to constrain the region of masses consistent with the MSSM Higgs mass determination, and those searches should be emphasized. There is no clear deviation of Higgs properties with respect to the standard model value, and that approximate alignment may lead to novel signatures in heavy Higgs case that have to be searched for. So electrolytic bounds are gaining strength. The square mass dependence should be taken into account. The SUSY at the weight scale could lead to a solution to the matter problem. Direct matter detection bounds may be avoided, but it's not trivial. G-2 can also be explained. And again, there are interesting new experimental signatures in regions consistent with our matter in G-2. And finally, the corrections to MW may be significant, but only in extreme values of parameters. Thank you.
Okay, thank you. Thank you. This nice talk. So, okay.
Can you tell us a little bit more about the last point that you didn't mention at all?
The NSF?
No, the B anomalies.
Yeah, okay. This was covered by Andreas Krivelin, so I didn't mention anything about the B anomalies. So actually, the B anomalies can be fitted in the case of supersymmetry R-particle variation. Cannot be done without R-particle variation. Because the only diagram that can lead to BS mu is a box diagram including leptons, quarks, and yes. And I did it. I tried. I tried, and then I failed. Well, those are the most important contributions that can lead to an enhancement of visuals with mu to visuals. No, this has been done before. But we can discuss if you want. If you disagree with me, to tell me how, and then we try. I failed.
Yeah. I think even in the R parity violating MSSM, you can't get a perfect fit to B to SLL. But yeah.
That is true. Even choosing the precise coupling that. So if you look at this paper by Almanshofer, where they tried with the R-parity violation is very bizarre than what you need to do to really get to the right values of parity. Very, very difficult. But if you believe that you can do it, you tell me how, because I tried. Very hard.
But my question was another one. If you go back to your slide where you had this Higgs decays to other Higgses, there was this small region which seems to be preferred even.
Sorry, let me go back.
Yes. Stop. There it was. No, one further. No, further. Here, yes. This one here. So since your black region is significantly smaller than the colored one, it seems like this white spot would even be preferred by data, correct?
No. First of all, I presented this diagram only to emphasize that similar searches as the one that have been performed with the case of H2Z8 should Yeah. The gray is the present exclusion region. This is expected. Yeah, there is a small excess in those regions, and they are symmetric. Yeah. Well, you know, unfortunately, this is an old. There used to be a prominent excess that was interesting. That went away.
But Atlas still has a region where MA.
It's above 400.
So Atlas has this region of MA of 610 and M capital H around 290, which they claim to be close to a 3 sigma. That was their largest fluctuation. And that as far as...
Will be there.
well, no, it's the other one.
But I mean they're symmetric in this.
No, but they really distinguish. It's A to Z capital H is what they... And as far as I know, there's no contradiction to that fluctuation.
Is this A to Z H?
A to Z capital H, yeah.
How do they distinguish between one and the other?
We can talk privately on that.
Okay, very good. But in this plot it's pretty symmetric. Yeah. And there seems to be an excess that here or there.
Okay. Is there any other questions? Okay, if not, let's thank Carlos again. Okay, so now the... please.
Which video? First?
First is SUSY-2022, and then afterwards.
So we will move on time tomorrow morning.
Thanks.
So next talk will be given by Steve King. He's going to talk about neutrinos and flavor models. This is the pointer. This is the pointer. And then right, just to...
Okay, so many thanks to the organizers for a great conference and for the nice invitation. Thank you. So I'm going to be talking about neutrinos and the flavor problem from the Planck scale to the electroweak scale. So this is the flavor problem. Okay, some of the particles are missing, but you can guess what they are. And there's a very strong hierarchy in the masses.
Try to speak over the phone.
Okay, can you hear me better? Yeah, okay. Clearly, to understand the charge lepton mass hierarchies, we need to go beyond the standard model picture of Yukawa couplings. And there are three different directions that you can consider based on symmetry, anarchy, or the effective approach. Most likely, it seems to me that Yukawa couplings are some kind of effective couplings, and that they're small due to powers of this ratio phi over lambda, where phi are some scalar field mass insertion. So you have some higher order operator which is generating the Yukawa couplings, and that's leading to the suppression. Now, if you follow that line of argument, then all you know is that this ratio phi over lambda has to be a small parameter in the theory to explain the hierarchies. But it doesn't tell you what the numerator or the denominator is. And the denominator is lambda. That's what I call the flavor scale. And that in principle could be anywhere from the Planck scale right down to the electroweak scale. Now, I'm going to consider two different possibilities. The first is that this scale lambda is up there at the Planck scale, and that's motivated by strings, SUSY and guts, and they're suggesting this high scale theory of flavor. Whereas the B physics, the recent phenomenological hints from B physics that we heard about this morning, they seem to be suggesting a low scale theory of flavor closer to the electroweak scale. Now, turning to the neutrinos, these seem to motivate non-abelian symmetries. So whereas the quark CKM matrix is, you can account for this hierarchical pattern by a U1 Froggatt-Nielsen symmetry. For the neutrinos, if you look at the PM&S matrix, you see that the second column has a kind of threefold symmetry, and the second and third rows have a twofold symmetry. That's the tri-bimaximal mixing pattern. So that kind of threefold permutation symmetry and twofold permutation symmetry, that seems to suggest a non-abelian symmetry. Now, these non-abelian symmetries have been studied quite widely over the recent years. These are some examples, subgroups of SU3, and you see there's all sorts of different possibilities. Now, over the last few years, there's been a lot of interest in modular symmetry as the origin of these flavor symmetries. Now, if we go back to Peter Niller's talk, he mentioned modular symmetry from string theory. So string theory is based on compactified extra dimensions. And if here you see two extra dimensions as a torus. Now, if you cut open the torus with scissors, lay it down flat, you can see that you can describe the torus by this plane here. These are the two dimensions here. And typically you have a twisted torus, so you have a twist angle here. And this torus can be described by two lattice vectors, omega 1 and omega 2. But they're not unique. You can have alternative lattice vectors given by these blue vectors here. And this non-uniqueness gives rise to a symmetry called modular symmetry. And what's relevant is this field tau, which is the ratio of omega 1 over omega 2. That's a hidden sector modulus field. And this modulus is invariant under this transformation, A tau plus B over C tau plus D, where A, B, C, and D are integers and its unit determinant. And this is the modular symmetry. And this modular symmetry can be generated by these two transformations, S and T. So S is tau goes to minus 1 over tau, and T goes to tau plus 1. And these two can generate all possible symmetries. Now, if you impose the further constraint that T to the n equals 1, then you get back to these finite modular groups. The modular symmetry is infinite, but imposing this constraint gives you a finite modular symmetry. So these are the groups that people have been playing with, flavor groups, over the past few years, and they're now they have this modular symmetry origin. So this is a bottom-up approach as compared to what Peter was talking about, which was a top-down approach. And this has been studied for leptons, quarks, and various grand unified theories, SU5 and SO10, over the past few years, and you see there's a lot of gaps in this table. There's not much work on quarks, and nobody's worked on this one, n equals 6. So this is a subject that's still in some sense in its infancy. I'm going to just look at a few examples now. Here's the case of n equals 3, which is A4, and in this case, what you say is that the Yukawa couplings involving twisted states whose modular weights don't add up to 0 are these modular forms, and they form, in this example, they would form a triplet under the A4, and the value of the components depend on the value of the field tau, the modulus field tau, which is parameterized by this Q parameter here, which is e to the 2 pi tau, and this tau is the modulus VEV up here. So for a given choice of modulus VEV, you would generate a particular alignment in the Yukawa couplings. So it only depends on one complex parameter, tau. Now I'm going to introduce some notation. This this Yukawa coupling, which is a triplet, it's an A4 triplet, so I'm going to put a little 3 there in boldface, and there's a 2, which means that this has modular weight 2. So this is an example of a modular form. And okay, now let's do an example of this. You can assign fields, lepton fields, different A4 assignments and different modular weights. And in this example, we're going to introduce a weighton, a new field, which is an A4 singlet, but it carries a non-zero modular weight. And this weighton can get a small vacuum expectation value, about 0.1, let's say, for example, and it can appear in the superpotential, which is modular invariant. So each term in the superpotential has to be a singlet of A4, and it has to have 0 modular weight. So that's compensated by the modular weight of the Yukawa coupling here. And when you expand it out using the Klebsch rules of A4, you end up with a matrix like this. And phi tilde is a small parameter, like we said, and you can see that there's a hierarchy here. So phi to the 4th is very small, phi is not so small, so you generate a hierarchical Yukawa matrix. And this provides a natural explanation of charged quark, well, lepton in this case, but you can also do it for quarks, and it was done for quarks without using some complicated potentials. So this might remind you of Froggatt-Nielsen, but here, this weighton field, let me emphasize, it doesn't break the flavor symmetry. It's a singlet, so it's not a flavon. It's a weighton. So it's very different. Okay, let me turn to another example based on 2 modular groups. So here you can have a modular group in the charged lepton sector and a level 4 modular group in the neutrino sector. You can break them down to the diagonal subgroup S4, and then you have a theory with 2 moduli. So this is a richer structure. And with 2 moduli, you can go over here, and the modulus tau L is which are called phi L over here, is controlling the charged lepton sector. The modulus T nu is controlling the neutrino sector. And S4 has 3 generators, ST and U. If you break S and U but preserve SU, then you end up with this trimaximal 1 form, where the first column of the tri-bimaximal matrix is preserved. And here what we're doing is assigning the value of the modulus field to a particular fixed point in the string theory. And these fixed points give particular alignments. So this one, for example, the SU fixed point gives an alignment 2, -1, -1, which accounts for this first column here. So you can generate interesting structures this way. Okay, another example would be SU5. Guts, again, with S4, here again involving a weighton. This is the driving field here. And you can write down all the Yukawa matrices. I'm just writing down the up-type Yukawa matrix here. Again, same idea. You can see the hierarchies. The up mass is smaller than the charm, which is smaller than the top, and so on. And in the neutrino sector, you can work at particular fixed points and get these interesting alignments for free. You don't have to work very hard to get these alignments. They're just there as fixed points in the theory. And you can get a 0, 1, -1, and this one here, which you would never guess, really, but it's coming out of the theory, 1 + √6, 1 - √6. And you can end up with structures like this, which you can call littlest modular seesaw. It only involves 2 right-handed neutrinos and has particular alignments. And here you can see it's consistent with data. So this is the ratio of MS over MA. These are the 2 parameters here, and the parameter eta. So there's only 3 parameters, MA, MS, and eta. And with these 3 parameters, you can explain all of the neutrino data for this value of phase and this value of MS over MA. And so it seems to work very well. Right, changing gears now. I'm going to talk about the other motivation for flavor, which is the B physics anomalies. So I can be super quick here, because Andy gave a great talk this morning on these anomalies with RK and RD, so you know all about this. There are these deviations. And he also mentioned that the vector leptoquark can explain both RK and RD from these kinds of diagrams here. So there's some motivation for looking at vector leptoquarks. He also mentioned that the vector leptoquark can come from Pati Salam. So here's Pati Salam. You've got SU4 in that direction and SU2 left and SU2 right. So all the quarks and leptons fit into the multiplets of the Pati Salam. And the leptons are basically the fourth color. And this U gauge boson, which lives inside the SU4, takes you from leptons to quarks. So this is the vector leptoquark that's going to be interesting for the anomalies. Now, for the anomalies, this vector leptoquark has to have a TeV scale mass. But it's not allowed, actually, due to k long to mu e. There's this constraint. So by throwing across a U1 gauge boson here, you can change a strange to a mu, which are in the same family, and a down to an electron, which are in the same family. So there's no mixing suppression at all. And this gives you a bound of 1,000 TeV, 1 PeV for the vector leptoquark. And that's the conflict then between the TeV mass and the PeV bound. And this is difficult to reconcile in a UV model, as Andy mentioned. I'm going to talk about one example of this called twin Pati Salam. It's basically two copies of the Pati Salam group. So you have the red Pati Salam here, and you have a blue Pati Salam 1 and Pati Salam 2, and you break them above this high scale, preserving one of the SU4s. This is the critical part. You preserve this SU4 because that's where your U1 gauge boson is going to be living, but you break down the SU2s to the diagonal group and so on. And then at a second stage, at the low scale, around a TeV, you break this to the standard model, SU3 cross SU2 cross U1. So these circles are just the gauge groups. Okay, so this is I should stress that this is an attempt not only to explain RD and RK, but also to account for the origin of quark and lepton masses. So it's an attempt at a full theory of flavor, quark and lepton masses and RD and RK. So not just the anomalies. And in the talk, I'm going to just mention, because of time constraint, a simplified model. I'm going to ignore the first family and ignore the neutrino masses, even though I work very hard on those, but I don't have time to talk about them. They're in the paper if you want to look at them. This is the simplified model. This is Pati Salam 1, this is Pati Salam 2. So we have three families of quarks and leptons transforming under Pati Salam 2, the blue group. And then we're going to add a fourth family, one vector-like family under the first Pati Salam. Okay, and then we have some Higgses here in green, but crucially we don't have the Higgs 1, 2, 2, which would generate standard Yukawa couplings. So there are no Yukawa couplings of the usual kind in this model. Instead, they're going to be generated by mixing with the vector-like fermions. In fact, they're generated by these diagrams. So we have low-scale effective Yukawa couplings generated by anarchical mixing. So this is an example of anarchy, not symmetry. Just remind you, there is no A4 or Zn, or this is just pure gauge groups. There's no additional ad hoc symmetries going into this, so this is anarchy, actually. And in a suitable basis, you have basis freedom, so you can rotate to a basis where this diagram gives a contribution to the third family. This will be the top quark, and bottom the heavy third family contributions. And here you end up with these zeros in the first row and first column. So in the simplified model, the first family is massless, like we said. And we're going to assume a hierarchy in the masses, these vector-like masses. So this is going to be dominating, this M4 psi, which contains the doublets, is dominating over the vector-like masses that contain the singlets. So that's the reason why there's a hierarchy between the third and second family. Okay, now when you break the symmetry to 4, 3, 2, 1, this diagram splits into these 6 diagrams here, and you get so you get a separate Higgs field for the top, which is in red, for the charm, which is in orange, the bottom, which is in yellow, and the strange, which is in green, the tau, which is in blue, and the purple type color will give you the muon. So these are like personal Higgses for each mass with these kind of structures, and you can account for the masses quite well with this. What about the vector leptoquark couplings? Well, they don't couple to quarks and leptons, which seems like a bit of a problem, but you can generate them through mixing. The same type diagrams that generate the quark and lepton masses also generate the mixing, which gives you effective couplings to the vector leptoquark for the third family. So in this model, because this M psi 4 is dominating, and we're in this basis where it only appears in the 3,3 entry, this effectively gives you this 3,3 third family vector leptoquark coupling. So dominantly, the vector leptoquark only couples to the third family. Now, in this model, we know the mass matrices. That's the whole motivation for the model, to do everything. So we know the mass matrices, so you can work in the mass basis simply by going from here to the mass eigenstates, and this gives you these diagrams here, which contribute to RD and RK, suppressed by these small. Well, this is a small mixing angle. It's the ratio of M charm over M top, and that's for RD, and for RK you get suppression of M mu over M tau on the left, because you've got a second family fermion here, and M strange over M bottom on the right. And it turns out that this is actually a bit too small for RD to explain RD. So we have to go beyond this model and consider three vector-like families. You also have many other phenomenological constraints as well. So it turns out with three families you can impose a sort of a gym mechanism as well. So there's a sort of there's a good motivation for three families from flavor changing. So we've been working on this. I have a student, Mario Navarro, and we've been working on this for about eight months now, doing a global analysis of all the data. And I can show you some preliminary results. The paper will be coming soon, but this is just showing you that it could work. So the yellow band is RK. So I'm in the plane of two of these Yukawa couplings. Yukawa coupling third family to fourth family and second family to fifth family. And you see that the yellow band is here. The green band is the region you want to be in for RD and RD star. And then these other lines are various constraints. These are the most constraining processes. You see the most constraining one here is delta of delta MS. This is the BS bar mixing constraint. This is Z prime to tau tau from Atlas, tau to 3 mus. You also get a Z primed and a coloron when you break the SU4, and these are the constraints from Atlas and CMS for this particular benchmark value. So just to show you that it can work. So I'm basically done. Okay, I will need that 5 minutes in a moment for a reason that you'll see. So here's my conclusion, pictorially. To understand the origin of Yukawa couplings and the quark and lepton mass hierarchies, we really need to go beyond this picture of a simple Yukawa coupling, and there's three different ways to go. Effective couplings here. I mean, it seems to me that this coupling should be effective, and the flavor scale could be anywhere from the Planck scale to the electroweak scale, because of hints from B physics tie it at the weak scale, and strings seem to prefer the Planck scale. And what we've studied in this talk is modular symmetry, which provides a bridge to string theory, and those kinds of modular symmetry models seem to be up here at the Planck scale. And we also considered a two-copy Pati-Salam theory, anarchy, actually twin Pati-Salam anarchy, which provides a bridge to phenomenological hints from B physics. And it remains to be seen if either of these has anything to do with nature. Okay, so That's it. Thank you.
Okay, thank you, Steve. Okay, we have some time for questions.
Nice talk, Steve. Have you tried to have a stringy realization of the twin Partisalan model?
We haven't looked at that. We haven't looked at that at all. Yeah.
You haven't tried?
This is just a low energy.
Yes, but you have looked for potential realizations? Because
We have not. We have not yet.
Okay, we can talk. This seems
that could be interesting.
Yeah.
Yeah. Thank you.
I think you can.
Very nice talk and very nice work, Steve. I have a question. If, right-handed neutrinos, can you get a realization of the Saposnikov et al. New MSM here? So as a low-scale right-handed neutrino could play the role of dark matter in some of your symmetries?
We haven't really looked at that. You mean within the framework of the Partisalan?
Yeah, within your framework of the Partisalan.
Yeah, because everything is at a low scale, then you might want to think about that kind of thing. Yeah. So it's not what I was doing, but it's a good question, good point. Yeah, you could think along those lines. Yeah. Yeah.
Okay.
Thank you for the nice talk. So, how can we calculate the weight of modular weight of the weighton? Well, what gives the modular weight of the weighton?
So what I'm doing is basically a bottom-up approach, where I'm just putting in. So this table here, for example, I'm just allowing myself the freedom to assign A4 representations and any modular weights that I want. So this is the bottom-up freedom. What Peter Nilles was talking about was where he had an orbifold string construction, and he was getting these assignments from his top-down construction. So there's two different approaches. Yeah.
So are there many top-down examples with this weighton?
Not so many, yeah. Or with the weighton.
Yeah.
Yeah. I don't know if there's any examples where this weighton is coming out of an orbifold model, but there's no reason why it should not. Yeah. Yeah. That I know. Yeah.
Okay. Another question.
I was wondering if in your twin Partisalan, besides alleviating the anomalies in neutral and charged currents BDKs, you do expect some other observables, observables that will be sensitive.
Yeah, I mean that's a good point. It's a good point. Yeah. So what this graph just shows the most constraining processes. We've actually considered a whole lot of different processes. There's a whole lot of different processes. There's. I mean, it's an excellent question, because the way you're going to test this model is by finding these processes and cataloging them and so on. So for our final paper, we will surely show predictions for different processes. But yes, that's going to be absolutely key to testing this. Yeah, thank you.
Okay, so now there is a little announcement for tomorrow.
So tomorrow we will start a little bit later, which means the bus also will be there at 9 o'clock. So you can sleep a little more, but not too much. You know?
Good news. Good news.
I I also have an announcement about the next SUSY. So
okay.
could
Go
I-
ahead. Yeah.
Just 2 minutes. Just 2 minutes. Just literally 2 minutes. I won't hold you. Okay, so you probably know by now that the next SUSY conference is going to be in Southampton, and I guess some of you don't know where Southampton is. So here it is. It's right on the south coast of England. It's very close to all these major cities. It's very strategically placed to visit all these places. Sorry. Yeah, so it's quite a big university. It has a lot of undergraduates and staff. We have a research active physics department and a healthy number of undergraduates and staff in the physics department. These are some of the people which you may know. We work across whole areas of phenomenology, BSM, lattice, gravity strings. We have our group also includes some mathematicians as well. We've already got a local organising committee. There will be students have been enlisted to this as well. The provisional dates for the SUSY to put in your mental calendar are 17th of July. This is to be confirmed. This is the SUSY. We're going to have a pre-SUSY the week before, but 17th of July for the major conference. Here's a few postcards of Southampton. This is some historic sites here around the city. It's on the coast. It's on the waterfront. It's a working docks. It's a cruise capital of one of the cruise capitals of Europe. So it's a very nice place to walk around. There are lots of good hotels in Southampton. This is one of them. This is right on the water. This is on the waterfront and also by the old town as well. So this is a particularly strategically well placed hotel. But there are others, and there are plenty of nearby attractions. We haven't decided where to go for the excursion yet, but it will be to one of these places, I'm sure. Yeah, and we look forward to welcoming you next year. It wasn't built there, but it sailed from there. Yeah, sailed from there.
So is the venue going to be the Queen Elizabeth? Is the venue of the SUSY?
This is advancing.
Wrong language, sorry, but yours wouldn't finish, I'm sure, right? Yes. I just wanted to make a comment. I felt deja vu. Yogi Bear would say, I felt deja vu all over again. In 1984, I heard John Schwartz give one of those early talks, and he had someone asked about the cosmos or constant problem. He said, nobody knows how to do that, solve that problem. And here we are, going to 2022, it's still very difficult. It's string theory.
Actually, the string theory is the only place where there is a solution for mixes. Nobody has a solution.
Yes, we're still struggling, but yes, yes, exactly. chair here. So you almost start things on time. Yeah, I mean, that's the trick to this. I'm ready when you are. Right, so I'll just go up here and stand next to you.
Okay, so πώς το βρίσκουμε?
This is the correct talk, yes.
This is?
Yes.
Ah, right, okay, so, sorry about that then. Which one? This one?
No. This?
This one. Right, okay.
And you advance, just to be sure, you advance with this, right?
Actually, you have this. So this is a pointer, and you change the...
Can you alternatively use
You
this?
can.
Oh, yeah. You can do it either way.
Yeah,
You can do it either way, sure.
Right,
And you
so-
have a pointer. Good.
It's my pleasure to welcome Professor Allen.
Thank you.
And he's going to talk to us about dark matter waves.
Very good. Okay. I'll watch for the time. Let me begin with some predictions. This is the title, of course. The first is that within the next 5 years, if this theory is correct, a dark matter particle should be seen at one of the xenon-based experiments. That means xenon NT, LZ, or Panda-X. The mass, all the parameters in this theory are well defined. There are 0 undefined parameters. And so therefore, there's a clean prediction that the mass of the dark matter particle will be 72 GeV, plus or minus 1 GeV. We estimate this cross-section is slightly below 10 to the minus 47 square centimeters. And according to the estimates of xenon NT and LZ, the sensitivity in early experiments should extend down to about 1.4 times 10 to the minus 48. So finally, this particle should be within reach of the dark matter direct detection experiments. There's a second prediction on a much longer time scale. This involves at least the high luminosity LHC and possibly other experiments. It should be observed by the high luminosity LHC in about 12 to 15 years, if that experiment can reach about 3,000 inverse femtoborns. And finally, there's a post-diction that this particle may have already been detected in the gamma rays emitted, they're observed by Fermi-Lat, and possibly in the antiprotons observed by EMS. So here's a reminder of the well-known plots of the sensitivities of previous experiments. This is a WIMP, again with a mass of 72 GeV. So we look for this cross-section that we're estimating of below 10 to the minus 47. With a mass of 72, we're here, and that should be within the range of LZ. And of course, it's well below the sensitivities of the previous experiments, so it's consistent with those experiments. It's also consistent, as I'll mention in a moment, with the various other experiments for indirect detection and collide detection. So just to emphasize with a bit of repetition, because these points are so important, the mass isn't just of the order of 72 GeV. It's almost exactly 72 GeV. We therefore have small cross-sections for annihilation, scattering, and creation, and that's why it's consistent with the previous experiments. But that cross-section is still sufficiently large to enable detection in these experiments that are coming up. And certainly, if it should be well within the range of Darwin, which would be the last of the projected xenon NT experiments. These are our two most recent papers in which we give the arguments that lead to these conclusions. The difference between this candidate and previous candidates is that it involves two component fields, bosonic fields that are put together in the theory that's given here. So this follows from a fundamental theory. I'll advise you not to look at the fundamental theory unless you're able to dedicate a lot of attention to details of the mathematics. But you can just look at the phenomenology as outlined in those papers that I just referenced. Here we treat the model as just a phenomenological model. But what comes out is that one has to combine two component bosonic fields, and here we're combining a two-component bosonic field with the charge conjugate field, so it's a Majorana-like bosonic field. And because we have the field combined with this charge conjugate, the first-order couplings cancel. We have only second-order couplings, and that's the reason why we have these small cross-sections for all the various experiments. Here's the final result. We eventually have a one-component real scalar boson field. We have called these in our papers Higgson fields. The Higgs boson, I'll come back to in a few minutes, that's another field that emerges. This is an extended Higgs sector, extended in this way. And the couplings are well defined. We have only these gauge couplings to the Z and W bosons. So when this particle is finally discovered, let's remember that we have a prediction here. As soon as these xenon-based experiments do detect the dark matter particle, there will inevitably be a few dozen postdictions involving fitting the parameters to the data. Here we have 0 parameters to fit. They're all well defined. But I'll mention that there are various other, for example, extended Higgs sector models that have been proposed. Here's one example. This is something called the inert doublet model. It's very popular. In this model, one has this structure for the combined fields. And so it's a similar model, but the phenomenology is very different. So what will discriminate between the present theory and these other extended Higgs sector models or other models, including fermions, for example, is the phenomenology. So here are many processes that occur in the extended, in the inert doublet model that do not occur in our theory. This, and we have had a series of papers, read only these last two, which are the final version of the theory. The final version is fully Lorentz invariant and it's consistent with all experiments and all of theory in every sense. Again, we've called these particles Higgsons, represented by small h, to distinguish them from Higgs bosons, represented by capital H, the Higgs xenos. I should mention at this point that this talk does belong in a conference on supersymmetry because the theory, the fundamental theory, cannot even be formulated without supersymmetry, as well as an SON theory to unify the coupling constants. So there is supersymmetry. There presumably is a supersymmetric partner that's also stable, a neutralino, for example. The picture here is that this is the dominant dark matter component, but something like the neutralino can be a subdominant component. The mass is pinned down by fitting basically to the relic abundance. The relic abundance tells us that we must have that mass. Because if the mass were higher, we would have too rapid annihilation. If the mass were lower, the annihilation would not be sufficiently rapid, and therefore we have a process that has to involve a mass below the mass of the W boson, and in fact, the correct mass is about 72 GeV. Let's remind ourselves of the experiments for indirect detection that are relevant to indirect detection. We have Fermi-Lat observing gamma rays, for example, from the galactic center. We have the MS experiment observing cosmic rays, for example, antiprotons that have been attributed in various analyses to dark matter particles annihilating. And then we finally have Planck that places constraints on the dark matter particles. Here are quotations from two representative discussions or analyses of the data from Fermi-Lat for the gamma rays. And the analyses favor a dark matter, annihilation of a dark matter candidate, which has a mass range like this that includes our mass of 72 GeV. The anti-protons, these are the two representative analyses for the antiprotons observed by AMS. And again, they're consistent with both our cross-sections and with our mass of 72 GeV. So there is good evidence already from the gamma rays observed by Fermi-Lat, and possibly a little less convincing for the antiprotons observed by AMS, that these particles have already been observed through indirect detection. At one point, one might have thought that the dark matter particle had a higher mass. These are the positrons observed by AMS. They would indicate a higher mass particle, but this interpretation has now been ruled out. For example, by the data from Planck, that would correspond to this region that's excluded by the Planck data, whereas our candidate is in this region, which is comfortably in agreement with the Planck data. The best hope for direct detection, for example, in these xenon-based experiments, and also in other experiments like SuperCDMS, is via these Feynman diagrams involving a second-order coupling loop diagrams involving the Z and the W. And the cross-section we estimate to be slightly below 10 to the minus 47 square centimeters. And again, just to remind you, that places us just in the right place to be consistent with the previous experiments and to be observable by LZ, xenon, NT, and so on. The best prospect for collider detection appears to be vector boson fusion like this, and the signature will be greater than of the order of 150 GeV of missing energy together with 2 jets. The results from these quarks. The theory contains the Higgs, for example, along with this new particle, which we call the Higgs-on, and they're both amplitude modes. If these two component fields are put together one way, the amplitude mode is a Higgs boson. That is analogous to the Higgs or amplitude modes that are observed, that were theoretically predicted and then observed in superconductors in condensed matter physics. The other way of doing things is like this. Here we're joining two fields that have opposite spins. Here we're joining a field with its charge conjugate, and here this is the other sort of field that can be formulated in the theory. So we get the Higgs boson back, and we also get these new Higgs-like particles. Let's remind ourselves that there have been a lot of surprises through the years. There are three kinds of particles in the standard model. The spin-1/2 particles are leptons and quarks. Originates in 1897. It's very unlikely that J.J. Thomson could imagine the richness of phenomena that we observe in quantum electrodynamics and so on based on the electron. It's very unlikely that J.J. Thomson saw the electron as being described by a 4-component Dirac field. In 1905, the second sort of particle was introduced when Einstein essentially gave us the photon. Those are our spin-1 gauge bosons. Again, it's very likely that Einstein in 1905 envisioned the richness of quantum electrodynamics. And now we have the third type of particle in the standard model, a spin-0 boson, discovered 10 years ago, almost exactly 10 years ago, on July the 4th. So surprises may yet lie ahead, and that's why we think this extended Higgs sector of ours is a very natural extension of what's already been observed. So again, just to summarize, we've proposed this dark matter candidate with some very favorable features. They're strong, even though it's not definitive evidence of indirect detection by these satellite experiments. The collider detection should be possible within the next 12 to 15 years, and direct detection should be possible within the next 2 to 5 years by these xenon-based experiments. And I'm not sure exactly how much time I have left. 5 minutes? I don't even need 5 minutes, actually. This is the last slide. I just want to emphasize that we have many different reasons for believing that this is an ideal dark matter candidate. And I hope I've convinced you that at least it has good prospects for being discovered. And I'll quit early, since we started a little late anyway. And you can just read this slide if you want to. Thank you very much. And you'll have to pardon me, my hearing is not what it used to be, so you have to speak loudly or through the microphone. I think we were instructed earlier to address a particular part of the microphone. Yes?
So where does this extremely precise number where does this extremely precise number of 72 GeV come from? Did you perform some...
72 GeV?
Yeah.
Yes. Again, I can just go back to the slide, but I can just say it very simply. It's just if the mass is above the mass of the W boson, there's extremely rapid annihilation into real W bosons and real Z naughts. If the mass is well below the mass of a W boson, there's very slow annihilation in the early universe. So in the first case, we get too rapid annihilation, too little relic abundance for dark matter. In the second case, we get too little annihilation, way overabundance for dark matter. And so we do a calculation with some standard software called micromegas, and when we do the calculation, we find that for 72 GeV, we get the right relic abundance or the right cross-section. This is the cross-section, for example, given to us by Steinman and collaborators many years ago for dark matter annihilation.
Yeah, thanks.
Okay, so the next speaker is Giorgio Busson. Did I say this?
Yeah.
And he's going to talk to us about the capture of dark matter.
Thank you. So first of all, I would like to thank the organizers for giving me the opportunity to speak at this conference. So today I would like to present you the results of a series of works that I've been doing together with my collaborators about capture of dark matter in compact stars, and in particular in neutron stars. So this is the outline of my presentation. I will start by motivating why to use compact stars to try to place bounds on dark matter. After that, I will briefly review what we have been doing in our works and our results. So you are all familiar with direct detection. In direct detection, we usually consider two different kinds of interactions, the spin-dependent ones and the spin-independent ones. But the whole picture is much broader. There are many different kinds of operators, many different kinds of interactions, and constraint depends strongly on the interaction type and on the target that you are using. In particular, in direct detection, we have no relativistic kinematics of the scattering, and therefore some operators are called momentum or velocity suppressed. The recoil energy is small. And as experimental detectors have some recoil energy thresholds, this limits their sensitivity to small dark matter masses that will give us very small recoil energy. So if we move to consider dark matter capture in stars, and in particular in the sun, what happens is that the dark matter that is traveling across the sun can sometimes scatter on some nuclei inside the sun, and if it's losing enough energy, can become gravitationally bound to the sun. And with subsequent scatterings, it can accumulate in the center. Now, if dark matter can annihilate, of all the annihilation products, only neutrino could escape from the sun, and they can be observed on Earth. And through the observation of such neutrinos, one can place constraints on the annihilation rate. And as at equilibrium, the annihilation rate is equal to the capture rate. One can, in practice, probe the same parameter space as direct detection. So this is a complementary search to direct detection. So what happens is that for spin-independent interaction, direct detection usually is able to place stronger constraints, while for spin-dependent interaction, usually dark matter in the sun wins due to the larger mass of your detector, the sun. There are also some other ways to infer indirectly the presence of dark matter inside the sun, for example, by looking at modified energy transport. Now, why to look for dark matter capture in neutron stars? So neutron stars are very dense, and very large density means that they are able to give a very efficient capture. For example, the whole dark matter flux that is going across the star can be captured for cross-sections that are as small as 10 to the negative 45 centimeters squared. So what are the possible signals that we can try to observe by looking at neutron stars. So we can look for neutron star collapse to a black hole, but this is more likely to happen for bosonic dark matter. The presence of dark matter inside the neutron stars would stiffen the equation of state and can increase the tidal deformability that can be observed during mergers. So this is a gravitational wave kind of observation. But what we will focus on this talk are the last two bullet points that are the so-called kinetic heating and the kinetic pulse annihilation heating. So if we look at the temperature evolution of a neutron stars have no known large heating sources. This means that they are thought to lose energy indefinitely by neutrino and photon emission. In the absence of other heating sources, one expects the temperature to drop to 1,000 Kelvin after 10 megayears and to 100 Kelvin after 1 gigayear. Now, if the neutron stars can capture dark matter, for every capture event, a small amount of energy would be deposited into the star that is roughly of the same order of the dark matter mass. And this would act as a heating mechanism. And therefore, there would be some equilibrium temperature that is 1,700 Kelvin if the whole dark matter flux can be captured. And if on top of that dark matter can annihilate, the equilibrium temperature is raised to 2,400 Kelvin. Now, to calculate the equilibrium temperature, basically what we need is the so-called geometric capture rate. That is the capture rate that you obtain if the whole dark matter flux going across the star is captured. And we multiply this by the average energy transfer that is of the order of dark matter mass. And we set this to be equal to the energy loss due to photon emission. And we obtain the equilibrium temperature through equation 2. Now, what are the advantages of using neutron stars comparing to the other to dark matter in the sun, for example? First of all, we have a high capture probability. Dark matter particles are accelerated at the speed of light, very close to the speed of light. That means that we wash away any non-relativistic kinematic suppression. We have sensitivity to very small cross-sections of the order of 10 to the negative 45 centimeters squared. That is in the same ballpark as stereo detection. There is no threshold recoil energies. And we have a similar sensitivity for all kinds of interactions, spin-dependent, spin-independent, momentum suppressed. So how can we place bounds using these observations? Well, we need to observe a neutron star with a temperature T that is smaller than the equilibrium temperature that we quoted before. And if we are able to do that, we can use equation 4 to constrain the dark matter interaction cross-section. And to use equation 4, what we need is the equilibrium temperature that we already found and the threshold cross-section. This threshold cross-section is what we have been trying to calculate with very good accuracy in our works. So before going to our works, let me make a couple of examples where neutron stars are very powerful. The first example is if you consider inelastic dark matter, so dark matter where you have two particle states and elastic scattering is not possible, and you have some small mass splittings in between the two states. Now, if you look at the plot on the right, you can see that the mass splittings that we are able to probe using neutron stars are several orders of magnitude larger than what you can do in the sun or on the Earth. This is at least 3 orders of magnitude more, but it can be even 5 or 6, depending on the dark matter mass. Second example is the case of the so-called momentum suppressed operators. Here we see the constraints that you would get from the observation of a cold neutron star and from direct detection for various operators. And as you can see, the constraints from the operators that are the purple and blue dashed lines, vary a lot depending on the operator, and this is due to the fact that some operators have this non-relativistic kinematic suppression and some don't have this suppression. And instead, in the case of the constraints coming from neutron stars, the bounds are all very similar and of the same order of magnitude. And they're usually stronger as well. So what are the detection prospects? We hope to be able to observe some of these cold neutron stars using the James Webb Telescope. It was launched on December last year, and it's operating exactly in the range of wavelengths in the infrared. That is the range of wavelengths that we need to observe a neutron star in the desired range of temperatures. These are some infographics about the James Webb Telescope and how it compares to Hubble. So detection prospects. Here we show the maximum distance for which we can be able to resolve a neutron star as a function of the temperature for some observation times. And on the bottom, the average number of expected neutron stars that can be observed. And as you can see, even for the more conservative observation time, we hope that we will be able to observe at least a few of these cold neutron stars. Just as a reference, at the moment, the coldest observed neutron star has a temperature of the order of 42,000 Kelvin. So what we did was to start from the capture rate formalism for dark matter capture in neutron stars, in the sun, sorry, developed by Gould in the 80s, and we tried to adapt this formalism to the case of neutron stars and also white dwarfs. And to do that, we had to undergo a long series of modifications, including switching from Newtonian gravity to general relativity. We need to pick up some equational state for the neutron star to describe its interior. We had to go from non-relativistic to relativistic kinematics. We need to change the targets from atomic nuclei to baryon and lepton targets. And this is a series of consequences, as we will see. We need to switch from a Maxwell-Boltzmann distribution for the targets to a Fermi-Dirac. But there are also some simplifications when we go to consider neutron stars. For example, the capture probability can be approximated to be equal to 1, unless the dark matter mass is so large that one needs to account for multiple scattering. And even in the case of multiple scattering, one can usually treat this analytically or semi-analytically, while in the sun, one usually needs a Monte Carlo approach. Two important things that we have discovered during our works is that, first of all, likely in the case of the sun, where one needs to include form factor for atomic nuclei, one needs to include form factors also in the case of baryon targets, because baryons are composite particles, so they have a structure, and you are actually able to probe this structure because the scatterings are very energetic. And the second important thing is that inside a neutron star, due to the fact that you have a large density and a large QCD background field, what happens is that in practice, this background field acts as a Higgs field and is modifying the mass of your target. So you need to use density-dependent target mass for your hadrons. So let's go to the results. First of all, I'd like to show you the importance of using a fully relativistic treatment. So here we have the constraints on the operator scale for several targets, and we want to concentrate on the results for electrons, that is the solid blue line, using relativistic treatment, and the dotted line without using a fully relativistic treatment. So as you can see, these two results are completely different, and they differ by several orders of magnitude, and the cross-section scales with lambda to the 4. So that would be amplified if you would plot the relative cross-sections. So what we did, we calculated the capture rates for a typical neutron star for these targets, considering all possible dimension 6 effective field theory operators. And from this, we have calculated the threshold cross-sections, and we plot them here, comparing them to direct detection exclusion regions in the usual direct detection parameter space. So these are the light blue and the purple line bands, the threshold cross-sections. So as you can see, these threshold cross-sections are more constraining than all current and also of the future direct detection experiments, and they're also able to probe some regions that are below the neutrino background. Now, switching to baryon targets, so basically neutrons and protons, in this first slide, we want to highlight the importance of considering the form factors and the mass, density-dependent mass. And this is shown in these plots where we calculate the capture rates with and without these effects. And we plot the ratios on the bottom of these panels. And as you can see, these are in log scales. But not accounting for these effects, one can get several orders of magnitude of difference in the relative result. And this will translate also in the relative threshold cross-section. In this other slide, we consider a heavier neutron star. And in this case, we are considering, so in this heavy neutron star, we can also have on top of neutrons and protons, also some exotic hadrons as a targets. And here we on the bottom of the panels, we plot the fraction for which each target contributes to the total capture rate. And we can see that in the case of some operators and for some mass range, the exotic baryons can actually dominate the total capture rate. In this plot, once again, we want to highlight the importance of those two effects, and we show how the threshold cross-section is changing by not including those two effects, but to including those effects. So we lose basically more than an order of magnitude in the threshold cross-section. And so these are the final threshold cross-section plots for hadronic targets. On the top, we have a spin-independent interaction, and on the bottom, we have spin-dependent interaction. Once again, we compare them with direct detection constraints that are basically these regions here. And you can see that, especially in the case of spin-dependent interactions, the exclusion bounds that one can potentially get from the observation of a cold neutron star are much, much stronger than any current, or also even future direct detection experiment. And once again, they're able to probe regions of the parameter space that are well below the neutrino floor. So coming to the summary, I hope that I've shown you that neutron stars are a nice cosmic laboratory to probe dark matter scattering interactions, where we have a completely different kinematics comparing to direct detection experiments, but also dark matter capture in the sun. Thanks to the fact that we have scattering at very high energy, we wash away any momentum suppression, and also we are able to have a higher reach in the case of inelastic dark matter. We are able to probe a very large mass range. In fact, if you notice in the various plots, we consider masses that go from the keV to the 10 to the 6 GeV or more. We are sensitive to all kinds of interactions, and we have similar sensitivities going from one kind of interaction to the other, including, as already said, the momentum suppressed operators. At the moment, the coldest neutron star has an observed temperature of 40,000 Kelvin, but there are good prospects for the observation of a cold neutron star below 2,000 Kelvin in the coming decade. Thanks for your attention.
Thank you for the talk. I'm not sure if I understand when you show. So when you show those contours for each of the constraints, there is a certain thickness with a shaded area. What does this?
Which slide?
Like those blue, like all those slides actually, the blue green lines. What is this shaded green and blue areas? Why some regions are larger than others, for instance?
So this shaded green area here.
Yeah.
So this is in practice the uncertainty that we get because we consider several possible masses of neutron stars going from 1 solar mass up to the maximum that is around 1.9 solar masses. So depending on the neutron star mass, you get a different threshold cross-section, and so the result can vary a little in the plane. That's the origin of the band. And the yellow background is the neutrino floor, and these other excluded regions are from direct detection.
Okay. And also, I remember there was a couple of years ago this paper from Thomas Ambi and Garani, which is doing similar kind of constraints. Is it are you competing with those constraints, or is it the exact same?
It's the same thing.
Okay.
It's the same. I mean, it's our approach, but it's the same. I mean,
more general.
Yeah, it's the same observable. Yeah.
Hi, thanks for the talk. If I know and understand well, there is a threshold temperature that of neutron stars that this sort of dark matter models are ruled out, correct? You mentioned this. I want to ask if this temperature is the 2000 Kelvin that you mentioned.
Yeah. So what was the question? Sorry.
The question is, if a neutron star is observed with temperature less than, I don't know, about 2000 Kelvin, I don't know the numbers. This means that this sort of dark matter models are ruled out?
So if you are not able to observe a neutron star whose temperature is below these threshold temperatures, you cannot say anything, okay? If you're able to observe a neutron star whose temperature is below these threshold temperatures, basically what you can say that your cross-section is such that you are not able to have a maximal capture, so it has to be smaller than the threshold cross-section that I was showing you in the plots. So that means that if you are able to observe a neutron star that has a temperature below the 2000 Kelvin or whatever it is, you can say that the cross-section lies below this threshold cross-section shown in these plots.
Or equivalently, these models are ruled out with such a big cross-section.
Yeah, basically you can rule out all the area above these lines.
Okay, thanks. Yeah. Thanks a lot.
Thank you very much. Thank you for the organizer to give me this opportunity to talk here. So how do I use the... Okay. Yeah, so it's a great pleasure to present this work here that I've been doing in collaboration with my collaborators in the US, Keith Dineth, Fei Huang, Dujin Kim, Brooks Thomas, and Tim Tate. So that led to a paper back in November, and hopefully will lead soon to 2 other additional studies which are unpublished, so I will not be able to talk too much about it, but that's basically a lot of future directions for this kind of a topic, which is, as you will see, a very interesting curiosity about how the cosmological history of our universe may have been affected in the past by the presence of a very non-minimal dark sector. So let me start by just mentioning that when we look back in the history of our universe, basically the main observation that we have is the cosmic microwave background, which is the oldest picture that we can have about the primordial universe, because we could not see anything before that. And because we are humble human beings, we can only have access to a fraction of what the history of our universe was. This is the allegory of the cave. We only see a picture of what has happened in the early universe, and because we are physicists, we try to interpret this picture and try to guess what is the theory which is behind the observation of the CMB spectrum, and what is the model that we can come up with to explain what we actually observe. So this is us here watching at the CMB, but it could be that the lambda CDM model, which is the best tool that we came up with in order to describe cosmology, may actually just be the surface of a much more complicated nature. And so I'll try to study here how much different the history of the early universe could be as compared to the lambda CDM model. So that's what I call here the lambda CDM ideology, and I don't want to offend anyone, but this is basically the very simplistic vision that we have about the history of our universe. Basically that at early time, the energy density was quite constant. That's what this expansion, accelerated expansion of the universe called cosmic inflation. And after that, the universe is reheated, and this is the hot thermal, hot Big Bang phase of our universe, which is dominated by radiation. Radiation is diluted by the expansion to the power a to the minus 4, because not only the volume is diluted, but also the energy of the particles which are in the thermal bath gets redshifted. Whereas matter is diluted only by volume expansion because it's cold, and therefore scales with a to the minus 3. So here I plot things in a logarithmic scale as a function of a, and as you can see, radiation at some point gets dominated by matter because matter is diluted much less fast. And finally, dark energy is what we observe today, may have come quite late in the history of the universe. So this is the picture that everybody has in mind when describing primordial cosmology from the time of inflation to present time. And it's a pretty nice picture. It helps a lot understanding the data, but it, of course, leads to a lot of question marks. First, we really don't know what the inflationary phase of our universe history is. There are plenty of theories, very few observables, so of course we can come up with a lot of models, but this is still a big question mark. We don't know how matter or dark matter has been produced in the early universe, and we don't know the nature of dark energy, and also we don't know how it arose in the early universe. So that's a lot of question marks behind this very nice picture. And it's very important for us as cosmologists to try to understand what has happened before this very simplistic description of the universe today. So in particular, one feature of this history is that the universe, as we think about it, is never dominated, is always dominated by one species or the other. As I told you, the universe was either dominated by a vacuum energy, or matter, or radiation, and there could be phases where one or the other dominates, but the time where they kind of cross each other is very localized in time. So matter-radiation equality is a very specific moment in the history of the universe. Here I draw an early matter domination period, which could correspond to the oscillation of the inflaton, for instance, or something else. That's why I add this early matter domination period. So the question is whether, is it really true that the universe always has to kind of like fall either towards matter or radiation? And that's why I will try to discuss this cosmological stasis idea, the idea that maybe the universe was not necessarily falling for one or the other, but maybe actually standing in between. So as I said, nature may be much more complex than what than the lambda CDM model describes. And there are plenty of studies on which consider the possibility that weird stuff happened in the early universe. So this is one example, for instance. If a so-called moduli is long-lived in the early universe and for some reason gets produced because, I don't know, because the field starts oscillating, for instance, and decays very late, then typically that would lead to an early matter domination era. And you can see here how the radiation bath is reheated by the decay of this extra particle, which was at some point dominating the early universe energy density. But this is also a very simplistic picture. There are plenty of theories which predict the existence of many particles which may be decoupled from the standard model and therefore being quite long-lived in the early universe. So it could be that UV theories may actually lead to a much more complicated story. So what if, instead of having one moduli in the early universe, you actually had a bunch of particles which tried to dominate the energy density and came up to reheat the universe quite late? I mean, quite late, quite early as compared to nowadays, but at different times along the universe history. So that's the big question I want to ask in this talk, okay? So what would happen in that case? Typically, and this is here basically the same drawing, but plotted in terms of relative abundance instead of total energy density. So omega is the ratio between the energy density and the total energy density in the universe. And typically what those long-lived states would do is that if they are ever produced in the early universe, what they would try to do is they would try to dominate over radiation because they are diluted less fast than radiation. So they would try to dominate, and at some point, of course, if they are metastable, they would start decaying. So their relative abundance would look like something which increases and then decreases with an exponential rate. And the location of the peak would depend on their lifetime. And of course, the height of the peak will also depend on how much they have been produced in the early universe in the first place. So there is a non-trivial kind of correlation between like the different energy densities, the different decay width, which give you different rates of decay and different location of the peak. So now the question is, what is the total matter sector, how the total matter sector evolves in this kind of context? Naively, you could say, okay, if like along the spectrum, if those states are more and more long-lived, then they would start dominating more and more the energy density of the universe. So this total contribution to the matter relative abundance would increase with time. Or it could be that the heaviest state were the one which were able to kind of like dominate the energy density for a while in decay, but maybe the lightest state are actually quite short-lived, and then they reheat more and more, and therefore the total abundance may actually decrease. So that's the question mark, and that's what I want to address in this talk. So let's take a model. Let's assume that you have a tower of states like that, a non-minimal UV sector, which of course has to end at some point, and you cannot produce an infinite amount of states in the early universe with infinite masses, so you have to stop this somewhere. And each of them would contribute to the matter sector of the universe. So and we assume that there is, for simplicity, we assume that there is only matter and radiation, and that those states decay directly into photons, so that we don't have to care about the masses of those particles. But that's a strong assumption, and of course that could be modified in a real particle physics model. The system is relatively simple, and this is a set of Boltzmann equations and Friedmann equations combined together with basically decay terms here and the redshift of each of the species, and those decays source the evolution of radiation. So that's the system of equations that we study, and then the evolution of the total matter sector relative abundance can be extracted from those in order to derive the dynamics of this omega m. And that has this form where you see here there is a collective contribution from the decay of the different states in the tower. Of course, this has to start somewhere and to end somewhere. The tower is finite, so it starts when the heaviest state starts decaying, and it ends when the lightest state decays. And after that and before that, of course, nothing happens. But this is a parameter of the model. And then we have to parameterize our ignorance about what this UV sector is made of. So we take benchmark values for the values of those towers, of this mass spectrum in particular. So we consider a mass with an index L, which goes like to L at a certain power, delta. And delta is a parameter that we choose arbitrarily, but in principle, in a real particle physics model, you should be able to tell what this spectrum is. Okay, this insect is starting again. And then, of course, if we expect a certain regularity in the mass spectrum, then we expect that there will be also a certain regularity in the lifetimes of those particles, because if I ask you how does the lifetime of a particle scale or the decay width scales with the mass, naively you would say probably it's like linear with the mass. So it would go like the mass to a certain power, and there may be some phase space suppression factor, but let's ignore them, which is quite a fair assumption for a large part of the tower of the spectrum, as long as you neglect the masses of the particles into which those particles decay. And for the abundances, we also expect that the initial abundances of those particles will scale with a certain power of the mass. This is a strong assumption, but this is all what we can do at this stage, unless we really specify how those particles were produced in the early universe. But you can have in mind something like the inflaton decay, for instance. The inflaton would produce all those particles, maybe with certain number densities. If they produce them democratically, then the energy density will scale linearly with the mass, so this parameter alpha would be equal to 1. So, I mean, you can have in mind a certain amount of models which would give you certain scaling relations for the initial abundances. So it's not such a crazy idea. But of course, there are certain free parameters that are introduced here, the mass of the zero mode in the spectrum, the lifetime of the zero mode, the energy density of the zero mode. So in principle, one has to put parameters there, so which you may think like, okay, you may think that I'm introducing a lot of ingredients here, but as you will see, the interesting thing here is that the dynamics of the system that I just described is not so much given by a lot of those ingredients. What matters really are the scaling exponents, how those things scale with the masses. And I actually jump right away to the results before I explain you why they are what they are. Those plots here, it's just the same plot with logarithmic or linear scale, represent the different relative abundance of all the species. Okay, and here I choose a certain number of states, 300 states, and I choose certain values of the scaling exponents that I consider could be realistic values. And I put this in the code, and I solve Boltzmann equations. And this is what I obtain. Each of the state tries to dominate. Sorry, I'm trying to not vibrate too much. Each of the states try to dominate because matter dominates over radiation and decays. Okay. And as you can see, what's very interesting is that the total matter sector, the total matter relative abundance, converges to a constant for a while before, of course, the torus stops decaying, and therefore this regime ends. And if you play with parameters and you say, okay, now maybe I just chose a very specific, I mean, that's maybe a very specific choice of parameters, and if I take another one that will not be that way anymore, well, you realize that for different scaling relations, you will actually have the same kind of regime happening, but for different duration and at a different value of the relative abundance omega m, which is very interesting. And this is what we called cosmological stasis, because now we have a constant omega m, which is the sum of all those different individual contributions. And this is not something that one would expect naively unless thinking of a very, very fine-tuned situation. Now, is there any fine-tuning in there? Because you may think that I actually tuned my initial conditions in such a way that I managed to have those regimes happening for different choices of parameters, but I did not. We actually did not expect this to happen in our simulations because we were studying something else, and we saw that this was happening, and we tried to understand why. So let's try to understand it. I derived this equation for the evolution of omega m, and we may wonder how can you actually have this variation to be 0, and that leads you to this equation, which is quite difficult to interpret. And you may then think, okay, what's a necessary condition for it to happen? Let's assume that omega m is a constant. Let's see how h evolves, and let's see how the individual contributions evolve with time. You can also do that, and you come up with certain conditions. The total sum has to be a constant, but the sum of gamma L omega L has to be inversely proportional to time, which also doesn't really tell you anything, because I mean, it's pretty hard to know how this thing would scale with time. So what you need to do is to actually put the particle physics model in there and to see what actually happened for the when you perform those sums, which you can do when you start having those formulas. So if you do it and you take the limit where the tower is sufficiently large so that you have a sort of continuum limit in your spectrum, then you actually arrive to a condition which looks like this. So if you take the ratio of those two conditions, you arrive to this formula here, which is roughly inversely proportional to time. And if you say, okay, now I want this equals what you actually get from this ratio here, that gives you the value of this omega m bar, which is the limit of this constant omega m that should be reached. Is that okay? Is that right? Well, those values are plotted here. Those dotted lines predict exactly what's actually happening in the numerical simulation. So that seems to be right. But this is a necessary condition, and I didn't really demonstrate at that point that the system should actually go there. That's just, if it goes to such a constant regime, that's where it should be. But actually, one can demonstrate that, that this regime is an attractor solution. It is easy to solve the Friedmann equations for Hubble, introducing this average value of this total omega m. And one can reduce the system to a two-dimensional differential system for omega m and for its average value, and realize that in this system, the point where omega m equals omega m bar, which I derived earlier, is actually an equilibrium. And if you want to study the stability of this equilibrium, then you can look at the Jacobian of the system and derive its eigenvalues. And what you realize is that those eigenvalues are negative only if omega m bar, this thing that we can compute from the scaling exponents, is between 0 and 1, which means that basically if you use your parameters to compute this omega m bar and find something which is between 0 and 1, which is a physical situation, then your system is, your equilibrium is stable. Now the question whether it's a global attractor or not, this proves that it's a local attractor. But if you want to prove that mathematically that it's global, then you need to do a little bit extra math, so which we didn't do. But numerically, we did solve the system for various initial conditions, and we proved that it is actually a global attractor. So you can start with how much radiation energy density you want in the first place. The system, as long as the tower is long enough to reach it, the system is attracted to this regime of cosmological stasis. And I think I have to rush now, so I will skip how this affects the history of cosmology, but of course you can understand that if such a regime happened where matter and radiation track each other, that can affect cosmology quite a lot. And that can affect a lot of models of particle physics in the context of cosmology. As soon as you start producing particles out of equilibrium, you need to know what's the dynamic of the expansion, and if such a regime exists, that will affect your prediction a lot. Now, if you're not a great fan of towers of particles, and maybe Kaluza-Klein towers of theories that are inspired by extra dimension, we're actually working right now on other models to realize stasis. And in particular, I will mention one of them. The evaporation of pyramidal black holes is another way to reheat the universe at different times in the universe history if you have an extended distribution of pyramidal black holes. So this is a different study with my collaborators in Durham, Jessica Turner, Juber Perez-Gonzalez, and Andrew Chick, where we studied the evaporation of extended distribution of black holes. We can see that the equation of state of the universe during the evaporation may vary quite a lot during the evaporation process. And so this is an example with a Gaussian distribution, but we are actually working out now the evaporation of other distribution, and we see that we can also have a stasis, cosmological stasis arising from just a situation where pyramidal black holes evaporate. And I will let you hear with the conclusion because I think I said most of it already. Thank you very much.
Right, so this stasis refers to omega m only, right? Or refers only to matter, right? Or also refers to radiation and other components of your omega. So the total omega should scale properly. You just looked at a particular component, I would say.
Right, so here it's just a transfer of energy between matter and radiation. And definitely the dynamics of the system is very dependent on that here. But we are working out other situations where a transfer of energy between dark energy and matter or dark energy and radiation could actually lead to a similar situation. So I can't say more about it right now because this is under study, but this is something that we are working out, and we already have examples where that works as well. It's just a different dynamics.
Okay, I understand. Yeah.
Thank you.
Classified information.
A little bit.
Yeah, there are plenty of questions.
Thank you. What can you say about this global attractor? I mean, do you know the time scales or exponents or is the general behavior you have? All this has been analyzed, or you have just a qualitative view of what the way it works?
So yeah, very good question. So definitely here I have only studied the dynamics of, and I have never showed you any numbers about what's the value of the temperature, what's the value of the masses, what's the value of the mass shift in the spectrum. The interesting thing when you study that in a completely general setup is that you realize that this value of omega m bar is not depending at all on the numbers here in terms of masses and energy scales. In full reality, and we are also working out a proper example of cosmology where the universe would be reheated through this kind of mechanism, you have to be extremely careful because the temperature of the universe is rising, while the value of the temperature may actually reach the value of the masses of the particles which are decaying, or the particles which are out of equilibrium may start thermalizing. So you have a whole bunch of cosmological constraints that you have to satisfy. You also don't want to have too many particles decaying during BBN. So if you can do it, but it's just that you have to be careful and apply all the cosmological constraints to have a viable scenario, but it's possible. Thank you.
So maybe I missed this point, but you mentioned, for example, dark matter. How this will be different from just a matter domination?
So
because it seems like you have a bunch of matter particles and then they at some point decay again and you have radiation domination.
Right. So I didn't really discuss dark matter here because to have dark matter you need matter which is able to
be affected by a non-standard evolution.
Yeah, well, Yeah, so those are basically behaving like dark matter, right, in the early universe, just that they would be metastable, so they would have decayed early enough. If you want to have a dark matter candidate in there, what you can do is take the lightest mode, because typically it can be much more long-lived.
I mean, if you have a matter domination epoch, right, at first, how this will be different from what you are saying by having a bunch of different matter-dominated epochs?
But that's what it is. That is what it is.
Oh, no, I mean, how can you differentiate between them?
From one? Well, the cosmology would change, because so that's if you look at those, if you're familiar with those pictures of the modes evolution, you know, this is the value of a given mode, and this is the size of the Hubble horizon shrinking during inflation and then re-increasing. Typically, the way this re-increases will depend on the equation of state parameter of the universe. So if you're radiation dominated, the size of the horizon would increase faster than matter domination. If you're in a stasis regime, basically the slope would differ from radiation of matter domination. It would be something intermediate. So there are plenty of consequences of that. Here, for instance, from this drawing, you can tell that this will affect the number of E-folds that you need from inflation, for instance. Now, if you ask me, can you really differentiate that? I think there is definitely a degeneracy. On this drawing, for instance, you can understand that having a matter domination then followed by a radiation domination could be equivalent in terms of number of E-folds to just, I mean, they could be equivalent. But if you look at other things like the evolution of the perturbation modes during that time, or the production of some particles, then all those things would be affected by the equation of state of the universe, definitely. So that the prediction that you would make in a matter-dominated era or in cosmological stasis era would be different.
Oh, okay, thank
you. But you have to look at specific observables then. Thank you very much.
Yes. Thank you very much. Can you hear me? Okay. So I would like to tell you about the discussion of the results will be mostly about these two recent papers, which are done with Maxime Laletin, and with some background over all the papers with Tobias Binder, Thorsten Brinkmann, and Michael Gustafsson. And let me start with the message first. So two main messages. So the first one is related to freeze-out. So typical picture for freeze-out is that if you plot the Combevik matter number density versus time, so this is the typical freeze-out curve you see all the time. But now imagine you have additional particle that decays to dark matter, right? So you have some unstable long-lived state decaying to dark matter, which its evolution is just a decay. And now you ask the question, so what is going to be the difference in dark matter evolution? So you would expect something like that. So there will be just a bit more particles because you just produced more, right? Now, since more particles means bigger density, means perhaps bigger annihilation, maybe there is some small decrease due to this increased annihilation, right? So the first message is that what actually can happen in some models is that this additional adding of additional states decaying to dark matter can decrease significantly your radial density. So that's the first message. And the second is related to freezing. And that is if you plot typically the annihilation cross-section today for freezing particles, and again, you have like limits and the galactic center excess could be fitted more or less here. Typical freezing models lie down below. There are kind of no way of finding them in indirect detection. My second message is that there is also a mechanism that you can have models living around here. Okay, so to see why and learn more, stay tuned. Okay, for this I need a bit of a background. So first, the history of the universe is that first dark matter is in a full chemical and kinetic equilibrium. Then chemical decoupling happens, then is a freeze out, and only after that kinetic decoupling happens, typically. And chemical decoupling and kinetic decoupling are both non-equilibrium processes that can be in general described by such an equation in kinetic theory, which you've rather seen typically as an equation for number density, which is derived in the following way, that you start with this Boltzmann equation, and to integrate over momentum, which is you take the zero of moment of this equation, and you get the equation which you're probably very familiar with, where the change of the number density is given by this annihilation, thermal average annihilation cross-section, and this gives you the standard freeze-out picture, right? Now, what I want to emphasize is that for this to happen, you need to have an assumption. So in order to integrate over momentum, you need to make an assumption that during chemical decoupling, kinetic equilibrium is maintained. Because what you need is you need your distribution function to be proportional to the equilibrium distribution function times by some factor, some normalization, which is only dependent on temperature, but not momentum. And only then you can get this equation so simply. So all the numerical codes available on the market are using this assumption, implicitly, typically. Okay, so what is the difference between freeze-out then and decoupling? So chemical freeze-out is governed by annihilation processes, and chemical elastic scatterings govern the kinetic decoupling. Now, those, in the simplest models, those amplitudes are just rated by cross symmetry, which means that the amplitude squared is given by the same analytic function, just depending on different kinematic variables. So you don't expect them to be very different in magnitude in the end. So since dark matter is typically much heavier than the particle it annihilates to, it means that the Boltzmann suppression of the initial state here is much larger than here, and therefore elastic scatterings are more efficient, more frequent, and you typically have kinetic decoupling after chemical decoupling. So this is the standard picture, but can it happen that this is not the case? And indeed, there are many examples of situations in which kinetic decoupling happen early enough that affect the freeze-out process. So the possibilities are several, but let me classify them here this way. So first, you can have violation of this similarity of those two amplitudes. Example, if you have resonance. You can have the standard model particle, like other mediator particle, as heavy as dark matter particle, example in forbidden-like dark matter scenarios. You can have scatterings annihilation that have completely different structure because they come from different part of the theory. For example, if you have some annihilation or 3-2-2 models, then in many of those models there are no scatterings at tree level at all. And finally, if you have multi-component dark sectors, everything can happen, basically, depending on your model. Okay, so what do you do if you cannot make that assumption I mentioned? So you can come back first to the Boltzmann equation for the phase space density function, and then see that in the collision term you have to contain both annihilations as usual, but also you have to add scatterings. And then you have two possible approaches. You can just solve numerically this equation, which has advantage that gives you also the insight into the distribution, but it's slightly more challenging numerically. But you can also solve for the moments of this distribution, but not only for the zeroth moment, but also the second moment to give you the evolution of the temperature. And it gives an approximate solution, which is a bit easier to handle. So luckily, you don't have to do it yourself now. We have published recently a code which we call Drake, going from dark matter relic abundance beyond kinetic equilibrium. And this code is written in Wolfram language, so you can use it in Mathematica or outside as well. And it allows you to compute dark matter relic density for any user-defined model, and study also things like phase space distribution of dark matter during freeze-out, and also other stuff. So I encourage you to check it out. It's on HackForge here. So let me just come now to the examples of results. So first, like a very old but good illustration. So if you take the simplest dark matter model ever, the scalar singlet dark matter, which is just the standard model Lagrangian with one scalar singlet, and this interaction term. And this model has been studied by Gambit collaboration a few years back to get the modern fit, and the modern fit puts you the best fit point in the resonance region. And in such a resonance region, annihilation is resonantly enhanced, while scattering isn't. And therefore, you have this violation of the typically late kinetic decoupling situation. And if you plot now the results of the ratio of the correct relic density divided by the one you get from micromegas using the standard assumptions, bearing in mind that there are some few different details which I don't want to go into, this basically shows you the effect of the difference. So you can easily get a order of magnitude difference, actually. So you're essentially making order of magnitude error if you use micromegas in this case,
And also down here in the resonance, also order of magnitude down. And thus the solid curve is the situation when you solve this coupled Boltzmann equation system for the moment, while the full numerical solution here is these black dots. All right, so let me now come, so this is kind of the simplest possible example to show how the code works and why it is interesting. But also now let me come to this recent result. So in this example, so what happens if you have multi-component dark sectors? So as I told you at the very beginning, you can have a situation that some unstable dark particle decays to dark matter. And this process distorts your distribution function, right? Because you have like some thermal distribution, and on top of this, you get energetic particles. So it can modify the annihilation rate, and also we were interested in studying how the thermalization actually happens. So as an example, let's take a situation that we take two assumptions. First, the dark matter has two components. One comes from thermal freeze-out, just for simplicity, and the second comes from a decay of some intermediate states to dark matter. And the second assumption is that dark matter annihilation has a threshold, such that it's very suppressed below some energy, and only if it gets some energy, the annihilation is very efficient. So what happens in that situation? So you have the component from freeze-out, and then you inject some additional dark matter particles which are much more energetic. If now you calculate this as usually, would you assume kinetic equilibrium and nothing else, then they will thermalize immediately, and therefore you have a bunch of particles with relatively low energy, which cannot efficiently annihilate above the threshold, so you end up more particles in the end. Now if you solve it for the full phase space, then what you get is that some of the energetic particles, since they have enough energy, they can hit themselves or particles from the thermal plasma, from the dark matter particles from thermal component, and annihilate above the threshold very efficiently. And therefore, the annihilation is very, very strongly enhanced. While also if you add self-scattering processes that redistribute energy in between dark matter particles, then this annihilation is even much more efficient because energy redistribution allows to upscatter some of the low energy particles to give bigger energy and then annihilate above the threshold. So if you look on the results for this type of model, an example results look like this. So here we have the number density, here we have temperature parameter, and okay, here's the plot of the different snapshots of the phase space distribution. So if you concentrate first here, so if you had no decay, the results would be like this. With just decay but not taking account any phase space evolution, you would get indeed increase of dark matter density. And then when you include the at the phase space level, without and with self-scatterings, you get huge suppression of the Rayleigh density for this type of model. And consequently, the temperature is also very different. So this is the equilibrium temperature, like the thermal bath, and then the dark matter is much heated by the fact that you inject energetic particles, right? And if you have self-scatterings, it's heated more because you upscatter those particles efficiently. And then if you look on the distribution function, then indeed here you start with close to equilibrium, and then times go up. So here you create the second bump from the injection, and then this kind of cools down and also interacts with the first bumps to create some intermediate particles. And these are all the results from our Drake code, which you can play with for your model. Okay, and then the remaining few minutes, 5 minutes, let me go to the second message of the talk, which is to the freezing part. What I want to introduce is a new process that can be used for freezing model building, which has a peculiar feature. And it's also accurate determination of the Rayleigh density requires that you solve look at the temperature, not only number density evolution. And what is this model? So this is the mechanism we call semi-production. This is the inverse of semi-annihilation. So imagine you have your dark matter dark matter particle created via freezing, but not as usual from a decay of some particle or from pair production from the plasma, but rather you need from the same inverse semi-annihilation process, which you need first some dark matter particle to be in the initial condition in order for this process to happen, right? So what is different when you use this process than usual case? Well, the production rate is proportional to dark matter density, right? Because this process requires, so it's proportional to this density of those particles in the initial state, which means that in order to arrive at the same relic abundance for freezing, you need larger cross-sections because it suppressed the production. And also, as I mentioned, since this semi-production modifies the energy of dark matter particles, and also it depends on the distribution of dark matter particles, it also have a temperature evolution can affect in non-trivial way the relic density. Okay, thanks. So this is the result for example case for such a model. And what I just want to emphasize is that, okay, so here's the co-moving number density, here's the temperature. And if you look on the co-moving number density, these are the lines for the dark matter density. And you can see that first there is some process 2-to-2 production, typically happens anyway, but it's very, very, very suppressed, and it would not produce enough of dark matter. But then when enough of kites are built up, then the semi-production happens very, very efficiently. And there's kind of exponential growth here. And you can see if the correct computation gives you this result, while if you forget about the temperature evolution and just did it naively, you would get this result. So there's still an order, kind of an order of magnitude difference if you do it properly or not. And in this model, when you look on the plane I showed at the very first slide, is that the present cross section, so those would be ruled out these days, there will be hierarchic center excess, and these are the results of the scan for one particular realization. And you can see that, of course, many of those points are still way, way, way below the detection threshold, but you can see a significant part of points that are not only potentially detectable in the near future, that also can affect the core formation, as some annihilation does through self-heating, and also potentially even explain galactic center excess through freezing. And just to mention here, the different colors are because some of those points can be tested via laboratory experiments like Matusla, Phaser, and SHIP, and so on. And those are the field ones. The other ones are harder to detect. Okay, so my conclusions. So kinetic equilibrium is necessary, even though of an implicit assumption, but it's not always warranted. And we introduced Drake, a code which I invite you to use to study these cases. And then if you have multi-component sectors, many weird things can happen that you naively wouldn't expect. Thank you very much.
Thank you for the nice talk. So I was just wondering, other than the scalar singlet dark matter model, what kind of models do you have in mind where this will be manifest very drastically?
Any resonance model, even for like if your resonance is as narrow, like as wide as the Z resonance, you could have like 10% effect sometimes. So you don't need to have a very narrow resonance, but of course for narrow resonance you can have an order of magnitude. As I said, like sub-threshold models, or like combination of those. In sub-threshold does not necessarily mean you have zero annihilation below the threshold, but if there are threshold annihilations, this could be important. And also in generic models in which you have elastic scatterings very suppressed, which can happen in many cases.
I see. Actually. And like for example, other than resonance enhancement, if you have something like velocity enhancement, like Sommerfeld enhancement, and
yeah. As well, Sommerfeld enhancement, stuff like this. Yeah.
Okay. Thank you.
So I'm wondering when the code that you mentioned can be used. Do you make any assumption on the phase space distribution of the extra particles that you add? Do you assume a Boltzmann distribution, or can you put any kind of distribution and just get?
For the moment, the code handles one distribution you solve for. The others you have to assume. And we assume internally they are in equilibrium, but you could modify this to assume there are different distributions known from something else. Now the code is going to be developed, and then we will be able to have solution of different states which are like generic distributions.
So the boosted one, you assume that they have a Boltzmann distribution?
No. The boosted one are just assumed. No, they are calculated fully. So you basically have a decay component, and you have collision term for a decay, and this produces something, and this what comes out, this comes out.
Oh yeah, that's really okay. Thank you.
Hi.
I have a question regarding your freezing part.
Mm-hmm.
So in the process, there is a phi chi to chi chi process, the process you have considered. So in this process, so the final relic density is also dependent on the initial abundance of chi. Is it right?
Yeah. Yes.
Yeah. So is it your free parameter or so you
no. So
dynamically generated from other processes?
So, okay, of course you can have a model in which you have no other process of production like this, but this is actually quite unlikely. So even if you have like a scalar type of model, you would have more like this, basically in Lagrangian, this process would be from one term, but you have other terms in Lagrangian. So typically the 2-2, phi phi to chi chi, this type of process is present as well. Okay. So there's enough that you have such a process that produces like minimal amount of dark matter, okay. Then this one kicks in.
Thanks.
And it's very unlikely that actually you have not a completely zero dark matter from no processes ever, right?
Thank you.
Any other question? Let's thank the speaker again. Now, the next speaker is Roy. Are you Roy? No, Roy Raiders. Right. And then the follow-up speaker is Ross.
Very short.
Right. Did you send me your talk? Yes, okay.
Ganguly.
Okay, so you're Ganguly.
Yeah.
So not Roshan.
No.
So Roshan has also gone.
He's also absent.
Yeah, okay.
Okay. So
right.
How do I use this? So this one pointer. Yes. Sorry.
Okay. Okay. Thank you. I'll give you both in 5 and 2 minutes.
Okay. Thank you. So first of all, I would like to thank the organizers for giving me this opportunity. So this is the title of my talk, and this talk is based on this paper, and this work has been done in collaboration with Anirban Bishwas and Shourab Rai. So we all know that from the cosmological astrophysical evidences that there exists some dark matter, and there are some known and unknown facts about the dark matter. And the known facts are that almost 1/4 of our universe is made of dark matter, and the dark matter interacts gravitationally, therefore it is massive, and since it is dark, therefore it do not interact with the light, and it is stable in the cosmological time scale, and it forms structures. But there are some unknown facts about the dark matter, such as we do not know its mass, spin, interaction strength with the visible particles, and we do not know about it, whether it is a single component or a multi-component, or even it is a particle dark matter or not. And we do not know about its stability, whether it is absolutely stable or slowly decaying. And finally, we do not know how it is produced in the early universe. So to address the dark matter issue, it is required to extend the standard model. So here is the mass range of a particle dark matter. So the lower limit of a particle dark matter is roughly 10 to the minus 22 eV for a bosonic dark matter, but this limit is much stronger in case of fermionic dark matter, which is the precise value of the limit is 5 eV, which is known as the Tremaine gun bound. And the lower limit of the WIM dark matter, which I will discuss in the next slide, which is roughly 4 GeV, which is the Lee-Weinberg bound. And finally, the upper limit of the thermal dark matter is roughly 100 TeV, and this limit has been derived assuming that the universe is radiation dominated. So here is the idea of the WIM dark matter. So the basic assumptions of the WIM dark matter is that the dark matter is in thermal equilibrium. That means it is chemical and kinetic equilibrium with the standard model particles in the early universe. And the dark matter interacts with the standard model particles with the weak scale couplings. So now if we calculate the annihilation cross section of the dark matter to standard model, and we will find that the annihilation cross section is roughly 10 to the minus 9 GeV to the power minus 2. And now if we solve the Bose-Band equation for a 1 TeV dark matter, then we will find that to satisfy the relic density constraint, we need the 10 to the power minus 9 GeV to the power minus 2 cross section, which is this black line denotes the correct line for the relic density. So this is known as the WIM miracle. That is, if the dark matter mass is nearly 1 TeV, and if it interacts with the standard model particles with the electric scale coupling. That means the coupling strength is the G2, where the G2 is the SU2L gauge coupling. Then we will get the correct relic density for a 1 TeV dark matter. So this is known as the WIMP miracle. But the problem with the WIMP search is that the parameter space of the WIMP is stringently constrained from the dark matter direct detection cross sections. And one can see from this figure that for a 1 TeV dark matter, the 10 to the power minus 46 centimeters square up to is excluded from the direct detection constraints. So in WIMP can also be searched in the collider experiments also, but the problem with the collider searches is that we cannot predict its stability in the cosmological time scale. So since the parameter space of the WIMP is constrained from these direct detection experiments and also from the indirect and collider searches, so it is so we need to go the beyond WIMP paradigm to address the dark matter issue. So here is the basic classifications of the dark matter. So the dark matter can be classified, the basic classification of the particle dark matter. So the particle dark matter can be classified into two parts, mainly in thermal and the non-thermal. And the thermal can be divided into freeze-out and asymmetry. And the freeze-out part can also be classified into 4 parts. The WIMP, which I have already discussed. These are strongly interacting massive particles with the SIMP, and the secluded sector and the semi-annihilation process. So in the rest of my talk, I will discuss about the secluded sector dark matter. So here is the basic idea of the secluded sector dark matter. So the basic idea of the secluded sector dark matter is there exists a visible sector which contains the standard model particles, and there exists another dark sector particles, dark sector which contains the dark matter chi and a mediator particle phi. And the phi can be scalar, fermion, boson, anything. So I denoted it as a phi. And the relic density in this scenario, it means the secluded sector scenario, it mainly determines by the chi to phi type of annihilation. And the phi particles can interact with the visible sector through this phi SM interaction. And the phi SM interaction determines the thermal properties of the dark sector. And it also determines the constraints from the experimental constraints on the dark sector dark matter parameter space. And then to ensure the observation at the time of BBN remains unaltered, we need that the phi should decay before the BBN. So since we do not know anything about the dark sector, so the dark sector can be multi-component, that can be degenerate, and that can be thermally decoupled. So anything can be possible in case of a dark sector. So here we will discuss the thermally decoupled, the dynamics of a thermally decoupled degenerate dark sector. So here we show the different time scales of the dark sector. So at TD, so in the dark sector, suppose there are two particles, say A and B, and suppose their masses are same. That means the MA equal to MB. And in this, here we show the different time scales of the dark sector. So suppose at TD, the dark sector decouples from the visible sector. And at T prime equal to M, where T prime is the dark sector temperature, since at TD, the dark sector is thermally and chemically decoupled from the visible sector, so therefore the dark sector can evolve with the different temperature. So in the at T prime equal to M, the dark sector becomes non-relativistic. But since the dark sector, the masses of the dark sector particles are same, so therefore in this region, when the temperature of the dark sector is below M, the AA to BB and the BB to AA process is still can happen because these processes are not kinematically forbidden. And the B particle, suppose interacts with the standard model, and suppose at T gamma prime, B particle starts to decay into the standard model particles. So therefore, between the T prime and T gamma prime, the rate of AA to BB and BB to AA remains same. So therefore, they are in a thermal equilibrium. But after this point, the number density of B starts to decrease. this is because of the decay of out of equilibrium, decay of the B particle, and therefore there is some imbalance in the forward reaction rate, that means the A to BB, and the backward reaction rate, where the BB to A. And and at the time of when the T prime and when the dark sector temperature is roughly T prime F, then the dark matter A freezes out. So since the number density of the particle A, which is the dark matter candidate, decrease when the B starts to decay into a standard model. So this mechanism is known as the co-decaying dark matter scenario, and the special feature of this scenario is that the final abundance of A, that is the dark matter candidate, depends on the annihilation cross section A to BB as well as the decay width of B. So to study this scenario in some BSM model, we need a particle A, which is the dark matter candidate, and we need a mediator particle B, which couples with the standard model bath. So the obvious choice to extend the standard model is to U1 extension of the standard model. So since we have considered a U1 extension of the standard model, so therefore, if we want to construct a gauge theory which is an anomaly free, we have to add two left chiral Weil fermion, which with U1x charge is +1 and -1. Therefore, this dark set, the U1x extension is anomaly free, and these two particles are standard model gauge singlet. And as I mentioned earlier, that we need a massive mediator particle. So therefore, the gauge boson corresponding to this U1x gauge symmetry should be massive. So therefore, we need to break this U1x gauge symmetry. So therefore, we need a complex scalar, which is denoted as eta. And so when the complex scalar eta gets a vacuum expectation value, therefore the Z prime gauge boson becomes massive. And in the dark sector, there are four dark sector particles with the two Majorana fermions, the linear combinations of this Xi1n and Xi2l, the chi1 and chi2. And there is two mediator particles, Z prime, and the HD is the real component of this scalar eta. And since the dark sector contains these two mediator particles, Z prime and HD, and it will help us to detect this the dark matter by studying the gamma photon and neutrino signals from the dark matter annihilation. So in our scenario, the dark matter is multi-component with two dark matter particles, chi1 and chi2, and two mediator particles, Z prime and HD. And the role of the A particle will be played by chi1 and chi2, and the role of the B particle will be played by Z prime and HD, since Z prime kinetically mixes with the U1Y gauge bosons, and the HD mixes with the standard model Higgs. So here is the Lagrangian of our model. So LSM is the standard model Lagrangian. L gauge is the kinetic term of this U1x gauge boson, and this last term is basically the kinetic mixing of the U1y hypercharged gauge boson and the U1x gauge boson. LDM gauge is the kinetic term of these two left chiral Weil fermion, Xi1n and Xi2l. And LDM Yukawa is the Yukawa interaction terms of this Xi1 and Xi2 and eta. And finally, this L scalar denotes the kinetic term of this complex scalar eta and this scalar potential. So here is the dark matter annihilation channel. So in the first row, we denote this dark matter, the chi-I to HD dark matter annihilation channels. In the second row, we have shown the dark matter annihilation channels into two Z prime, and in the last row, we show the Z prime annihilation into HD. Since the dark matter is not involved in these processes, but since the Z prime also decay out of equilibrium into the standard model particles, we need to solve the Boltzmann equation for chi-I, that means chi1 and chi2, Z prime and HD. And also, since I have mentioned earlier that the dark sector is thermally decoupled, so therefore we need to solve the temperature evolution of the dark sector as well. So here is the results. So in the left panel, we show for a particular benchmark point, we show the Cohen number density y as a function of x, which is the x is defined as the m chi over t, where t is a standard model temperature. And the red line denotes the Cohen number density of chi. And the z prime, the Cohen number density of z prime and hd is denoted by green and blue line respectively. And the y chi eq, the black dash line denotes the equilibrium number density. So one interesting feature is that, so in comparison to the standard WIMP scenario, the dark sector freezes out at much later time, and this is because the dark sector freezes out when the z prime and hd starts to decay out of equilibrium into the standard model particles. So therefore, it is there. So therefore, it freezes out much later time. And in the right panel, we show the temperature of the dark and as well as the visible sector with respect to this x, which is x equal m chi over t. And the black dashed line shows the temperature evolution of the standard model, which is the standard radiation dominated era, which is proportional to 1 over a. However, this the red line shows that the temperature evolution of the dark sector, and in this region, the rate of fall of the T prime is very small comparison to this. This is because of the fact that in our scenario we have considered the 3-to-2 processes in the dark sector, and since the dark sector, because of these 3-to-2 processes, the dark matter enters into the phases called the cannibal phase. So therefore, in these phases, the dark sector the temperature falls as 1 by log a. So therefore, in this scenario, in this region, the dark sector temperature falls much slowly. So here is the constraints on the mediator particles. So in the left panel, we show the the kinetic mixing parameter, the kinetic mixing parameter versus the mz prime, and this region is constrained from the direct detection experiments. The orange region is excluded from the electric precision observable, and this green region is excluded because we are interested in a scenario where the dark sector is thermally decoupled. So therefore, in this region, the dark sector is in thermal equilibrium with the standard model particles. That means in the kinetic equilibrium. And in this, this is the constraint from the beam dump experiment, and this is from the SN 1987 cooling. And in the sky, the blue region is excluded from the fact that the lifetime of the Z prime should be greater than the T BBN. So the similar plot is shown in this panel for the dark Higgs mass as a function of the mixing angle between the standard model Higgs and the dark Higgs. So here is the M versus Gx plane, where the M is the dark sector particles mass, whereas the Gx is the dark sector gauge coupling. So the scattered points denotes the relic density satisfied points, and the yellow and green region is excluded from the diffuse gamma ray signals from the dark matter annihilation, where we have considered the one-step dark matter annihilation of a one-step cascade. We have calculated the photon flux from a dark matter annihilation via one-step cascade process. That means the chi annihilates to 2 Z prime, and Z prime decays into FF bar gamma. And this region is excluded from the fact that since we are interested in a scenario where this where the dark sector is in kinetic equilibrium with the standard model. And the variation of this, the epsilon parameter, which is the kinetic mixing parameter, is shown in the color bar. So here is the summary of our work. So as I mentioned earlier, the out of equilibrium decay of the long-lived mediator, that means in the Z prime and HD, leading to a delayed freeze out, which is known as the co-decaying dark matter scenario. And since we have considered the 3-to-2 processes in the dark sector, so the dark sector enters into a cannibal phase, and therefore the temperature evolution of the dark sector changes significantly. And we have also studied the allowed region of the parameters phase from the neutrino and gamma ray signals from the dark matter annihilation via one-step cascade processes. And finally, we have also studied the effect of the non-zero mass splitting between the dark sector particles, and we have found that some parameter space has been ruled out from the diffuse gamma ray background, diffuse gamma ray flux by measurement of the diffuse gamma ray flux by integral, the CMB anisotropy, and the positron flux, the measurement by AMS02 experiment. So thank you.
Hi, thank you for the nice talk. So I have two questions. So one question is that, so if this dark matter is decaying, then...
Dark matter is not decaying.
No, sorry. If there is a dark sector particle decaying, then do you also not affect the CMB spectral distortions and 21 centimeter?
No, that depends on the time when the dark sector particles decay. So in our scenario, we have not considered the parameter space, sorry, here. So in this scenario, the dark sector particles decay after BBN.
Okay, and this is already ruled out, you're saying?
Yeah, so we are in this region of our parameter space.
Oh, okay, so in your case, it already decays before Big Bang nucleosynthesis. Okay, and the second question is the second. Can you go to the second last slide? Yeah, here you're varying the kinetic mixing, right? So in principle, you could also try to see the plot between the kinetic mixing and the mass, where you have other experiments like beam dump and other kind of stuff.
Okay, so beam dump experiment. So in this plot, we have sorted the data in such a way so that these points are not there in this plot.
Oh, so okay, so that filtration is already done from.
Yes.
Oh, I see. Okay, thank you.
So on the plot where you have the two temperatures, I noticed that you start with a dark sector temperature which is lower than the visible sector temperature, right? So you take a ratio of 10 or so.
So yes, we have taken the T prime by T equal to 0.1. That means the T by T prime is...
I'm just wondering why, like, because you have this short period during which the dark sector dominates, and I assume that then it probably injects entropy.
Sorry?
Are you doing that in such a way that you have the correct entropy dilution effect, or...
okay, just tell me.
No, I'm just wondering why you choose this particular ratio.
In our scenario, we have considered this ratio to be 0.1, and since we have considered this gauge couplings, that means the dark sector gauge couplings is very large, it is a 0.477. So the initial condition doesn't matter in our scenario. So if we consider that xi, that means the T prime and T nearly equals to 1, then the final relic density will be same.
It will be the same?
Yes, yeah.
Although you have less, because you have entropy dilution from...
Entropy dilution, okay. So in this scenario, since in our scenario there are 4 Boltzmann equations is there, and we have assumed since the degrees of freedom in the dark sector is much smaller in comparison to the visible sector, so we have considered that the entropy is roughly approximately conserved in the dark sector. In the visible sector.
And I have another question. Actually, it's like, why the red curve? So when I understand that on the temperature plot again, you have, so the red curve starts plateauing because I assume that's the cannibal phase. But then when it stops dropping, that's because the mediators decays, right?
No. So there are two regions. In this region, there are 3 to 2 processes are active. In this region, the cannibal phase.
Yeah.
And in this region, all the processes are decoupled, so therefore T prime falls as 1 by a square.
So when does the Z prime decay?
Okay, so Z prime decay, so this is the temperature of the chi,
right?
Not Z prime. Chi, that the dark matter particle.
Right, but when does the Z prime decay on this plot?
Okay, so Z prime decay nearly x equal to 100, so here.
Okay, it's not there anymore after. Okay.
baryon number violation.
Yeah. Okay, so this this talk will be a little bit different from the others. So I'm gonna talk about an experiment that we're building at the European Spallation Source at TSS for searching for baryon number violation. And as you know, baryon number violation is very, very important. It's an essential condition for baryogenesis. It's a Sakharov condition along with loss of thermal equilibrium and CP violation. So it might be the key to explain matter-antimatter asymmetry of the universe. So baryon number is really not a sacred symmetry. It's routinely broken in extensions of the standard model. For example, of course, supersymmetry, RPV, SUSY, hidden sector models, extra dimensions. And even in the standard model, it occurs at non-perturbative level. And one thing that is also very interesting about neutron transformations, either to antineutrons or to sterile neutrons, which are the two channels we are be searching for in the experiment. This is very unique because then it's only baryon number that is violated. If you think about proton decay, for example, then you have both baryon and lepton number violation. So, and in this experiment I'll show you a little bit that we'll have the possibility to improve the sensitivity to neutron oscillations by 3 orders of magnitude. So, and this is really an opportunity to test a global symmetry, 3 times with 3 orders of magnitude better than before, is a very rare opportunity. So our experiment is going to be a stage experiment. So the first stage of the experiment is called high beam. And this is to happen in the late 2020s at ESS. So at high beam, we'll do world-leading searches for end-to-end pride and to sterile neutrons. And we'll also search for end-to-end bar with lower sensitivity. And the reason for this is that the high beam experiment is going to have a lower flight path. So we also do search for end-to-end bar via sterile neutrons, and this will be the first time that this search will be conducted. And of course, we'll use the opportunity to do R&D for the full NN bar experiment. So NN bar, this is to happen in after 2030, and where we'll do this extremely high precision searches for end-to-end bar and NN prime. But as early as next year, we will do starting prototype and background tests with cosmic rays. So just to show a little bit how the experiment works. So the strategy in this experiment is to let as many neutrons fly for as long as possible. So, and then it can be demonstrated just by straightforward quantum mechanical arguments that if you have free neutrons flying, then you have the probability of oscillation is given by this expression, which here you can see that here this is the neutron flight time and tau is the oscillation time. But the oscillation time, of course, we don't know. That depends on which model you're using. So the experimental figure of merit is NT-square. So which means that the more neutrons you have, the better for you to find this probability. And of course, the way that we do this is that we have a super focusing reflector here, and then we have a cold neutron moderator. So that's I'm going to talk a little bit, if I have time, about moderators. And then the neutron is allowed to bounce one time in the super mirror. And then if it oscillates to an antineutron, then it will annihilate in a carbon target and produce this multi-pion finite state, and then of course what you want to do is to enclose the final state and reconstruct the event with a 4-pi detector. And this is 200 meters, this is for NN bar, but we also in high beam, so in the first stage, since the flight path is much shorter, we won't have the sensitivity that we want for neutron oscillation. So we thought about a little bit of a different experiment searching for sterile neutrons. And the way this works is that we'll have some different searches here. So either here we are gonna in the first experiment we're gonna put a beam dump here, and then the neutron. The hypothesis is that the neutron either oscillates to some sterile neutron state here, and then it passes the beam dump because it doesn't interact with it, and it flips back to a neutron here, and then we count the neutrons. Of course, you have to control the background and etc., but that's the idea. In the disappearing experiment, you remove the beam dump, but then and then you control the flux. But then what happens is that if a neutron oscillates to a sterile neutron, then you have a decrease on your flux. So you have to have a very different type of neutron detector here that you also control the flux. And of course, just as in the first stage, in the first experiment, the sterile neutron could flip to a neutron, but it could also flip as well to an anti-neutron. So and then in this case, we put an annihilation detector here. And here, just to show the sensitivity that we have for discovering either regeneration or disappearance. And of course, regeneration has we have a smaller sensitivity because it's a higher order process. You have to have 2 flips. And the disappearance. And of course, it depends not only on that, on how long the experiment is running, but also on how large is your capture area, so how large your detector is. So the larger, then the better your sensitivity. So I just want to talk just very quickly about ESS. So ESS will be the most powerful neutron source. It's located in Lund, in Sweden, and is under construction, and our user program starts in 2027. So just here if people don't know about how the neutrons are produced in spallation sources, maybe not everybody's familiar with it. We have a proton linac here, and then it accelerates this into a tungsten target, which is rotating. And then the neutrons are then guided by neutron guides to the experiments. And of course, at this point, the neutrons, they are very energetic, but then we have moderators to decrease the energy to the ones that we are interested in. And here, just to show a little bit our experiment here on another view. So these are the current beam lines, neutron lines that are being already constructed at ESS. And you can see here that ours, the NR-Bauer final experiment, is going to be a straight, very long beam line, and then of course of 200 meters. And the reason why we can't go beyond this is because there is a road here. And of course, you might also ask yourself, people have done this neutron oscillations before. What's so great about ESS? Well, one, of course, is the number of neutrons. We're going to be producing lots of neutrons, but there is something else beyond the fact that we are producing so many neutrons, which is the angular acceptance. And the reason for this, one main reason for this increase here is because at ESS we are going to use what we call the large beam port. So this large beam port is, if you compare here how large a standard ESS beam port is, I mean, the large beam port will, it's equivalent to three times the size of a regular one. And also the fact that, a lot has, improved in terms of neutron technology, in terms of neutron reflectors. So that's also, those factors combined is what gives that factor of 40. I mean, there are other things, as I showed here, there are other things, but these are more standard. Like, I mean, you can run for longer, you can have the length, but these are sort of trivial. Okay, so we're a very big, very active collaboration. So here I'm just showing here our simulation framework, and the reason I show this is because it gives you an idea of every aspect of the detector that we need, or of the experiment, sorry, that we need to simulate in order to simulate the experiment. So this needs to be, of course, a magnetically shielded experiment. So it's for N and bar. So there is we do some simulations that there needs to be shielding simulations for the whole experiment, and also using neutron transport codes to produce the neutron source. And of course, I mean, the detector, we do the simulation using Geon4. So there is a lot of, there is even, I gave a talk in some CERN computing school. There is even a recording if you want to have a look. So, as I told you, so we have at ESS, there is already a moderator source, which is a moderator which slows down the fast neutron oscillations, and this current moderator is located above the target, the tungsten target. But we are also doing simulations to develop a new moderator, which will, because in the case of our large beam port, the large beam port will be able to see both moderators. So this new moderator that we are developing uses liquid deuterium and beryllium. And I mean, what our simulation shows that, I mean, we have a very, it's very effective for producing the neutrons that we're interested in. Optics now. So optics is another area that we have been doing lots of simulations, and the reason why this needs to be done is because there are different ways how you can make the reflection so that you guides. Because I mean the goal of the optics is to, as effectively as possible, to transport the neutrons to the target, to the carbon target, not to so there is no confusion. So we are comparing this, we have this, I showed you this figure of merit before, but we are using our figure of merit, we are comparing this to the last experiment that was done in the 90s. It was done in the 90s, and the ILL. So here you can see some results, and what is interesting about this is that, I mean, there are different ways that you can do the optics. I mean, different ways that you can build the mirrors. But we came to the conclusion that, I mean, this is elliptical nested reflector is the best one. But I mean, they are not that different. So, which means that, I mean, we can use a planar nested reflector just as well. So I'll very quickly go to the detector. So Our detector it's going to be a needs to detect a multi-fine pion state, one of the things, of course, is that we need to reconstruct the invariant mass that matches to neutron masses 1.8 GeV. So there are different requirements for the detector. I can go about this later, or if there are questions. But of course, I mean, this is just to show really quickly the detector. So we're going to have, so here is where the carbon target is going to sit, and of course, I mean, when the pions are produced, they will hit here the aluminum tube, and then this could cause some multiple scattering. So we want to put a silicon detector here. And of course, I mean, since we have pions, we need TPC. We need a tracker, of course, and also here an hadronic range detector so that we can distinguish between protons and pions. So, and of course, I mean, for the pions, of course, one of the most important things about the pions, about the pi zeros, is that we need a good electromagnetic calorimeter so that we can reconstruct the pi zero through the decay of the photons. So here you can see some simulation of this. So just to summarize, so our experiment is an active experimental program for ESS. We're going to do word-leading searches, sterile neutron searches in high beam, word-leading neutron-anti-neutron oscillation searches in NM-bar. And simulations and prototypes tests are the current our current focus, and we expect to deliver CDR by 2023. Okay, thank you.
Hi, thank you. Sorry, a bit tangential and maybe naive question, but is it going to be possible in ESS to measure other spallation processes like antiproton and perhaps anti-neutron production from
other
spallation processes like antiproton production, for example, or anti-neutron production, cross sections basically?
The cross sections. I don't know. I mean, there is a this specifically. I don't know. I mean, there is at ESS in terms of fundamental physics. There is a very big fundamental physics program that it's. So we are producing a paper right now on all different sort of measurements, and this might even be there. I mean, it's not my.
Okay, thank you.
but it's yeah.
So thank you for the interesting talk. So can you remind us, how can we estimate the length of the track which maximize the conversion?
The length of the?
Yeah, length of this this line.
The beam line.
Yeah, beam line, right.
Yeah, I mean the length. I mean we don't estimate. I mean we want the length to be as large as possible. So I mean and. There is no, I mean, if we have a flight path of 200 meters, so if we could have one of 300 meters, it would be better. So there is no, that just increases the probability of seeing an oscillation, just as well as the number of neutrons.
So is it highly theory dependent, and the length can be any?
Theory dependent?
Yeah.
Well, yeah, sure. I mean, the different, I mean, this is not guided by theory in any case. I mean, also because the information about what caused the oscillation will disappear. So that's not going to, it is just like G-2. It's not something that you're going to know why. Of course, there is a paper on RPV SUSY, for example, calculating, what is the oscillation time for this particular model, and you can calculate for different models, and that's going to, and that L then is affected by that. That's depending on your L, you might be able to see or not see depending on which model But that's completely dependent on, yeah.
Okay, thank you very much.
Yeah.
The final talk for this session is by Ioannina, who is going to talk to us about gravitational waves, primordial black holes in the early universe matter era.
Για πες μου, εδώ πέρα είναι αλλάζει. Okay. Thanks for giving me the opportunity to give this talk, and it's a pleasure to be in Ioannina again. So this is the title of my talk. I'm Ioannina from Athens, but I should say that I decided to give, let's say, a review of the topic, because I guess that most of you you are not working on this direction. So instead of discussing a particular topic, which is the GW production from an early matter domination era, this will be the last part of my talk. So I will start with an interview, a motivation, and then I will discuss some inflationary model building that gives production to PBH. So I'm starting from the basics. Since 2015, we know that gravitational waves exist and penetrate the universe. And also, by detecting gravitational wave spectrum, the spectrum of the waves, we learn a lot of things about the production mechanism, the source. For example, here we know that come from black hole mergers. And the message that we get is that, firstly, the universe is filled with gravitational waves that penetrate the universe, and also that these waves gives us information about the dark side of the universe. And the second is that primordial black holes exist. So this is the main motivation to work on this direction. And let me comment that black holes that we know that exist is the only object that we know that can be, that exists that can be the dark matter in the universe. There is nothing else that we have now that can be the dark matter. Nothing else. There is no particle that we know that can be dark matter, and no other object except for black holes. So it's natural to examine this scenario that PPH account for refraction or the entire dark matter density. So primordial black holes are primordial, so they are produced in the very early universe, and there is a gravitational wave signal associated with the PBH production. So PBH stands for primordial black holes. And this is gravitational waves are stochastic gravitational waves. So in order to study them, we have to estimate their energy density and their spectrum. And what actually we know, there is already a constraint that the omega, which is dimensionless energy density parameter, the omega of the stochastic gravitational wave background, has to be less than 2 - 6 to -5. This constraint comes from the CMB and BBN constraints. So we are expecting a very weak signal coming from the stochastic gravitational waves. So in order to detect them, we need a network of sensitive detectors and, of course, the knowledge of the spectral energy density. So actually, the theory of the early universe gives us several sources for stochastic gravitational wave background. One is first-order phase transition. Quiros talked about them today. Topological defects, inflation, also Kostas Dimopoulos talked about it a few days ago. And induced gravitational waves that I'm going to talk now. So why I'm interested in induced gravitational waves is that they exist. We know that they exist. All the others are more or less assumptions. So, and we know that they exist because we know that the CMB has temperature anisotropies. This is enough to guarantee that induced or secondary gravitational waves exist. And I'm going to explain to you what is induced gravitational waves. So a further motivation to work on this direction is that already there is a network of gravitational wave detectors that are mostly sensitive to 100 Hertz frequency band. But also there are, also it is the CMB, B-mode, other experiments that are actually designed. For example, LISA, which is going to operate in the next decade, and PT experiments that are sensitive in nanohertz,
The LISA is sensitive to millihertz. And of course, these are the experiments that are trying to detect B modes on the CMB sky, which will be sensitive in very small frequency ranges. So each experiment is sensitive to different frequency bands. And for example, LISA can give us a constraint on the energy density of the gravitational waves that can be it can be the sensitivity up to 10 to minus 12 of the critical density of the universe. And this is the overview of the experiments. Okay, I should say that the LIGO exists, and Virgo, LIGO Virgo, and CMB. All the other are forecasts. But as you see, it's very promising, all these experiments. It's very promising that there may be a positive detection of stochastic gravitational wave background, or equivalently, there can be very interesting constraints. So let me now say a few things about induced gravitational waves or secondary gravitational waves. They are produced because there are density perturbations in the early universe, that's all. So going beyond the linear order in cosmological perturbation theory, scalars couple at second order, and they can source tensor perturbations. So these are the second order or induced tensor perturbations or gravitational waves. This is known from 90s. So let me now say very few words about their amplitude. So we expect in the standard conventional inflationary theory, we expect that the amplitude of the primordial tensors to be stronger than the amplitude of the secondary gravitational waves or the induced tensors. However, as far as we do not detect gravitational waves from inflation, and this translates into a constraint on the R, which is the tensor to scalar ratio, and the R goes smaller and smaller, it is possible that the induced gravitational waves to have a larger amplitude than primordial tensors. So it might be that we will detect that the induced, the secondary tensors to give a stronger signal than the primordial tensors from inflation. And if there are primordial black holes, then we expect to have a very prominent signal. Okay, so you see here an enhancement of the powers of the second order tensors, and that can be actually probed by experiments such as LISA or even LIGO. So now the question is it possible to have such a huge enhancement? And the answer is yes. And the answer is yes because the constraints that we put on the inflationary models is only at a very small window, which corresponds to very large scales. So to wave numbers larger than 1 inverse megaparsec. So in smaller scales, we know nearly nothing about the amplitude of the primordial spectrum of the curvature perturbations, and most of the constraints actually come from the non-detection of primordial black holes. Okay, so a conventional inflationary model predicts a spectrum of curvature perturbations that looks like this, so it's a red one. So such models predict zero abundance of primordial black holes. Actually, this is the spectrum of the Starobinsky model. So in order to have primordial black holes, we need an enhancement. And so here I'm showing some models that predict an enhancement of the primordial curvature power spectrum. A first model from Bellido, also Ioannina, Ballesteros, Sasaki. And also let me show that people who participate in the conference, like Dres, Nanopoulos, Panos, Tammo, and also Mavromatos, and also Kostas, have given to us some models that predict a strong peak of the primordial spectrum of curvature perturbations. So now let me discuss some classes of inflationary models that give such an enhancement. And the first class is the so-called inflection point models, and I'm presenting my model, the model that I wrote with my collaborators, and George is actually here, George Stringas. So we used the alpha attractor models, and what we did was deformed their shape in order to have an inflection point at the last stages of inflation. So such models can produce an enhancement, a very strong enhancement of the power spectrum, and primordial black holes can form and can have an abundance that can be that can saturate also the dark matter abundance. So we can explain at this window of masses the entire dark matter abundance with primordial black holes. And also, as I said, because we have a strong enhancement of the density perturbations, we expect to have induced gravitational waves. And here you see the red line, which corresponds to these models, the so-called alpha attractors. These are results done with Konstantinos Kritos a few years ago. So let me now turn to a second class of inflationary models that can produce an enhancement, and these are of the primordial spectrum. And these are models that feature a very strong, let's say, a sharp transition in the energy density of the potential energy density. So they have some features that look like steps, and the reason that there is an enhancement is that during that stage there is a deviation from the slow roll inflation, and the eta parameter deviates strongly from 1. But what is interesting with these models is that apart from the enhancement of the spectrum, we have also oscillatory patterns at the peak of the spectrum. And the reason is that this sharp transition detunes the relative phase of the real and imaginary part of the curvature perturbation. So you see here that the curvature perturbation, as long as before the feature, the step, it's constant, but afterwards, after the experience, let's say, this sudden transition, we have this oscillatory pattern. And if this actually pulse you see here is negative, we have also a strong enhancement. So this is how the primordial spectrum of perturbation looks like. So it's enhanced, and it has also, in addition, on top of that, a very particular oscillatory pattern that we can describe also analytically. This is work done with Tetradis and Ioanna Stamu and the Tetradis students. Okay, and this is actually the difference between the inflection point and the step. The change of the f actually is the change of the eta. When you have a step, it looks like this, and when you have a inflection point, it's like this. And if this is sharp enough, you have also oscillations. Okay, this may sound a bit technical, but the result is that if we detect gravitational waves, and on top of that there is an oscillatory pattern, this means that there is a strong feature during inflation. Okay. So now let me turn to the third model. If we have terms in the field space, now we turn to multi-field models. This is work done recently with also the Tetradis and Boutivas and Kodaxis. And the reason is that the curvature perturbation is sourced by isocurvature perturbations. So if we excite isocurvature perturbations at some point during the inflationary evolution, then we can enhance the curvature perturbations. And actually, as you see here, at some particular points, here are the e-folds. The eta parameter deviates significantly from 1. So we have short deviations from slow roll. And what we get is an amplification of the power spectrum that also gives a very strong gravitational wave signal that looks like this. Now the difference is that we have a different shape, but not that prominent oscillations about the peak. So this is if we have 3 turns or 4 turns. So you understand that more or less these are very special models. Huh? Okay, and let me now discuss the fourth model. How much time do I have? 10 minutes? Less? Okay, a fourth model that is, in my opinion, also very interesting, is that what happens, okay, there is a question here, if the deviation from scale invariance of the primordial spectrum happens at the very last stage of inflation. For example, here, this is a model. This means that the primordial black holes will have a mass which is extremely small. And these are called mini black holes, and they will evaporate very fast in the early universe. So which means that they cannot account for the dark matter in the universe. However, they have one very interesting application that I studied with George Trigas and George Kodaxis recently, is that they can reheat the universe. So we can have a reheating only due to PBH evaporation. And here is a particular model. Okay, as you see, it's a runaway, so it's on purpose a runaway because these models cannot reheat the universe. So you see here the W parameter, which is the ratio of the pressure over density. It's -1 during inflation. There is a small deviation here due to the inflection point. And then it's 1, so we have kination. And what happens is that we have a generation of production of mini black holes that behave like pressureless matter, but these black holes evaporate promptly, and we have finally the radiation-dominated universe. And everything, all of this must happen before the time of BBN. So we are discussing about primordial black holes with mass less than about 10 to the 8, 10 to the 9 grams. Okay. What is interesting in this scenario is that we have a compound signal of gravitational waves. These are the induced gravitational waves, and these are an extra component, an extra signal that comes from the transition from the PBH domination phase to the radiation domination phase. And okay, so that's all about I want to say about the inflationary model building. Now let me turn to the last part of my talk, which is actually the title. And the question is, what happens if there is an early matter domination era? And actually one of the speakers discussed such a scenario, more or less. And I think this is mostly interesting, I mean, for the audience here, because many models that are, I would say, motivated from particle physics, they predict or they ask for a late entropy production in order, for example, to have the correct dark matter abundance or the correct baryon asymmetry, and so on, so forth. So in case we have an early matter domination era, all the story about the PPH production, the gravitational wave production changes because we have a stage with a pressureless matter. So we realized recently that the computation of the gravitational wave signal coming from an early matter domination era, that in this computation there is a gap, and the gap is that either they compute only a part of the total signal, or the result is totally unreliable. And the reason that it's not reliable or is partial is that during a matter domination era, the gravitational potential or the Poynting potential does not decay. You see, for example, if you have radiation or kination, these are quite similar. The gravitational potential decays very fast once it enters the horizon. However, if you have an early matter domination era, this is constant, and the density perturbations grow. And very fast, we reach beyond a certain scale, the perturbative analysis breaks down. So we enter into a nonlinear regime, and all this perturbative calculation of the gravitational wave spectrum is not valid anymore. So we asked ourselves, what can we do now? Because personally, I was very interested in the early matter domination era, and together with Chris Kouvaris, we found a way to calculate the signal coming from the early matter domination era after the perturbative regime has broken down, following the results of Zeldovich from 70s, and we found that a gravitational wave is produced because the quadrupole moment of this overdensity changes with time. So actually, this is what happens. There is an overdensity here, and due to the absence of isotropic pressure, due to the absence of pressure, there is an isotropic evolution of the overdensity, and then we have a pancake collapse. This is the well-known Zeldovich result. And actually, if the Hooke conjecture is satisfied, we have also the PBH formation. And actually, we verified this result, this analysis, recently, because we managed to run an n-body simulation, and I'm going to show this n-body simulation now. This is not a video, it's a PDF. So it goes like this. There is no pressure here, so it's a cold collapse. Okay, and this is more or less the result. Okay, somewhere here is the Zeldovich pancake. Okay, so in order to estimate the gravitational wave signal coming from the evolution of this overdensity of this distribution, we have to assume a probability density for the deviation from asphericity, and this is given actually from, we found that, okay, one can find that this is given by Doroskevich from 70s. This is a Gaussian probability density that describes the deviations from sphericity. And actually, what we have to estimate is the gravitational wave signal coming from patches that look like this. This is right after a picture of the universe with different patches right after the entry from homogeneities. And we have to integrate over all the contributions here. As you see, in some patches there is a black hole formation, but mostly we have failed, let's say, collapses to black holes. So we have some halo formation or pancakes. So what we do is we integrate over all possible configurations, and this is our result. And after doing the numerical calculation of this integral, we find the spectrum of the gravitational waves. So this is the spectrum of the gravitational waves produced during early matter domination due to halo formation. And this is the signal if we consider only the regions that collapse to black holes. You see it's small. But if we take into account all the regions, the signal is much, much stronger. And as you see, it's strong enough to be detected by future detectors. Or even LIGO, but okay, this is, let's say, very optimistic. And also, we are talking about early matter domination era, so the temperature plays a critical role. So we have different reheating temperatures, we have a different shape, not actually it's shifted, and amplitude of the signal, and this makes perfect sense because the later is the reheating, the smaller is the amplitude of the gravitational waves produced during early matter domination. So as I said, the amplitude can be large enough to be detected. So we take now the optimistic cases. So for example, this is the case if we have PBH to be the dark matter of the universe in the region of the asteroid mass, then we'll have a signal that can be detected by LISA of gravitational waves. And this is the characteristic pattern that tells us that the early matter domination era was realized in the early universe. And also, okay, this is extreme case of evaporating black holes. Maybe also LIGO Virgo could tell us something. And these are black holes in the solar mass region. That is, and the PT experiments are sensitive to gravitational waves at the nanohertz, which are associated with primordial black holes at the solar mass region. So this is a work in progress, and actually what we want to do is to successfully include all the processes that contribute to this gravitational wave signal coming from early matter domination era. And I think, in my opinion, this is very interesting, and also it's a novel result in the literature. So this is my summary. Okay, I think I will not read all this. I think I have run out of time. So yeah, thank you. Hope it was not, it was interesting for you. Yeah.
Hi, thank you for the nice talk. So when you have this kind of potentials and you have the power spectrum, so other than generating second order 10 tensor perturbations and primordial black hole, you must also be exciting non-Gaussianities, right? Because there are also 3-point functions contributing. So you must, I mean, one must try to see whether they are under control.
Your question is if there are non-Gaussianities and if they play any role.
Yeah.
Yeah, I think this has been discussed in the literature. Personally, I haven't done any work on this. Of course, now we are talking about larger enhancements of the power spectrum, and non-Gaussianities may play a role.
Yeah.
So in the literature, there are statements that they indeed influence the PBH abundance. The non-Gaussianities, but they don't change much. Let's say the picture of the PBH formation and the order of magnitude in the numbers. You know. Yeah.
And why is that? Because at the end of the day, you have your 2-point functions that is getting corrected, right? So your 2-point functions is inducing your power spectrum, which has a peak, and then you.
Okay. As far as I know, it depends, how you consider what's the impact of non-Gaussianities, how you consider them. Okay, in the end of the day, it may change, the required amplification of the power spectrum about a factor of 1 or 2 or 3. For example, instead of having 10 to minus 2, you may need to have 5 10 to minus 2. the amplitude.
Is at the pivot scale you're talking about, or
sorry,
so you're talking about this bound in the pivot scale or in across all k values?
No, this is this applies. No, this I'm talking about the PBH formation right now. So this this applies only to PBH abundance.
Oh, okay,
this bound on non-Gaussianities.
Okay, thank you.
Because I don't know if there is an. Okay, yeah, I'm listening.
Because you mentioned some of my papers, right? So
yes, I did, but I don't have time to say details.
Yes, your evaporation mechanism is one way of reheating the universe in non-oscillatory inflationary models.
Yeah.
But my question is, do you have to have the primordial black holes formed by a feature in the inflaton potential, like an inflection point, or is it possible to form some? I'm saying this because it's already very difficult to design successful non-oscillatory models of inflation. So if we have to also, introduce an inflection point, this would make it even more convoluted.
Indeed, but I think what you need is to have a population of mini black holes right after inflation. So somehow you must produce them. So if they are produced due to large perturbation, due to overdensities, due to amplified curvature power spectrum, or they are produced from other processes. I don't know. Maybe there are processes, for example, related to the reheating. I have heard, I'm sure that there are models that black holes are produced during reheating, and they have nothing to do with the inflation itself. It has to do only with
the... We're talking about non-oscillatory models, so there is no reheating.
Yeah, no, you're right.
Maybe instant reheating or something like that.
Yeah, that's true. Yeah.
Okay, we can talk about it later.
Yeah, but of course, what I can say is that what I presented it was a model that I constructed to be a runaway and to produce primordial black holes at the same time, but admit that these models were fine-tuned. Okay, it was very hard to construct them. Yeah, I don't know if it's possible to have. There must be maybe another mechanism that produces primordial black holes, but without traditional reheating. I don't know. Maybe there is. I don't know.
Well, let's thank the speaker again. And all the speakers of the session. Thank you very much to late stranglers that you stayed behind until this time. So the next and final session of this conference is tomorrow at 10. So the class is at 9. The class from the hotels is at